День добрый, меня кто-нибудь слышит?
Алло, Сергей,
Здравствуйте.
Да.
привет, это Петров.
Ага, добрый день.
Ну,
Хорошо.
я подзагружу прямо тогда перед докладом, да, не сейчас.
Так я сейчас это попробую, как у меня пойдет трансляция.
Ну ладно, давай, скажи тогда.
Сейчас. Сейчас это у меня пойдет. Так, 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 так. Так, демонстрация экрана. Ага. Так. Видно?
Да, видно.
Ага, отлично, хорошо. Я видео не включаю, потому что боюсь, что какие-то проблемы будут.
Угу.
Поэтому так вот. Ладно, хорошо, спасибо. Ну,
Ну
отлично
ладно,
тогда.
тогда я прям тогда перед тем, как говорить, я тогда подключу.
Ну все, я тогда все, спасибо большое.
Спасибо тебе.
Жду.
Hello, Christoph. Can you hear me?
Hello. Yes, I can hear you.
Okay, great. Let me start with you. If you can check your video, audio is perfect.
Yes. And
Also,
let
if
me
you
try
can,
to share the screen maybe to see if it's
right,
working.
right.
I cannot because there is somebody. Yeah, okay. So now I should be able to do it. So let me go there, share. So you should be able to see it now.
Right, right. Yes, I can see. Can you just move to the next slide once?
Yeah.
Right. Okay. Perfect. Perfect.
Okay.
So
Very
the
good.
slide transition is also perfect. Okay. Great.
Okay. So we'll stop sharing for now.
Right. Okay. So I move to Paul. Paul, yeah, your video is perfect. Can you hear
Thank
me?
you. I can hear you well. Yes, I was muted, so you're not going to be able to hear me if I stay muted. So hopefully that's okay now.
Yes, perfect, perfect.
Right. So let me try and share. How's that?
Yes, yes. And could you please make the transition to the next slide?
So excuse me, just a second. Hopefully that's okay now, and you can see.
Yes, perfect.
The
Perfect.
transition.
Yes.
Okay, great. Thank you.
Thank
I
you.
will stop
Thank
sharing
you,
and
Paul.
give you back control.
Thank you.
No.
Sergey? Hello.
Hi, I'm here.
Uh,
Try to...
can you hear me?
Yeah, sure. I'm here. Do you hear me?
Okay. Okay. Yeah, perfect. Could you please say, yeah, right. So
Yes, it's okay.
yes, perfect. Perfect.
I'm sorry I don't translate myself, so due some problem with network. But
okay,
I guess the slide is okay. Yes.
Yeah. It's
Okay.
it's perfect. Okay. That's good. That's good. Yes. So I move to the next speaker, Elena. She has not yet joined. Okay, let me move to the next speaker. Luciano? No, not joined yet. Okay, Vladimir? No.
Yes, I will try. I will try to.
Right.
For example,
Okay.
it's okay?
Yeah.
Okay, good.
Okay, and could you please make the transition to the next slide to see if that's working?
Excuse me, I go.
Right. Okay.
Well,
Okay, that's
très
great.
bien.
So we'll be waiting a bit before we start. Все. А со звуком что? А? Вот, сейчас включен. Да?
Звук с компьютера. Выключите звук.
А почему меня не слышно? Good morning, everybody. Good morning, Alexander. Yeah, good morning. Nice to see you and to hear you also. It's a great pleasure, yeah, at the conference that is organized in Moscow, as you know, yeah? Yes, absolutely, absolutely. And it's a pity, you know, this year that it's online. Yeah. But I'm very hopeful, like, you know, that next edition we will have double fun. Yeah, sure. That's no doubt. So no doubt. You see, we were waiting for the last moment before to declare that we are sorry that everything will be online. You see, we just announced officially. We have just arrived to this understanding more or less about in June, but we were waiting. Maybe some miracle will happen, but then we understood that it's not possible to wait, because people were asking when you send down us invitations, we have very short time to prepare visas. And and then that was probably our mistake, that we were waiting so long, just not they didn't say the truth, you see, because but no, okay, we're very thankful that nevertheless people are participating and everything. I mean, the speakers, the conveners are very well organized, so it will help. It is you provide, all participants and conveners provide a very reasonable help to organizers, because we have no any problem with all these adjustments. And also we have no experience, because this is the first time during the last year, 1.5 years, we used to give lectures online, yeah, but this is not like a big conference with a huge spread of time differences, as I just wrote, from +8 to -10. You see, it's nearly 24 hours time spread. Okay, well, probably we can start. Good morning, good afternoon, everybody. And I would like to give floor to Dr. Chodbury, for convening the session. Please, Samat, start, please. Thank you very much, Alexander. So at the very onset, as we discussed, we have a very robust program for the conference, in spite of it being online this year. And also at the very onset, I would like to mention that it's really a wonderful experience from my personal experience of the conference. It's a great conference in Moscow, at the beautiful city of Moscow, and at the prestigious Lomonosov State University, so where I have been. And not only the conference program, but the overall experience of excursions, the dinner, it's wonderful, actually. So hopefully we will be having it in the next edition. So our first speaker today is Christophe Royan. So Christophe is joining us from actually Mexico, in the California time zone.
So it's quite late in the night for him, and he told me that he might be logging out of like some time after his talk. Yes, Christoph, I don't delay you further, and I let you take the stage with the Odoron discovery by the D0 and the Totem collaboration, where Christoph played a leading role in this observation. Christoph?
Thank you very much, Somnath. Yes, I am just in the California time zone now, so let me share the screen. So I cannot share because you are displaying the program. So you need to stop. Yeah, thank you very much. So first of all, I would like to thank, the organizer for inviting me, to present this result, the discovery by the D0 and Totem collaboration. And I really look forward to meet again all my friends in Moscow next time when the conference is in person and not by Zoom. Okay, so I will start by introducing briefly the Odoron. Then I will discuss the Totem and D0 data. I will discuss how we need to extrapolate the Totem data to the Tevatron energy that allowed basically to compare the D0 data and the Totem extrapolated data that led to the discovery of the Odoron. So first of all, let me mention what we want to study. So what we want to study is elastic scattering at the Large Hadron Collider and at the Tevatron. So as you know, for elastic scattering, for instance, in proton-proton collision, the two protons are intact after the collisions. They are scattered at very small angles, or in other words, at large rapidity. So you see the red proton and the blue proton, and there is nothing else outside the intact proton in the final state. It means that basically, from the QCD point of view, since we have protons that are intact, we need a colorless object which is exchanged between the two protons, which is dominated, as we will see, by either Pomeron or Odoron exchange. So let me mention what is the Odoron, and starting again by proton-proton collision. Protons are intact in the final state, and in most cases, this is due to the exchange of the Pomeron. And as we will see, there are two components. So in the Tevatron or LHC energy scale, which are dominated by Pomeron and Odoron exchange. The difference is that Pomeron and Odoron, they correspond to positive and negative C parities. So it means from the QCD point of view, Pomeron is made of an even number of gluons, let's say it can be 2, 4, 6, 8, and so on, which leads to a +1 parity, whereas the Odoron is made of a odd number of gluons, as his name mentioned, which can be 3, 5, 7, and so on gluons, that correspond to a -1 parity. It means that the scattering amplitude for proton-proton case can be the sum of the even part and the odd part of the amplitude, whereas for pp bar interaction, it is the difference between the even and the odd part. So clearly, if you are able to measure the difference between pp and pp bar interaction, we can hope to see some evidence of the Odoron by, again, observing difference between pp and pp bar. So from now, it led also to the QCD picture. So you have this diagram, which is on the left, that corresponds to hadron-hadron interactions, where you have multiple gluon exchange, and you see that we have some ladders, and they are grouped by two gluons, they see in red. And this is described, this multi-gluon exchange, by the Bartel-Kwiecinski-Prasalovich equation. And Basarab-Nicolescu gave the definition of the Odoron, which is defined as the singularity in the complex plane located at j = 1 when t = 0, and which contributes to the odd crossing amplitude, as we just mentioned. So the image that we have is the drawing on the right, where you see the Pomeron. We have two gluons that are exchanged vertically. So this is this even number of gluons, whereas for the Odoron at leading order, you have three gluons that are exchanged. So again, what we are going to do is try to identify some potential differences between pp and pp bar. So before we go into the detail, let me tell you how the elastic cross-section look like as a function of t, where t is the quadri-momentum transferred square at the proton vertex that can be measured by tracking the protons or the antiprotons through the magnets of the machine. So what we have, first of all, we at very low T, let's say 10 to minus 3, 10 to minus 4, there is a so-called Coulomb region where we have a power dependence of the cross-section. Then we have the nuclear region. So the Coulomb was more QED, whereas the nuclear region exponential decrease of the cross-section. Then we have an interference region between the two. There may be or not some structure, and then at higher T, let's say above 1 or 2, we reach the perturbative QCD domain with a power decrease of the cross-section. So first, before I'm going to the Tevatron and LHC data, let me raise the question, why is the Oderon so elusive? Why didn't we observe it yet in previous experiments? And there were maybe some indication at the ISR, so there's some data at 53 GeV, where we compared PP interaction for the elastic cross-section, these are the black points, compared to PP bar interaction that are the empty points. And you see indeed that in a region of T, let's say between 1.1 and 1.6 GeV squared, you see some difference between these two interactions. But in fact, I was a bit easy when I told you that this kind of elastic events can be due to Pomeron and Oderon exchange, but at low energy, it can also be due to exchange of additional particles like the rho, the omega and phi meson, or also to region. So it means that the situation is quite complicated at low energy, and it's not easy to distinguish between all these exchanges, and this can become very model dependent. This is why this difference was not considered as an evidence for the existence of the Oderon, but could be due also to omega exchange. So where do we stand at the LHC? So let me just show you first one plot, which is a pre-LHC predictions, I mean, for all these people. And you see that the elastic cross-section that was predicted as a function of T was basically going on many different orders of magnitude according to the people. And some predictions were very flat. You see this black curve, for instance, and some of them were showing some maxima or minima. That is shown, for instance, for this blue curve. But I must say that not many people thought, in fact, about the Oderon. And so let me just show you, first of all, this kind of data from the LHC. This is from Totem at 7 TeV, which is the red and blue curve, and at 13 TeV, the green and red curve. So what you see immediately is when you go to even large values of T, we get a very smooth distribution. So you don't see this kind of minima and maxima that might be predicted before the LHC. You just see one minima and maxima at the beginning at low T, but then you get a very smooth distribution. So what it means is basically at the asymptotic regime at the LHC at high energy, we do not see this region and meson exchange. So it means that we can concentrate on Pomeron and Oderon studies. So if we see at TeV energy some differences between PP and PP bar interactions, we can be sure that it will be due to the Oderon. And this was the basic idea to study the differences between Tevatron and LHC data. So let me describe, first of all, the PP bar data. So in fact, the D0 collaboration at the Tevatron installed some Raman pod detectors on both sides of D0, just at the end of the data taking, and measure elastic scattering, as is shown on this plot, the sigma dt as a function of T, with a luminosity of about 13 inverse nanobarn for T, let's say, between 0.25 and 1.2 GeV squared. The Totem collaboration measured also many elastic cross-section at the LHC. What I'm talking about many is because we can run, first of all, the LHC machine at different center of mass energy. So it means that it will be quite important for the following, but it means that we'll have data at 2.76, 7, 8, and 13 TeV in the center of mass energy. And also the important point at the LHC, and it's illustrated on this figure, is that we can have different ways of injecting the beam of the LHC, or different values of beta star, which describe how the beams are parallel between each other. So you see this green curve, which is here, that corresponds to a beta star, which is very high, 2.5 kilometers, and the acceptance in T gives you values between 10 to minus 4 and, let's say, 0.1 GeV squared. But if you use another value of beta star, for instance, 90 meters, which is the bottom rectangular green area, it gives you acceptance between, let's say, 10 to minus 2 and 4 GeV squared in T. So by using the different values of beta star, we can get a very good coverage in T for the measurement. And we will see that it's also important for this Oderon discovery. So let me illustrate, 3 of the data set that were collected by Totem. So on the right plot, you see the data at 13 TeV, center of mass energy, and you see that these data are extremely precise. You don't even see the uncertainties of most of the points. Then in the middle, I show the 2.76 data, and we will see they are crucial for the Oderon discovery. And on the left, there are the 8 TeV data. And in addition, we have also 7 TeV data. So now let me discuss how the data look like. And for this, I just put on the same plot all the data by Totem. You see these 4 colors, 13, 8, 7, and 2.76 TeV. In the same domain of measurement as D0, so basically 0.25 and 1 GeV squared, as we said before. So what we see is that for all these data sets, we see the same structure. You reaches basically the data, the cross-section is going down, then reaches a minimum, then is going up, reaches a maximum, and decreases again. And we see this for all values of square root of S. But if you remember the data from D0, we do not see the same feature. The cross-section is decreasing, is more or less flat, and maybe decreases again at higher T. So the idea is to identify the features of the elastic PP cross-section data in a way that will allow us what will be the values, the characteristic at the same energy as the tevatron. So let me show you one sketch that defines a bit what we call these characteristic points. So this showed d sigma dt as a function of T for PP elastic interaction, and this is true for all square root of S of the Totem measurement. So what we define, first of all, is the dip, which is the minimum of the cross-section, the bump, the maximum of the cross-section. So these are the 2 characteristic points. And the idea is to identify 8 of them. 8 is arbitrary, but we choose 8 points that are characteristic of the shape of the elastic PP cross-section. So as I said, the dip and the bump. Then we define dip 2, which is the same value at the cross-section at the dip, but at higher T. And when I am talking about characteristic point, this is both the T value and the value of d sigma dt. Then we define mid1 and mid2 that is the middle in the cross-section between the bump and the dip. Bump 2, the same value of the cross-section at the bump, but at lower T. And finally, what we call bump plus 5 and bump plus 10, that correspond to 5 times the difference in cross-section between the bump and the dip, and 10 times the difference in the cross-section. So what I should mention, for instance, we use directly the data. So for instance, if we don't have a data point exactly at the bump, but slightly to the left, for instance, we will keep the data point in order to avoid some model dependent fits, but we keep the data points where they are. So the first observable, what we are going to discuss is the ratio in cross-section between the bump and the dip, which is of course the easiest way that we can think of. And the result is shown here. First of all, the ratio R, so again, the cross-section at the bump divided by the cross-section at the dip. The green points correspond to the ISR, so before the LHC measurement, you see that it's as a function of square root of S, so this is basically before 100 GeV. Then you see the Totem data for PP interaction, which are the black points, extrapolated to the tevatron energy of 1.96 TeV as the red triangle. So, and these are compared with PP bar measurements that are the empty points that are in the bottom. So already at this level, and we could extrapolate the Totem data because we do not see any square root of S dependence at very high energy, contrary to the ISR. And we have already at this level about 3 sigma difference between the Totem extrapolated data and the D0 measurement. So now what we are going to do is a more quantitative study, which is based basically on the 8 points that I just mentioned before. Again, all these 8 points that I showed you in the schematics. So let me show you first of all the results, and then we are going to discuss them. So what is shown on these 2 plots is the value of T as a function of square root of S and if the points correspond to the totem measurement for the different points that I introduced before. So you see that you have D2, mid2, the bump, and so on and so forth. And the value of the cross-section of the right, again, as a function of square root of S, which are the full point correspond to the totem measurement. And we use a 2-parameter function to extrapolate the Tevatron data that are the stars that are shown here. So which is 2 parameters in log square root of S for T and purely in square root of S for the sigma dt. You see that we use the same form for all characteristic points. And also we use different forms that these two, the two that are shown here at the bottom, which are the default, with 2 or 3 parameters, and they lead basically to the same extrapolated value within uncertainties. So let me do 2 remarks. First of all, you see how important the 2.76 data are. Because let's imagine that we didn't have this data. Then we would have to extrapolate some data at 13, 8, and 7 TeV down to the Tevatron energy, which is 1.96 TeV, which means that the range of extrapolation would be much larger. That's why it's crucial to have the 2.76 data. But people may ask, yes, but why don't you run the LHC at 2 TeV? Because then you could make direct comparison without this kind of gymnastics. And this is a good idea. But first of all, it's very difficult to run the LHC at 2 TeV. And second, we would have, in fact, no acceptance with our existing Raman pods in the region of the dip and the bump, which is here, where we compare with the D0 data. So unfortunately, it's not possible to have directly 2 TeV data. So basically, what do we get right now? So let me go back maybe a couple of slides. So we are getting this characteristic point that I mentioned at the value of the Tevatron energy, 1.96 TeV. And what we want to do is to compare to the D0 measurement that I showed you before. These are the measurements that we have. So what we need to do to do a direct comparison is to compare this D0 measurement in these T-bins that were measured by D0. And we need to predict the totem extrapolated PP elastic data in the same T-bins at D0. And for this sake, we are going to fit the 8 characteristic point that I defined here at 1.96 TeV. So the formula that we use is indicated here. So this is the double exponential that describes how d sigma dt varies as a function of t. The first exponential may describe the data up to the dip, and the second exponential above the dip. I should mention that this function is chosen for fitting purposes only, but still this kind of function describes all the totem data in the deep bump region at all center of mass energy, so 2.76, 7, and 8, and 13 TeV. I should mention that we use, as usual, all the correlation matrices in the fits, so that we know the full uncertainties on the fit parameters. So this leads basically almost now to the final result, except that I put something which is remaining under the carpet. What is it? It's because we have to take into account some possible difference in normalization between the D0 measurement and the totem extrapolated data. Why is it like this? It's because, for instance, D0 has an uncertainty on luminosity, which is of the order of 14.5%. So it's not a negligible uncertainty. So we need to some way to normalize both data sets between each other. And for this, we adjust the totem and D0 data to have the same cross-section at the optical point, d sigma dt at t equals 0, which is completely true if we have only Pomeroy exchange or the Oderon doesn't exist. But in the case of maximal Oderon model, we would predict a difference which would be of the order of 2%. And this is taken at an additional systematic uncertainties. So the first step is first to predict the total cross-section at the same energy as the D0 measurement, so about 2 TeV or 1.96 TeV. We do the same trick as before. So we have the totem measurement of the total cross-section at 13, 8, 7, and 2.76 data. We fit this data in order to predict the PP total cross-section at 2 TeV. and we obtain a value which is of the order of 83 millibar. From the value of the total cross-section, we can get the slope, the sigma dt at t equals 0 using the formula which is here. So this leads to a totem value of the order of 357 millibarn per GeV squared. D0 measures the same quantity to be 341 millibarn per GeV squared. So what we do is to rescale the data, the extrapolated data from totem by the ratio of these two numbers, which is 0.954. So this allows to get a global normalization between both data sets. Of course, we do not claim that we perform the measurement of the sigma dt at the optical point at t equals 0, because it would require much more measurement closer to t equals 0, but we use these two extrapolations to normalize the two data sets between each other. It means that we could have chosen, I mean, it's a kind of arbitrary value. We could have chosen, for instance, to normalize both of them at 1000 millibarn per GeV squared, for instance. What we need is basically to normalize the data set between each other, but we decided not to touch the D0 measurement and to rescale the totem value to the D0 measurement. So basically now we are getting the money plot already. So what you see on this plot is, first of all, in blue, the PP bar measurement from D0, again, in T range between 0.5 and 1. And they are compared to the extrapolated totem data, which are the red triangle. So you see immediately that we see some difference between, let's say, 0.57 GeV squared up to 0.8 GeV squared. In this region, we see the difference between the two data sets. And this can be interpreted as the existence of the Oderon, because as we mentioned already, the meson and region contribution becomes negligible at the TeV energy scale. So what we still need to do is to evaluate quantitatively the difference. And for this, we use the chi-squared method as usual. So the first term corresponds to the difference between totem extrapolated data and the D0 measurement. And we use, again, the full covariance matrix to take into account the correlations, plus the two constraints on the slope and also on the normalization. So if you do this, you obtain the chi-squared with 6 degrees of freedom, which has a p-value of 6 × 10⁻⁴, or a significance of the order of 3.4 sigma. It means that the difference between the D0 data and the totem measurement is of the order of 3.4 sigma. So now let me come to the last part, which discusses how we are going to use some other previous measurements from totem that were performed in the Coulomb nuclear region. If you may remember at the beginning of the talk, I told you that this region corresponds to very small t. It means 10⁻�3, 10⁻⁴. Whereas this comparison that we did, as I mentioned, something like 0.5 and 1 GeV squared. So in fact, this Coulomb nuclear interference region is a completely different data taking. So in fact, it was another value of beta star, even other detectors from totem. So these data sets are completely independent. That's why we'll be able to combine them later on. So the advantage of the Coulomb nuclear interference region is that, in fact, we are sensitive to the phase of the nuclear amplitude. So it means in this region, we can measure the value of rho, which is the ratio of the real part to the imaginary part of the nuclear amplitude at t equals 0, and also the total cross-section. And this was performed at 13 TeV, especially by the totem collaboration. And this is illustrated on these two plots. On the left, you have the total cross-section, and on the right, the rho parameter. They are compared to different kinds of parametrization that are coming from COMPIT. There are about 180 parametrization in these plots. The blue kind of the parametrization is a total cross-section, which has a log squared S term plus a log S term for the total cross-section. And the green series of parametrization has only a log S term. So you see clearly the total cross-section favors the blue series of parametrization, whereas the rho measurement favors at 13 TeV the green series of parametrization. And I should mention, for any of these parametrization, there is no Oderon. It's only Pomeron exchange. So if you introduce the Oderon, there is no longer tension between these data, and the Oderon explains clearly the difference between these two data sets. So in that sense, we may say that this is an independent way to see the Oderon. And for the model that are included in COMPETE, the totem row measurement at 13 TeV provide an independent significance of 3.4 to 4.6 sigma. And this we can combine with the D0 totem result that I introduced before. And if we combine it, since the data are independent, we obtain a significance of 5.3 to 5.7 sigma. Why is it a range of significance and not only one? Is because, as I showed you before, we get this range basically of parametrization. That's why you get different number of sigma due to the difference between rho and sigma tot. And I must say that this is true for all models that exist on the market. We always get something which is higher than 5.3 sigma difference. So it means that the models without colorless C-odd gluonic compound are excluded by more than 5 sigma. So this brings me to the conclusion. So we did a detailed comparison between PP bar and PP interactions. So the about 2 TeV data from PP bar from D0 and 2.76, 7, and 8, and 13 TeV from totem. We had to extrapolate the totem data to D0 in order to make the comparison. But already the ratio of the bump over dip shows a difference of more than 3 sigma between D0 and totem. Then we fitted 8 characteristic points of elastic PP d sigma dt data so that the dip, the bump, and so on as a function of square root of S in order to predict PP elastic interaction at 1.96 TeV. And then we obtained that PP and PP bar cross-section differ with a significance of 3.4 sigma in a model-independent way, and thus provide evidence that the colorless C-odd gluonic compound, or in other words, the Oderon, is needed to explain elastic scattering at high energy. When we combine it with the rho and total cross-section result at 13 TeV, the significance is in the range 5.3 to 5.7 sigma, and thus constitute the first experimental observation of the Oderon, which is a major discovery at CERN and Tevatron. So thank you very much.
Thank you, Christoph, for the very nice talk, the summary on the discovery of Oderon from D0 and totem. So I leave the room, open the room for questions. I see the first hand from Professor Petrov. Yes, please go ahead.
Hello, Christoph.
Hello.
And my question is, I already maybe asked it you before, but it is of general interest. Is it possible? Is it possible to extend your very ingenious techniques of translation of the data to the places where the data was not measured to other energy? For example, from low energy to higher energy, from 2 TeV to 13 TeV, etc.
Yes, yes, and yes, it's true that we discussed already about it, Vladimir, and I thank you for this question. I think it's, of course, a very good suggestions. So we should definitely try it. With one caveat, of course, that we know that at ISR energy, let's say below 100 GeV, the behavior of the data is very different. So that's why we have, of course, all this meson exchange, region exchange that make this data more complicated, let's say, to interpret. So it may be that it's not as easy to extrapolate from low energy to high energy, and it's easier to go from higher energy from LHC to lower energy. But this is a very interesting exercise. I completely agree with you. And again, we might get some surprise. So I think we had no time to do it yet, but definitely something that it should be pursued and should be done. I mean, this is completely true. So it's a nice suggestion. Yeah.
Okay. So nonetheless, we cherish a hope for that.
Yes. Yeah. Yes. It may be. Who knows? I mean, definitely it may be more complicated. As you know, I mean, better than me, but because we have all this difference, we see it already at the R value, that the behavior is very different at low energy, below 100 GeV, up to, if we compare it, above 1 TeV. And we don't know what is going in the middle, of course, because we don't have data points.
Okay, sounds fine. Thank you very much. Thank you.
Thank you. Thank you.
More questions from the room? No. Okay, Christoph, I have a very naive question. That's on this double exponential which you fitted there. So, yeah. So I was wondering, like, on the uncertainty in this function, like, you know, the fitting uncertainty. So can you elaborate, like, how much is it? What is the range of this?
Yeah, so what we use, as I said, is basically the full covariance matrix, I mean, to take into account the correlation. And in fact, the correlation for the totem data are point to point, I mean, in T, are much higher than for D0. So in first approximation, you could forget about the correlation between the D0 data and take only the correlation for the totem data. And the bin-to-bin correlation is very high. I mean, it's more of the order of 60, 70% or something like that for the totem data. So it's quite an important fact, I mean, to take this into account. And then when you do this, so the value of the uncertainties you see basically on this plot, because these are the error band is the band that you have here, which goes between the vertical error bar. So this is the kind of uncertainty that you get. So it gives you the order of magnitude.
I see. Okay. Thank you.
So
okay,
thank you.
Okay. Thanks a lot, Christoph. So if you have no more questions from the room, we move to the next speaker. Then
I apologize.
Thanks a lot, Christoph.
Thank you. I apologize that we'll disconnect soon because now it's past midnight here. Sorry. I'm sorry for that.
Okay. Good night, Christoph.
Thank you.
I can say. Okay, so now we are joined by Professor Paul Jackson from University of Adelaide. So from the other end of the earth, from California, we moved to Australia, and Paul would be speaking on the highlights of the results from the ATLAS and CMS experiments. So Paul, it's all yours. I allow you to take the stage, please.
Thank you very much. And I'll echo Christoph's sentiments of thanking the organizers and wishing we could all be together in person. Hopefully next year we'll get to come to Moscow. So yes, I'll be talking on behalf of the ATLAS and CMS collaboration today, presenting an overview and some highlights. So the physics at the LHC is the most ambitious and farthest reaching high energy physics program of all time. And this has presented us with a huge data set with an extremely well understood detector performance that's allowed us to make precision measurements to determine fundamental parameters, access to rare processes through probing poorly and untested corners of the standard model, and also, of course, introduced a broad search program at the TeV scale and beyond, so the high energy frontier, but also now looking at the sort of feeble interactions of the low coupling frontier. We've also, of course, been able to study new states of matter. And I would direct you, given the time constraints for my talk, to the various ATLAS and CMS talks throughout the conference for a lot more detail on some of the topics I'll flash today. So the LHC dataset from run 2 has been extremely successful. This is a goldmine for physics, with on the order of 140 inverse femtobarns at 13 TeV of good for physics data for both the CMS and the ATLAS experiments. And on behalf of my experimental colleagues, we all thank the LHC team for their dedication to these data and their commitment in view of run 3. This has led to a variety of breakthroughs. If run 1 was highlighted by the discovery of the Higgs, run 2 could be highlighted by the observation of all the main production mechanisms of the Higgs boson, observation of the Yukawa interactions with third generation fermions, constraints on the Higgs self-interaction, and evidence for Higgs to mu and Higgs to LL gamma. Rare processes, such as the observation of weak boson scattering modes and observation of other TTX channels and evidence for 4-top production, and a huge search program, excluding, as we know, a wide range of beyond the standard model parameter space, and also probing experimentally challenging signatures, such as compressed spectra, displaced vertices, long-lived particles, and unconventional signatures. So these results are only possible thanks to the excellent understanding of the detectors themselves and the development of advanced reconstruction and identification algorithms. So I flash a few plots here from the ATLAS experiment for electron identification, tau and B-tagging identification using advanced neural network techniques, and muons and jet energy scale. The take-home message here is that the very highly efficient object reconstruction at the percent level or better provides the understanding of this performance in data. A couple of other examples from Atlas here. On the left-hand side is showing lepton identification for muons in this case, down to very low transverse momenta of about 3 GeV. And on the far right-hand side, charm jet tagging, which has become a bit more of a hot topic throughout the Atlas and CMS programs recently. Touching on some of the CMS performance, the CMS muon trigger system has provided extensive measurements throughout run 2 of level 1 and high-level trigger performance, and we can see improvements as a function of year for PT and ETA here. And the comparison of the Z mass resolution on the left before and after the final calibration to include the legacy run 2 reconstruction is showing improvements as a function of absolute ETA. So again, the same take-home message that really excellent object reconstruction, allowing us to really probe the data in incredible detail. So from the Atlas experiment here, on the order of 10 to the 10 Z bosons have been produced in run 2. This allows the standard model to be tested in Z2L plus or minus with at least one jet of a PT greater than 100 GeV. So the standard model predictions with event generators up to next to leading order in QCD and electroweak can then test measurements of cross sections in extreme phase space, such as collinear and back-to-back jet emission. And this can then be fed into the various generators to improve modeling, especially in the collinear region and for high PT. Excuse me. The Z invisible width can be probed from a simultaneous fit to Z to nu, Z to mu, and Z to EE enriched regions. This is a beautiful result from the CMS experiment. Yields the single most precise direct measurement of the Z invisible width, as we can see on the right-hand plot here, competitive with the combined direct measurement from LEP. And I'd highlight the statistical uncertainty of this measurement being incredibly precise and the large domination of the error from the systematics. Sticking with vector bosons, vector boson scattering can provide a key test of electroweak symmetry breaking through vector boson self-interactions in cubic and quartic couplings. Characterized on this plot from the Atlas experiment, on this slide from the Atlas experiment, is the Z gamma JJ production, which is shown by jets with a large mass and rapidity gap. The signal strength can be extracted for the Z to invisible and Z to L plus or minus final states with very good agreement with prediction from the standard model, a 5.2 sigma observation of Z to nu gamma JJ, and 10 sigma observation of Z decaying in the charge lepton final state with a very precise measurement in this case. WWW production provides a rare process to give access to WZ self-interaction and cubic and quartic couplings again. The main backgrounds here are from diboson production, Ws and Zs decaying leptonically, and these are estimated with control regions. The Atlas experiment extracts signal using boosted decision trees here in 2-lepton and 3-lepton final states, yielding a first observation of this process with a significance of 8.2 sigma, a signal strength in agreement with the standard model of 1.66 plus or minus 0.28. And we can see one of the candidate events here from Atlas with a very clean event in the LHC with 2 electron candidates here in green and 1 muon candidate in the red track, and then the missing transverse momentum vector. Sticking with triple object production from CMS here, there's contributions to triple J-psi production from single, double, and triple parton scattering. And we can see the first observation of triple J-psi production with greater than 5 sigma significance from CMS here. This production is expected to be dominated by double parton scattering and triple parton scattering contributions. And this is a candidate channel for the first observation of triple parton scattering as a result of this. And we can see the measurement of the effective cross-section of double parton scattering compared to the same measurement in other processes, and very good agreement from the variety of experiments that are being highlighted here. Moving on to the top quark, there's on the order of 100 million TT bar pairs have been produced during run 2. This provides a environment in which to test the standard model with very high PT top quarks, where deviations might be expected from beyond the standard model contributions, and a measure of both the TT bar system and radiation. These provide standard model predictions from next to leading order in QCD and next to leading order electroweak. To do this, a lepton plus jets channel is used, and you can reconstruct a hadronic top quark, as is done by the Atlas experiment here, as a reclustered R equals 1.0 anti-KT jet with a high PT and a mass range around the top quark mass. Then measurements can be extracted as differential cross-sections provided for up to 16 variables, 8 of which are being used for the first time here for boosted top quarks. It's difficult for next to leading order event generators to model the additional radiation in these processes as well, and the constraints on this can place constraints themselves on effective field theory operators. One can also look for CP violation in semi-leptonic TT bar. The CMS experiment does this, measuring an asymmetry of 4 time-odd observables, which, if CPT is conserved, are also odd under CP transformation. The measured asymmetries, A prime CP, are affected by dilution effects due, for example, to misassignment of the quark and anti-quark in the system. But all the measured asymmetries shown in the lower plot here of raw asymmetries are consistent with 0. And this indicates there's no CP violation that's been observed in semi-leptonic TT bar. The single top quark polarization, the T channel dominates single top quark production. And we see high polarization expected from the V-A structure of charge current weak interactions. And this can test any beyond the standard model impact on the TWB vertex that may be present. This is a first measurement of polarization in 3 dimensions via angular observables of the leptons, electrons and muons, from a semi-leptonic B decay. And that's the 3 lower plots here. And the Atlas experiment places constraints on the real and imaginary parts of effective field theory operators using this analysis. Moving on to the Higgs boson, there's millions of Higgs bosons produced in run 2. And as I alluded to earlier, these have been used to test a variety of things, such as the Yukawa interactions with leptons. In this case, with the tau lepton, which is experimentally challenging to observe due to the numerous neutrinos that are produced in the final state, leading to poor mass resolution. Atlas uses multiple boosted decision trees to try and suppress the backgrounds from zeta tau tau and TT bar. The zeta tau tau is the dominant background coming from Monte Carlo, which is controlled by Z2L plus or minus data via a kinematic embedding procedure that's used to improve this background contribution understanding. This yields a gluon-gluon fusion significance on the order of 4 sigma observed, and for vector boson fusion, a little over 5 sigma observed. And there's a factor of about 2.5 improvement over an earlier analysis done with a smaller sample of run 2 data. We can see in the plot on the right-hand side here, for all of the various Higgs production mechanisms in Higgs to tau tau, good agreement with the expectation from the standard model. Sticking with Higgs to leptons, there's evidence for Higgs decay to mu plus, mu minus, with a beautiful candidate image here from the CMS experiment of a Higgs to mu mu emerging from gluon-gluon fusion. The signal strength, which has been measured in this channel, is 1.2, in good agreement again with the standard model, with an observation of 3 sigma. And we can see in the plot to the right-hand side here for the various particle masses and the prediction of the standard model Higgs boson for the couplings, there's incredibly good agreement now probing down into the 2nd generation. Sticking with the 2nd generation in this case, we can search also for the Yukawa interactions with 2nd generation fermions as evidence for leptons only thus far, and search for Higgs to CC bar in association with a vector boson decaying either to L plus or minus, L nu, or to pairs of neutrinos. This requires dedicated charm tagging, which, as I alluded to earlier, is something that both Atlas and CMS are working very hard on. The results are just a limit at the moment for Higgs to CC bar of less than 26 times the standard model cross-section, but getting close to making observations of VW and VZ with charm tag jets in the final state, which is an important first step to making this measurement, hopefully, or getting closer to this measurement in run 3. And here's one of the candidate events for the Z to mu mu Higgs to charm jets. In terms of di-Higgs production, direct access to the Higgs potential is arguably one of the last parts of the standard model that needs direct testing. There's a small di-Higgs cross-section, of course, which makes this a challenge to do, and a variety of experimental final states that can be used to probe di-Higgs production. One, for instance, is the BB tau tau final state, where you can use triggers from single leptons, leptons plus tau hadrons, taus decaying hadronically, and single hadronic taus and dihadronic taus. Various multivariate analyses are used to extract potentially signal over background, And this yields one of the most sensitive limits thus far in the non-resonant di-Higgs final state of less than 4.7 times the standard model, which has led to a factor of about 4 improvement over previous measurements. This is going to be one of the things that we look forward to seeing moving forward in run 3 as we try and combine all the various different channels of di-Higgs production. And here from Atlas is one of the candidate events that are included in their data set of Higgs to BB, Higgs to tau tau. Moving on to searches, there have been a huge number of searches performed at the LHC. We'll start out with some SUSY searches coming from the CMS experiment. They carried out a search for boosted and resolved Higgs to BB final states, where the B jets can either be in a delta R of less than 0.8 or a delta R of greater than 0.4, either contained in fat jets or resolved into smaller jets. And these results can be interpreted in terms of simplified supersymmetric models for direct electroweak Eno production in the 2 diagrams to the left here, in a GMSB model, or in a sort of standard MSSM type model, or strong production of gluinos decaying to Higgs, where the different final states would be characterized by the number of additional jets that we would be producing. Of course, there's no significant signal that's been seen in this final state, but the limits that are being placed here, for instance, on the gluino mass is now well above 2 TeV. In terms of electroweak SUSY, there's good motivation to think that electroweak Enos could be produced below the TeV scale. And this Atlas analysis looking for electroweak Enos is targeting a mass difference between the lightest supersymmetric particle and the next to lightest supersymmetric particle of greater than 400 GeV. And it's their first search with fully hadronic final states using large radius jets tagged either as Ws, Zs, or Higgs jets. And this has placed the strongest constraints from the Atlas experiments on electroweak Eno production decaying to Higgs, with limits scraping or getting close to the TeV scale at this point. So very, very stringent constraints being placed on supersymmetric models at this time. Moving to heavy particle searches, that's motivated by the hierarchy problem. We could expect new physics at the TeV scale. So a heavy gauge boson with right-handed couplings decaying, in this case, to a top-tagged large radius jet and a small radius jet that's B-tagged. This analysis from the Atlas experiment uses a deep neural network top tagger, which relies on jet substructure. And the discriminant then is the invariant mass of the top and B candidate. We can see the plot of this here comparing data with background, and there's no observed signal that's seen here, and limits are placed of greater than 4 TeV. Vector-like top quarks can be potentially produced singly, and these would lead to final states of electrons and muons with Z or Higgs tagged large R jets and small R jets, some of which could be B tagged. The effective mass is the key discriminant here, and there's no significant signal that's seen in this case either, with limits being placed on the order of 1.8 TeV. Moving on to perhaps more challenging final states, tri-boson resonances searching for decays via a scalar radion. This can decay to 1 or 2 reconstructed large radius jets, and results are combined with a complementary search using a lepton plus jets final state. We see again that there's no significant excess that's produced, as can be seen from the various signal region plots from the CMS experiments on this occasion, and very stringent limits are placed in this 2-dimensional MW-MR plane. In terms of flavor anomalies, recent results from B meson decays or B hadron decays seem to indicate deviations from lepton flavor universality. One potentially compelling solution to this would come from leptoquarks. And so at the LHC, we can search for direct leptoquark pair production. This is done in this case, relying on a missing transverse momentum trigger and looking for hadronic taus with greater than or equal to 2 B-tag jets. We can see in this case that limits have been set here up to on the order of 1.8 TeV for a vector leptoquark interpretation in the T nu and B tau final states of decays of this 3rd generation leptoquark. Sticking with lepton flavor violation, there's on the order of 10 to the 10 Z bosons, as I mentioned earlier, and lepton flavor violation has only thus far been observed in neutrino oscillations and is known to be negligible for charged leptons in the standard model, so would be a smoking gun of any new physics. Z2E mu searches have been performed based on normalization to the Z2EE and Z2 mu final states, and Z2E tau and mu tau searches with neural networks to suppress the key and rather challenging pernicious backgrounds here have also been performed. The relevant plots here are showing for the E mu final state, no significant bump in the E mu mass, and for the mu tau final state to the right-hand side here, no significant excess in the combined neural network output. The LEP limits have been surpassed by a factor of 5 for the Z to E mu and 2 for the Z to E tau and mu tau limits here coming from the ATLAS experiment. One final analysis coming back to CMS is looking for low mass, long-lived particles, where CMS has looked for displaced dimuons with a data scouting method. This allows lower trigger thresholds by recording a reduced information, keeping a low threshold and therefore unprescaled by throwing away information as opposed to prescaling. This gives lower mu1pt sensitivity and gives sensitivity to lower dimuon masses. In the plot shown here, the regions that are grayed out are vetoing the standard model resonances that would otherwise dominate these regions. And unfortunately, in this novel approach, there's just with one of these example exclusion plots, there's no significant excess that's seen for, as shown to the right-hand side, specific examples of potential new physics signals. So I'll just flash up the standard model summary plots from both ATLAS and CMS, probably taking only a few seconds to go through hundreds of PhD theses that have been poured into all of this incredible work to understand the standard model at 5, 7, 8, and 13 TeV. And just quickly touch on the long shutdown 2 activities. From the CMS experiment, there's been a variety of things going on. A new barrel pixel layer 1 has been installed. The HCAL readout has been upgraded, a new beam pipe installed, and gem detector first station has been installed also during the pandemic. And CMS are ready to keep moving on with the pilot test beam run very soon. To be ready for run 3, there's work on the B parking, which uses low PT displaced triggers, motivated by the several lepton flavor violation analyses, and they're studying how to further optimize these triggers. Data scouting with an aim to run particle flow at a higher rate has been evolving, possibly with additional level 1 triggers on GPUs or leveraging pixel tracks. And there's novel extensions to the long-lived particle program, both in the trigger at level 1 and at the HLT. The ATLAS preparations for run 3 have been dominated by the construction and installation of 2 new small wheels for the muon spectrometer, which are moving ahead at a lightning pace at this time. Improvements to the level 1 topological, Calo and muon triggers, and increased performance in the software algorithms are allowing us to make gains ready for run 3. So hopefully I've not gone too far over time and convinced you that there's an enormous body of work in recent times from both CMS and ATLAS. The results presented herein can all be found at the various links for both ATLAS and CMS, with some very handy physics briefings for ATLAS and CMS here. And everyone in the collaborations, I'm sure, are looking forward to run 3 next year as we prepare for collisions greater than 13 TeV. Thank you.
Thank you, Paul, for the very nice talk summarizing the results from ATLAS and CMS. So let's open the room for questions. I don't see any hand yet. Any questions for Paul? Okay, I have a question, Paul, regarding the di-Higgs production in BB tau tau, yes, which you showed in slide 23.
Yeah.
So here, so with regard to ATLAS, could you please let me know, like, what would be the improvement in the measurement, the uncertainties in the VBF mode when you extend the, detector coverage in terms of rapidity coverage for the HLLHC?
It's a great question. I don't have that number to hand. It is one of the sort of target analyses that we consider in terms of the upgrade work, sort of to showcase the performance of extending out to pseudorapidities of 4. So that's certainly something that's present in work we've been doing. I don't actually have a number in terms of how that improves the sensitivity, but it certainly does in the channels where we consider BJets, for instance. That's one of the key things. And so one of the poster child analyses for HLLHC is the 4B final state, where the timing detector being included behind the upgraded inner tracker adds this sort of extra sort of 4-dimensional tracking ability to that. So yeah, while I don't have a number, it certainly will add improvement to these channels, and that should be something at the HLLHC we're measuring with quite high precision.
Right. Okay. Like, thanks a lot, Paul. Because there'll be an extended tracking coverage as well as the timing. So, with respect to the VBF production, there would be like, with respect to this pilot projection and also, the jet measurements, the uncertainties would be significantly reduced. But okay, I think this is an also ongoing study at CMS with respect to what has been measured so far. So continuing this. Okay, so if we don't have any questions for Paul, let's thank Paul again for this very beautiful talk on the LHC results from Atlas and CMS. And let's move on to the next speaker, Sergey, who will talk about the results from the CMS experiment, the highlights from CMS.
Okay, hi, do you hear my slide? No, do you see my slide? Yeah. Okay.
Yes, Sergey.
Okay. Good morning, dear colleague. First of all, thank you very much for organizing this opportunity to be here. Also, many thanks the previous speaker for comprehensive report. I believe it saved some time for me. And today I would like, with great pleasure, to review results of the CMS collaboration. As you well know, the compact muon solenoid is one of the 2 largest experiments as the LHC. It brings together over 4,000 participants from the 51 countries. Among them, there are almost 3,000 scientists, over 1,000 engineers, and almost 300 technicians. My report includes highlights from the physics result of the standard model, Higgs physics, searches for new physics. Also, first, I am moving very quickly over current collaboration activity during the second LHC long stop and status of phase 2 upgrade. Today, the collaboration has published 1,058 paper on collision data. Here are distribution of this article over time, physics direction, and journals. Indeed, I do not have time to touch on even a small fraction of all these results, so everything that I will show is my personal choice and my personal point of view. But besides, I would like to draw your attention to the fact that 11 reports on the results of the CMS will be presented at the conference, so I address you to this report for details. In round 1, LHC was running with proton beam colliding at 7-8 TeV during round 2, which has separated from 2018 until end of 2008 with 30 TeV. For this time, the integrated luminosity recorded by CMS experiment has reached approximately 119 inverse femtobarn. It is expected that round 3 will start at the next year, and the value of integrated luminosity will be about 350 inverse femtobarn by the end of the 2024. According to the LHC timeline, starting from 2027, the LHC will be running as a high luminosity regime that will be allow increased statistic by more than one order of magnitude up to 300 inverse femtobarn by the LHC phase 2. Also, CMS collected and analyzed heavy ion collision. Review of these results were already presented by Sergey the first conference day. So the LHC long stop LS1 and LS2 were focused on phase 1 upgrade of the CMS detector to ensure effective operation at high luminosity at the nominal LHC energy. During LS2, works on barrel hadron calorimeter were completed. In 2019, crucial path of muon system upgrade finished in the last year, and the beam pipe and pixel detector installation were completed in this year. Also remain work to be done before end of LS2 is a yoke closing magnet restart as a cosmic runs. During LS3, the major LHC upgrade to the high luminosity is planned to ensure feasibility of the high luminosity physics program. At large scale modernization of the detector system is also a requirement. The related CMS phase 2 upgrade is scheduled for LS3, and the CMS detector system have to be upgraded to be able to run a significantly rising level of radiation. The mean pileup did not exceed 20, 30, 40 in run 1 and run 3, but it's expected to reach 40 in run 3 and about 140 for high luminosity regime. It will increase about factor 5, what impose additional requirement on the performance of the detector, the readout electronics, and data acquisition and analysis system. It also requires the use of radiation hard materials for detection, for detector element, and development of new method for experimental data analysis. And now, CMS reached excellent progress in all these projects. All technical design report prepared, and last 2 in this year. More physics projections for high luminosity started to appear, but that is beyond of my talk. Before moving on the physics results, I would like to show a couple of most recent examples of studies of detector performance. The first one is the reconstruction and efficient algorithm for electrons and photons with CMS experiments. The measured energy resolution electron produced in these boson decay range from 2 to 5%, depending the electron pseudo rapidity and energy. Recently, CMS also published paper on study efficiency on the muon CMS trigger system for level 1 and high level trigger. Significant improvement for success of the CMS physics program have been made to muon trigger system, very improving muon reconstruction and identification algorithm since the end of run 1 and through the run 2 data period. Also, beta-gain performance of the CMS legacy dataset 2018 was studied with the deep neural network. The discussion of the physics results, I would like to start with a slide with summary of the standard model test, which based on measurement of the total cross section for the different processes. From the very beginning, LHC capability provide enough statistics to study inclusive and differential distribution and make precision measurements. Deviation from standard model expectation may indicate the presence of new physics electron field theory interpretation, I guess today Katerina will provide a set interesting results on the subject. This is a summary plot for different electroweak processes demonstrate good agreement with standard model at the scale of cross-section from nanobarn to femtobarn. I address also to Alexander talk for details. Energy dependence of the Z and W production cross-section agree well with next leader for the calculation. An important result that I want to mention here is precision measurement of Z invisible width. This result is the first measurement of Z invisible width at Hadron Collider and is the single most precise direct measurement in the world, competitive with the combined direct measurement from the lab experiment. As I mentioned before, the LHC allowed to study differential distribution and in particular differential distribution of gauge boson over transverse momentum, the angular variable, and rapidity of electron pairs. In all these cases, no significant deviation from standard model prediction and NLO. The differential cross-section and charged asymmetry for inclusive double V production also provide important constraint of the Parton distribution function of the paraton in the small range of the Bjorken scale. Now I'm moving to the production of the massive vector boson pair, which is a key process for the understanding of boson-abelian gauge structure with a standard model and the electroweak symmetry breaking mechanism. Relevant information can be gathered measuring vector boson scattering and triboson production processes that occur through the electroweak production of jets in association with boson. Measured cross-section of production ZZ pair with jets with number of jets larger than 4 agree with leading order standard model prediction. A measure is also performed of electroweak production of W boson in a section with 2 jets. It is in agreement with leading order standard model prediction. The final state is also used to perform search for anomalous trilinear gauge coupling. Limit on anomalous trilinear gauge coupling associated with dimension 6 separator are given in the framework of the effective field theory. The next slide gives more details for study electroweak self-couplings with gauge boson pairs and triple production. The study boson production is important as the standard model of particle because it's sensitive to the self-interaction between gauge bosons via trilinear gauge couplings. Also, it allows study VBF and VBS mechanism test of high order correction, PQCD test, and search for new physics. All measurements are in good agreement with theoretical calculation and combined next to leading order quantum dynamics and next to leading order electroweak accuracy. Limits on anomalous triple gauge couplings are given in this table. The very important results is the very first observation of combined production of 3 massive gauge bosons. The observed significance of the combined production signal is about 5.7 standard deviation, and this corresponding measurement cross-section relative to the standard model production is 1.2. Physics with jets provide a test of quantum dynamics both in perturbative and non-perturbative regime, as well as it allows one to look inside the proton structure to measure PDF, measurement of the running consider running couplings, and so on. The current measurement of ZPT spectrum demonstrate agrees with next leading order in general better than leading order. The associative production see big work with gauge boson are used to probe the strange bottom quartz content of the proton. Again, for details, see talk by Olga. Azimuth of jet correlation are very sensitive to detail the pattern, showering, categorization, and multi-pattern interaction. And the next to leading order calculation match with pattern showering as implemented in Herrick. It gives better overall description of the measurement than the pair or hack methods. Starting from the round one LHC is really considered as a top factory, above 200 million quark pairs were produced during LHC round two. Also, the single top production was studied in details. Apart from dedicated talk by Frank Boyle, just a few major results. First of all, I would like to show that the top mass quark was measured with unprecedented accuracy even with round one data, and we expect that full round two data improve this precision. Then the running of the top quark mass experimentally investigated for the first time with CMS data. The analysis is performed using candidate event with electron and muon channel. The extracting running is found to be compatible with the scale dependence predicted by corresponding normalization group equation. In this analysis, the running is probed up to the scale of order about 1 TeV. And the last top results is the first direct model independent measurement is presented for the Habibi cooperation matrix element VTB. In final state, enriching singles top quark T-channel events, and the low limit for this matrix element is measured is 94% confidence level. Electronic B-meson decay offers an excellent opportunity to perform precision tests of the standard model because the minimal hadronic uncertainty is a theoretical prediction. For the decay B-mu, the evidence at the 3 standard deviation level has been obtained by CMS collaboration and combined on the round one data. The results are regularly reported by CMS for BS to mu, ranging frames of end effective lifetime, and from a search for decay B to mu. Combination of round one and round two data results to BS to mu is observed with significance of 5.6 standard deviation. No significant signal for B to mu is observed and only upper limit determined. These results are consistent with the standard model prediction. Overview of the Higgs with CMS, I start with measurement of Higgs mass. The recent combination of round one and round two data into gold decay to ZZ gamma gamma gives the most precise measurement about 1.1%. Since the discovery of the Higgs boson by CMS and Atlas collaboration, the extensive program of the measurement focuses on the characteristic, its properties, and testing its compatibility with standard model of particle physics. The Higgs to gamma gamma decay has a small branching fraction. However, it is a clean final state topology with two well-reconstructed photons provide a narrow invariant peak that can be used to effectively distinguish it from background. As a result, Higgs to gamma gamma is one of the most important channels for precision measurement. Measurements were performed within simplified temporal cross-section framework. This includes standard model signal stretch modifiers, production cross-section, and Higgs boson coupling to other particles. This permits measurement to be performed across the major Higgs boson production, including gluon fusion, vector boson fusion, vector boson associated production, production associated with top quark, anti-quark pair, and production is in association with a single top quark. I'm sorry. So, the major contain for the STC approximation was also applied for Higgs to tau channel for measurement of the signal strength and production of the cross-section and branch refraction. All results are found to be in agreement with standard model expectation. CMS also studied CP violation and anomalous coupling of the Higgs boson to vector boson and fermions. Kinematic of Higgs boson for lepton decay into gamma on this production station with vector boson, hadron jet, and topple pair jet. Here is the observed confidence level interval for coupling modifiers reinterpreted from the signal strength measurements in the field corresponding to the full combination of TTH and gluon fusion. As we see, there no deviation from standard model prediction. One of the most important results for the run 2 is the first evidence of couplings of the Higgs boson with fermion and the second generation. These results combine searches for the 4 inclusive categories targeting the production of the Higgs boson, its gluon fusion, vector boson fusion, associative production, and top anti-quark production. Here you see Higgs to mu candidate in gluon fusion channel, excess of event over background expectation is observed in data with significance of 3 standard deviation, where expectation for the standard model Higgs boson. The strange signal relative to standard model prediction is 1.19. So, differential Higgs boson production are sensitive probe for physics beyond the standard model. The new physics may contribute in the gluon fusion loop. The dominant Higgs boson production is LHC and manifests itself through deviation from distribution predicted by standard model. A new set of measurements designed to quantify the different Higgs boson production processes in specific kinematic region of phase space have also been presented. The differential cross-section as function of transverse momentum and rapidity of Higgs boson, the numbers at jet and transverse momentum and unique associative jets, all this variable was used in this study. All results are consistent within the uncertainty with expectation standard model. The limit obtained for individual couplings KB AKC in this region. Higgs self-couplings can be studied in Higgs pair production. We do not see clear signal for such processes to date. CMS only set limit on cross-section and the level 3.6 of the standard model. Also, CMS developed a broad program in beyond standard model Higgs searches. This program included additional Higgs invisible decay, lepton level violation, decay, and 2HDMA model. The search targeted the production of Higgs boson via vector boson fusion. The data are found to be in agreement with background from standard model. and observed upper limit are placed. The other study standard model extension postulates that additional approximate global symmetry with spontaneous symmetry breaking is sufficient condition for the existence of at least two new particles, He and A, both scalar whose masses are not constrained. CMS performed search for new particle in extended Higgs sector. Model-specific limits are set on production cross-section of these processes and extended Higgs sector with additional SU2 doublet of triple introduce a gauge to theory to heavy neutral of charged Higgs boson with specific signature. So we study double charged Higgs. Events are selected by requirement 2 or 3 electron or muons, moderate missing transverse energy, and 2 jets with a large rapidity. Also, no excess of event which respects the standard model background is observed. The LHC also could produce many long-lived particles, masses from MeV up to TV, that would lead to signature involving displaced vertex. The plot above shows the observed exclusion limit from CMS hadronic long-lived particle analyzed on the Bragg fraction of the standard model Higgs. The plot below demonstrates the observation exclusion limit from different CMS hadronic long-lived particles analysis on paired production cross-section for gluina in mini-split models. And of course, I should stop on the searches for heavy resonances. The presence of the new phenomena, both resonance and non-resonance in the high mass lepton state is predicted by various theoretical models. The standard candles for such searches are lepton pair in final states. The new searches now presented for full run-to data. No significant deviation is observed with respect to standard model. We set up a limit on the ratio of the product production cross-section and Bragg fraction to dilepton of new narrow resonances. This provides the most stringent lower limit to have to date on the masses of various spin 2, spin 1 resonances in the Randall Sandom and extended gauge boson. The another new CMS results is the search for V gamma resonances for mass range between 0.76 TeV. We set model specific upper limit on the product, the cross section for these processes. In specific narrow resonances benchmark models, heavy scalar triplet resonances are excluded for a range of model parameters. And the search for dark matter as LHC is one of the activity of exotic groups, the Atlas and CMS collaboration. The approach development during run and run 2 involves the use of simplified dark matter models, the description of interaction between dark matter and standard model. The effective approach makes it possible to operate with limit number new particle and add only one mediator of interaction from dark sector of matter to ordinary one and one dark matter, which is assumed to be fermion. In the simplest case, only S-channel processes are considered. More complex scenario also contain T-channels, processes, flower violation, vector mediator, extended Higgs sector, and gauge sector double porters with scalar and vector mediator. I show just two examples from CMS. The right plot is observed expected exclusion, demonstrate observed the expected exclusion region for mediator in dark matter mass plane for dijet and dilepton combined results. And the left plot is exclusion limit of pseudoscalar model as function massive moderator for a different value of missing ET based on documented searches. I believe the Maria will see it, will show it in detail. And this slide, I summarize the SMS exotic searches. The plot show limit in model parameter for various physics scenario in different channel. There is a limitation for contact interaction, the dark matter, RPV SUSY, the extra dimension, and so on. And my last slide before conclusion contains summary of results for supersymmetry searches. CMS has a rich SUSY search program which setting strong limit on many models. The current limit with run 2 data are presented on this plot for superpartner for the lepton, electroweak, boson stopes, quarks, and gluons. We see that no deviation from standard model prediction, and we can only set some limitation for a different scenario. And my summary, despite the pandemic, the SMS physics analysis, LS2 and phase 2 upgrade activity are going well enough. Many new analyses became public for summer conference and available as public physics briefing. Round 3 preparation and phase 2 upgrade go according to timeline, and we are looking forward and I hope to new physics. Thank you for your attention.
Thank you, Sergey. Thank you very much for the nice summary from CMS. So any questions from the room? If there are no more questions, let's thank Sergey again for this summary from the CMS experiment. And we move to the next speaker, Elena from EPFL Lausanne.
Hi.
Hi. So she'll be talking about the results from the LHCb experiment. Elena, yeah, okay, great.
Okay,
So,
can you see my screen?
Yeah, right. Okay, please proceed.
Okay, I hope you're hearing me well. So good morning. So I'm Elena from Lausanne, as you just said, and I'm going to show some highlighted measurements from the LHCb experiment selected among the results that we published or are being published in the past 12 months, more or less. So the LHCb experiment, I'm pretty sure most of you know, but it's a forward dump detector at the LHC dedicated to the study of heavy flavor hadrons, which are indeed produced in the forward region in proton-proton collisions. So the characteristics of this detector are great vertex and decay time resolution and the ability to perform a very high efficiency particle identification. In fact, it's composed from the rightmost side of the picture to the leftmost side of a vertex detector, which is called VILO, of 2 rich detectors, which are active in different parts, in different momentum ranges, and 1 tracker before and 1 after the magnet, as well as a set of calorimeters and pre-shower and a muon detector. So today, as I said, I just selected some of the results that we publish. I will not try to present an overview of all of them, of course, but I want to show you that LHCb is in fact a multi-purpose experiment. So I will also give a very short introduction to the LHCb upgrades at the end of this talk. But for more details, you can check out Paolo's talk 3 days ago, or Jacopo's talk today, or Surapa's talk on the 25th on selected topics. So let me start with oscillations, CP violation, and charm, which were among the original aims for which the LHCb experiment was designed. So to start with B0S oscillations, this is unique to LHCb. We can tag B0S versus B0S bar at production, and we have enough resolution in the vertex detector to measure the oscillation frequency with very high precision, as you can see from this plot, which compare the B0 S to and B0 bar S time. So we did this measurement with data collected in run 2 using B0S to DS minus plus pi plus minus decays. And we could measure the difference in mass between the two states with the precision that you can see here, which is in fact, I think, very good. On top of this, we did a combination with previous measurements, such as B0S to DS, one charged hadron and two pions, using a measurement that was performed using the full data set collected by LACB, further improving on the precision on delta MS. Also, charm mesons oscillate, and in fact, with this very recent paper, we provided the first observation of a non-zero mass difference in the system of the D0 mesons. So we can define two variables, x and y, which are respectively the difference in mass and the difference in decay width of these of the D0 bar states. And we have a lot of charm mesons at LACB because they are copiously produced, and we could analyze more than 30 millions of D0 to K short pi decays with a very small background. So the statistic was enough that we could use what we call the beam flip method, which is described in the paper that you see linked. This means that in every beam of the K short pi minus versus K short pi plus Dalitz plot, which approximately have a constant strong phase difference, we could measure the difference between D0 and D0 bar, accessing quite a good resolution on the X and Y variables, as you see described on the bottom right of this page. Before this paper, there is the global situation on X and Y was what is shown in the plot on the bottom left. And this paper shrank the uncertainties by a factor more than 2, I would say, on the two-dimensional plane. But this is not the only way to measure the charm mixing parameters. We actually measure them again in a huge analysis that was also aimed at measuring the CKM angle gamma. This is actually a huge combination of a lot of our measurements using something like 22 different decay channels and a lot of inputs from outside as well. And if you do this huge combination, you're sensitive to both to the CKM angle gamma and the charm mixing parameters. We included charm and beauty observables at the same time, and the final count was about 150 observables to fit 52 parameters. So this results in the most precise measurement of gamma by a single experiment, and we measured 65.4 plus minus about 4 degrees. And this is in excellent agreement with the global CKM fit, which has still a lower uncertainty, but this LACB is only a single experiment. What is also important is that we could, with this measurement, access the charm mixing parameters and improve the precision on Y that I just showed in the slide before by a factor of 2. So this was quite good. Another news, or if you want a confirmation, concerns the lifetime of the omega C0 baryon. You know, there are several charmed baryons, the lambda C plus, Xi C plus, Xi C0, omega C, and they include different quarks. And by first principles, you would expect a lifetime hierarchy that puts the omega C baryon in the shortest lifetime bin. However, 3 years ago, we measured the omega C lifetime, finding a value that was much larger than what we expect, and using semi-leptonic decays of this baryon. So we repeated this measurement using promptly produced C baryons decaying to pkk pi, and we measured simultaneously the lifetime of the omega C0 and Xi C0, and we confirmed the value of the lifetime that we saw in the previous measurement 3 years ago. And therefore also the new lifetime hierarchy that puts the omega C0 in the higher one of the highest lifetime bins actually. So this is kind of new, and I guess it requires a bit more theoretical work to interpret this result. let me move on to a topic which has become quite fruitful in LACB, which is that of spectroscopy. In fact, since the startup of the LAC machine, 62 new hadrons were observed by all experiments, of which 55 only by LACB. And about 15 of these are actually exotic hadrons, meaning that they contain 4 or 5 quarks, such as this one that we just observed in this very recently submitted paper. So we performed an amplitude analysis of about 800 BS to JPSI PP bar decays, and we studied the JPSI P and JPSI P bar spectrum, finding a structure which was unseen before that is consistent with a CC bar UUD pentaquark with a mass of 4,337 MeV and a width of about 30 MeV. Now, the significance of this observation, which is not yet an observation because we're missing the 5 sigma, ranges from 3.1 to 3.7 sigma, depending on what kind of spin you try to assign to this resonance, which is still unclear and requires a bit more data. Another very interesting measurement in this domain is the observation of a double-charmed tetraquark, which is not yet submitted, so this is a preliminary result. So for a bit of introduction, you would expect that the B quark is heavy enough to sustain the existence of a BB U bar D bar tetraquark decaying to 2 mesons. However, this conclusion is less clear for BC U bar D bar and CC U bar D bar. So these are all tetraquarks with 2 heavy quarks of the same flavor, so of the same sign. However, knowing the mass of the XICC++ baryon implies that the CC U bar D bar state should be close to the threshold for the production of a D0 and D star plus. So we searched in that mass window, and we actually did observe a narrow state in the D0 D0 pi spectrum near this threshold, which is compatible with the CC U bar D bar tetraquark. Now, this is a clearly exotic state because it's the first time we observe a tetraquark with containing 2 heavy quarks of the same flavor. The width of the bright thickener of this resonance is very narrow, 400 keV more or less. So this has a clearly resonant nature. The significance for the observation of this particle is overwhelming. It's about 22 sigma from the paper. And the significance for the fact that this is an actual resonance and not a D star plus D0 molecule is of the order of 4.3 sigma. You check this basically by checking that the resonance lies below the threshold for the production of these 2 mesons. Let me move on to a quite different topic. This is yet an unpublished paper, which is in preparation right now. LACB can also measure some standard model parameters, such as the W mass, which is one of the fundamental parameters. It is actually what limits the sensitivity of global electroweak fixed to new physics, because it's not known with a good enough precision. So usually at Hadron Colliders, it gets measured using the transverse mass, transverse missing energy, and the PT of the lepton in the W to lepton neutrino decay. What makes an LACB measurement interesting is not only that the achievable precision is quite good, but also that given the difference in the pseudo-rapidity acceptance of the, for example, of the Atlas and the LACB experiments, if you average the result between these 2 measurements, you can profit from a much reduced uncertainty due to the input PDFs. So at LACB, we fit the Q over PT of the 2 muons, so using both mu plus and mu minus, and the phi star, the decay angle. And we control the fact that the PT of the W, of the decay in W, affects this distribution by simultaneously fitting Z to mu plus mu minus. So using only the 2016 data sample for a pathfinder analysis, we find quite a good result. And let me stress that we already have 3 times more data than this already available for this measurement. So this result will be published shortly. Now, I want to move on to a topic that made a lot of noise in the last months, and this is that of the rare decays. And I will only focus on electroweak penguins, not on searches. So These are flavor changing neutral current decays, and they are powerful probes of new physics. Actually, LACB is able to probe branching fractions that are very low, from 10 to the minus 6, some of these decays, down to even 10 to the minus 10. These decays are forbidden at the 3 level, so new physics contribution can be sizable because nothing forbids, for example, a new particle from creating a 3-level diagram to interact in one of these decays. Now, decays mediated by a beauty quark decay to a strange quark and 2 leptons presented several anomalies in the past years, all pointing to a breaking of lepton flavor universality. Actually, in the last year, we published 8 papers on B2SLL alone and 2 on photon polarization studies in B2S gamma. The first of these measurements that I want to show is one that you will find on the archive tomorrow morning. And it's the update on the B0 and B0S to mu plus mu minus decays. So these decays not only are flavor changing neutral currents, as I was telling before, but they are also helicity suppressed. So they are expected to be very, very small in the standard model. On top of that, they have a single Wilson coefficient and a single hadronic constant in the decay rate, which is actually known to a very good precision. So this is something which can be predicted very precisely in the standard model, and therefore an even more powerful test of the validity of the standard model. So at LACB, the main problem is combinatorial background, which we suppress with ability calibrated on a data-corrected simulation. It's done quite well with a lot of attention. Further uncertainties are controlled by normalizing to 2 different decay modes, one that includes a dimuon like the signal and one which is 2-body like the signal. And the final result is what you see here, and it is shown, well, the mass plot in the middle of the page shows both the BS to mu mu and B0 to mu mu decay, and we could measure the branching fraction for BS to mu mu and put an upper limit at this time also for B0S to mu mu gamma, not only B0 to mu mu. So this is compatible with the standard model right now. Going forward, there is another thing you can do. You can check the differential branching fraction of the B2SLL decays, of course, excluding the CC bar resonances, because this is completely different physics. If you do that, we did that for several different decay channels, and we saw that there is a deficit of decay to muons in the B0 or B plus to K0, K plus mu mu, B0 or plus to K star 0 or plus mu mu, even baryon decays such as lambda B to lambda 0 mu mu and B0S to 5 mu mu, which is actually a measurement that we just updated. And it is shown in the last plot on the right. So further, the recent RK result suggests that decays to electrons are standard model-like. So there is something going on with muons here. So this new analysis of BS to 5 mu mu is both in agreement with round 1 and in 3.6 sigma tensions with the standard model prediction, as you can see from the plots in which the black points show the data points measured by LACB and the colored bar are always the theory predictions. Well, branching fractions suffer from some uncertainty due to the form factors. However, there are other observables, the angular ones, which profit from cancellation of most form factors involved. These are sensitive to Wilson coefficients, which can be modified by new physics. So we did perform this measurement in several channels. In the past year, we updated the B0 to K star 0 mu plus mu minus measurement, which initially showed a tension in the P5 prime parameter, which has been confirmed by 2016 data, yielding a global tension of 3.3 sigmas with the standard model. We also measured for the first time the angular parameters of B plus to K star plus mu mu, which also are in slight tension of about 3.1 sigma with the standard model. And we just submitted to the archive a paper measuring the angular parameters of B0S to 5 mu mu, which has much lower statistics and is consistent with the standard model at 1.9 sigma. However, apart from these discrepancies, what is interesting to see is to try to put all these observables together in global fits to the Wilson coefficients. And if you do that, all these three channels show coherent trends pointing to the fact that the C9 coefficient is actually modified with respect to the standard model. And they all point in the direction of about delta C9 being about -1. Finally, the most noisy measurement that we published this year was a lepton flavor universality one, comparing the amount of time a B plus decays to K plus and mu plus mu minus compared to how many times it decays to K plus electron minus. So these are a very clean theoretical prediction. This ratio, which we call RK, has to be 1, plus minus % level corrections, which are due to QED and QCD. But this is really very precise and very resilient with respect to possible other inputs, such as form factors. So at LACB, we measured this as a double ratio, normalized to decay modes that include the J psi to the lepton, in a way that reduced the systematics by far. We did this measurement with the full LACB dataset and found a 3.1 sigma evidence for the violation of lepton flavor universality. In fact, we measured RK equal 0.846, plus minus a very small error. So this is the first evidence from a single channel for the violation of lepton flavor universality, but measurements using other channels are going to be coming soon. As I promised, a small view onto the upgrade of the LACB experiment. So right now we are basically building a new detector down there, because we are keeping about 10% of the original detector channel and updating all the rest. We replaced the vertex locator, we replaced the tracking station, we are upgrading the readout of the reach of the calorimeter and of the muon detector. So this is just to show you how many channels we are keeping, which is the green slide with respect to how many things are going to be changed, which is the red part of the plot. I guess maybe the most important modification is that we are moving from a hardware-based level 0 trigger to a software-only high-level trigger. We are basically removing the level 0 trigger altogether, which will give us a lot more flexibility in terms of data selection and a lot more sensitivity in the analysis involving electrons and photons. For the upgrade 2, which we foresee for long shutdown 4, we will do again a great change of all the detector by upgrading the velo again. In that case, to handle that kind of occupancy, we will need a 4D pixel detector, not anymore a 3D pixel detector like the one we are installing right now. We will switch to silicon PM readout for the reach. We will replace the calorimeter. We will add a time of flight detector, add side stations side tracking stations inside the magnet to catch low momentum particles, and replace the tracker again. So of course the data processing will also have to be scalable and capable of handling this much larger bandwidth. So just to show you what this upgrade can give us. So of course the increase with statistics moving on to iLumi LAC will be huge and has a clear impact on the physics potential of the experiment, but also many systematic uncertainties themselves scale with the square root of n. For example, the data-driven templates that we use for the background estimations in many analyses. So we foresee that we can reach 1 or 2% precision on the lepton flavor universality ratios. And due to the new trigger strategy and the new detector, also access angular observables in the electron channels, which is a further huge test of lepton flavor universality. And of course, also the other parameters such as the CKM angle gamma will profit from much increased precision. As you can see from the plot, on the left that compares what we have right now with 5 femtobarn with what we could have with 300 femtobarn. So in conclusion, LECB originally was designed for CP violation and rare decays, but it has achieved much more, see for example the spectroscopy, and it is indeed become a multi-purpose experiment. Recent results include the first observation of a non-zero mass difference in charm and a confirmation of the flavor anomalies in B2SLL. And more studies are underway on other decay modes and especially also on the semi-leptonic decays B2CL new, which also show quite some anomalies. We are undergoing a major upgrade right now. We did suffer from the pandemic, but the schedule is on track now, also thanks to the fact that the LEC schedule was also postponed. The detector installation and commissioning is ongoing for some subdetectors and is going to start very soon for other subdetectors. And the real-time software-based trigger, which is being developed with a lot of manpower, will give much more flexibility. The framework TDR for upgrade 2 is in drafting phase, so it is not approved yet, but it's this is moving very fast. And we hope this will give us the potential to discover further cracks in the standard model and pave the way for new physics searches. Thanks. This was my conclusion.
Thank you, Elena, for this very interesting talk. And I hope in the very near future, we will see some new observations from LHCb with these very interesting results that are coming out. So questions for Elena from the room? If there are no questions, oh, okay, Paul has a question. Yes, Paul, please go ahead.
Hi, yeah, just maybe a tiny curiosity rather than a question. First, thanks very much, Elena, for this beautiful talk. This was lovely. Always great to see the incredible things LHCb are doing. On your slide 18, for the RK measurements, the Q-squared range changed very slightly from 1.0 to 1.1 in the later measurements. Maybe I missed something obvious, but what changed between the earlier 3 inverse femtobarn measurement and the later ones?
Well, okay, this is a very precise question. So I don't have a precise answer for you off the top of my head. I really don't remember why this was done. I think
I've probably looked at this plot, I don't know, 100 times, but it's the first time I've ever seen it. So
yeah. No, indeed. We did change actually for the arcade star measurement. We also changed the Q-square range, but we actually widened it. We expanded it up to 7 GV square. This is not published yet. It's still being finalized. However, moving to the 1.1, I think Jacopo can give more details because he has a talk on rare decays later, maybe this afternoon, if I'm not mistaken. But it's probably done to get farther away from the low Q-square bin.
Yeah, that makes
which
sense.
Includes the gamma resonance. However, I really don't have a definite answer. I'm sorry.
It's just more incentive for me to go to Jacopo's talk later. Thank you.
Any more questions from the room? If there are no questions, Elena, I have a question on slide 15.
Yes.
So this is on B0 to mu mu. So how much of improvement in the measurement you expect in the coming run, especially after this upgrade? And do you envisage a combination with CMS in the near future?
I think this is envisaged again. However, both experiments will have the precision to proceed on their own if they wish. I'm not part of this of the BS mu mu team, so I cannot say about the internal politics of combining with the CMS result. I think this would be a very good thing to do.
And how much of improvement in performance you expect in the B0 to mu mu for the next run, especially after this upgrade?
So this will really scale with statistics. We will increase the performance of the detector, but for a mu channel, this will not be so visible as it will be for an electron channel, for example. So you should really scale the square root of n, scale the result with the square root of n to have an idea of what the precision will be. Unfortunately, I don't have a plot for this right now, but
okay, no, but
I can't give you numbers.
But with respect to the systematics, for example, like, you know, the sidebands, like in the background estimation from sidebands. So the uncertainties related to that, do you expect that you have some new techniques or something coming up?
So, yeah, okay. As I said, many systematics also depend on the square root of n. Many other systematics depend, unfortunately, on the size of the Monte Carlo samples that we can produce. So, of course, that is also going to scale, but at a different rate, maybe than the incoming data set. So this is really difficult to foresee. It really depends how much CPU power we can put in producing our Monte Carlo samples and how many data we get from the detector. I don't have a clear prediction off the top of my head now, especially for the sidebands, which are a bit tricky.
Okay, and do you have BS2 tau going on or at LHCb?
Yes, we do.
Okay, and do you expect some new results soon?
I think Jacopo might mention this afternoon. I don't want to steal the play from him.
Okay, thank you, Elena. Let's thank Elena once again for this very nice, interesting talk from LHCb. And we move to the next speaker. The next speaker is Luciano from CERN. The ALICE spokesperson. So Luciano would give us the results, the latest results from the ALICE experiment. So I offer the stage to you, Luciano. Please, you may proceed with your talk.
Good morning, good afternoon, everyone. So let me share my screen and put it in full display mode. Let me see. All right, so hello everyone. So first of all, I also would like to thank the organizers for the invitation. It is really my great pleasure to give a talk on the ALICE physics highlights, status, and the future perspectives. So this is the outline of my talk. After a very brief introduction, I will discuss a few physics highlights, and then the status of the experiment, in particular in view of round 3, as well as the preparation of a bit more long-term upgrades. And for your reference, this is the list of other ALICE talks given at this conference. So let me start with a few quick words about the ALICE collaboration. We are at present about 1,000 signing authors coming from 173 institutes from 42 countries, including Russia, which represents a conspicuous contingent of the ALICE collaboration. Now, I do not have the time to introduce the ALICE detector in detail, but let me flash this picture just as a reminder that the ALICE detector is a central barrel with tracking, hadron, electron, and jet reconstruction covering 2 rapidity units, and the forward spectrometer covering the rapidity range from -2.5 to -4. And this is the data we have collected during the LHC runs 1 and 2, spanning from PP to lead-lead collisions at various energies. And we have at the moment a little over 350 papers published. We start now by presenting a few physics results. I will start with our core business, lead-lead collisions, and the study of the deconfined phase of QCD matter. so the quark-gluon plasma, which forms when the energy density is larger than 0.5 GeV per cubic Fermi, which is a value that is far exceeded in lead-lead collisions at the LHC and over a very large volume. Now, the results of lead-lead collisions cover a broad spectrum of measurements that address the various stages of the time evolution of the collision from the early phase when the two colliding charged nuclei pass through each other and produce the high-density expanding quark-gluon plasma, to the hadronic phase that precedes the kinetic freeze-out of the final state hadrons. And in the following, I've tried to select a few highlights from our recent measurements, which are representative of the various stages of the time evolution of the collision. So let me start with lead-lead ultra-peripheral collisions. So a powerful way of studying the initial stage of the nuclear collision is via ultra-peripheral collisions in which a photon produced by the strong electromagnetic fields of a nucleus interacts with a quark-antiquark pair from the partonic field of the other nucleus, producing a vector meson like ρ0, the J psi, or the psi2s. Now we have performed the measurement of the production across a section of J psi and psi2s as a function of rapidity. And this measurement then is compared with the impulse approximation, so the response without nuclear effects, allowing the extraction of the gluon shadowing factor, which turned out to be 0.65 at x of about 10 to the minus 3. And so these are measurements which allow constraining the models significantly. Moreover, we also performed the first measurement of the J psi production as a function of the Mandelstam variable T, which is the squared momentum transfer between the photon and the target nucleus. And this is sensitive to the transverse gluon distribution. So it provides constraints to the dependence of shadowing on the position of gluons in the nuclear transverse area. Now, let me, still on the same topic, but let me now move to the production cross-section of neutral pions and eta mesons at medium rapidity, which we recently measured up to unprecedentedly high transverse momenta in PP and proton-lead collisions using our calorimeters, the MCAL and the FOSS, as well as photon conversion techniques. Now I'm showing here the measurement of the RP lead, which provides constraints on the nuclear modification of the parton distribution functions. At low PT, there is a suppression of RP lead, which is consistent with theory predictions that also include the gluon shadowing or saturation effects. While at high PT, let's say above 10 GeV over C, we see that this is consistent with unit. Moving ahead, one of the characterizing features of the QGP is, of course, color deconfinement. And there the prime tool to study it is quarkonia. And the suppression of the J psi Charmonian state due to color screening, which was observed at the SPS and RIC, is historically considered one of the unambiguous signatures of the QGP. And here I show our results for the nuclear modification factor of the J psi in central lead-lead collisions, which actually reveals a suppression pattern which is fundamentally changed with respect to the one observed at lower energies. So at high PT, we have a suppression of a factor 5, which is described by models in terms of color screening and energy loss. While when we move to low PT, the suppression reduces. And this phenomenon is understood as the result of the fact that in a deconfined QGP, the charm quarks, which at the LHC energies are produced in large number, can recombine, regenerating the charmonium state. And this is qualitatively in agreement with the models. Now, this effect that, as I already mentioned, is seen only at the LHC and not at the lower energies, is also supported by the fact that when we go from forward to central rapidity, so from red to black in this plot, we see a larger effect, which is consistent with the higher density of C quarks at the central rapidity. Now, the effect of the quark gluon plasma on color charges are studied also with the measurement of the upsilon mesons, the measurement of upsilon production at forward rapidity indicates a strong suppression due to screening of strong interaction between the beauty and anti-beauty quarks in the deconfined plasma. Suppression that, as you can see now here, is flat in PT, indicating that recombination of BB bar quarks is small, as one would expect due to the much lower density. And the strongest suppression of the upsilon 2s state with respect to upsilon 1s, you see this, for instance, in this plot, which combines also results from CMS at the middle rapidity, is consistent with its lower binding energies, so with the expected hierarchy. Now, the data, the ALICE data shows a hint of a stronger upsilon 1s suppression towards a larger rapidity, a feature that is not described by most model calculations. Now, moving ahead with the evolution of the system, it is extremely interesting to study the expansion dynamics, which is described by hydrodynamic models and allows to extract the characterizing processes of the QGP. So here it is useful to consider non-central collisions in which there is an elongated geometry from the beginning. And then during the expansion by a pressure gradient, this maps into an azimuthal modulation in the momentum space, which then we analyze with the Fourier decomposition. And the second coefficient, V2, is called the elliptic flow, which quantifies the dominant elliptic modulation. Here I'm showing as an example results from xenon-xenon collisions. Of course, this has been extensively studied for lead-lead. And these are results for 5 different hadron species. And we see, as for lead-lead, that low momentum, a clear order in mass. So this suggests that particles participate in the collective expansion. There is a common flow velocity that imparts to hadrons an additional momentum, so a momentum shift, which is proportional to their mass. While at intermediate momenta, instead we see a clear separation between baryons and mesons, and this suggests that in this momentum range, the flow is carried by quarks and is then propagated to hadrons via an hadronization process, at least in part by recombination. Now, let me now move to measurements of the C and B quarks in the QGP, the measurement of their energy loss. It was anticipated nearly 20 years ago that B quarks, when traversing the QGP, would lose less energy with respect to C quarks, because due to their larger mass, they would radiate less at small angles due to the dead cone effect. And now we have measurements that are sensitive to this prediction. We measure the nuclear modification factor for non-prompt D0 mesons, which are represented here in blue, and compare it with the one for prompt D0 mesons in red in this plot. So they probe B and C quarks respectively. And we see that in the case of B quarks, there is less suppression, which is well described by the models that implement radiative energy loss with the dead cone effect. Soon in run 3, we will have more precise measurements with the new silicon tracker and larger statistics. Now, we have, I'm showing here now a new ALICE preliminary measurement, which uses machine learning techniques to discern the charm strange mesons, so the disabase that originate directly from the hadronization of charm quarks, and those that originate from decays of beauty hadrons, so the non-prompt disabase mesons. And these are then compared to our previous measurement of non-prompt D0 mesons, essentially to gain sensitivity to the production of beauty strange mesons, so the disabase. Now, the preliminary results show that the probability of forming beauty strange mesons in lead-lead collisions tends to increase with respect to that of forming non-strange beauty mesons, although the data is not yet fully conclusive. And the measurement is described by a theoretical model that includes hadronization of beauty quarks by recombination with UD or S quarks from the QGP. Again, also in this here, measurements with the upgraded ALICE detector during the upcoming run 3 of the LHC will certainly provide a firm conclusion on the matter. Now, I would like to show also some of the measurements in PP collisions, and here I come back to the study of the dead cone effect. Now, studying the pattern of the Patton shower is one of the key experimental tools in understanding properties of QCD. And this pattern is expected to depend on the mass of the initiating parton through the dead cone effect, which predicts, as already mentioned, a suppression of the Gluon spectrum emitted by heavy quark of mass M and energy E within a cone of angular size of M over E around the emitter. So a direct observation of the dead cone effect in QCD has not been possible until now due to the challenge of reconstructing the cascading quarks and gluons from the bound hadronic states. But by using new iterative declustering techniques to reconstruct the Parton shower of charm quarks, we actually made the first observation of the QCD dead cone. And this results confirms a fundamental feature of QCD. And moreover, the measurements of the dead cone angle constitutes also a direct observation, experimental observation of the non-zero mass of the charm quark. Now, the observable used to reveal the dead cone is built by constructing the ratio of the splitting angle distributions for D0 meson type jets and inclusive jets in the beams of the charm energy So this is given by this formula here, where the theta distributions were normalized to the number of jets which contribute with n splittings for a given charm energy AKT selection. And the measurements are reported in these plots in 3 radiator energy intervals, and showing significant suppression, you see here in this shaded area, of small angle splittings for the zero meson target jets relative to the inclusive jet population. Now, we also have performed a systematic measurement of charm mesons baryons production in PP collisions. So we have D mesons lambda 6 IC at 5 TeV and D mesons lambda C sigma 6 IC at 13 TeV. And these measurements enabled the determination of the total charm production cross-section with unprecedented accuracy, as well as of the charm fragmentation functions, so the probabilities of the various charmed hadrons to be formed. And we found that these probabilities are not universal, so they are not independent of the collision system as it was assumed for a long time. So the observed charmed hadron distribution in proton-proton collisions are actually very different from previous measurements at electron-positron and electron-proton colliders. For example, the probability of charmed baryons lambda C to be formed is about 3 times larger in PP collisions. Now, these ALICE measurements have stimulated an intense theoretical activity for their interpretation, mainly in terms of hadron formation mechanisms to take into account the surrounding environment of strongly interacting particles. Now, the last topic I wanted to talk about is the use of the LHC as a general purpose QCD laboratory. In particular, one of the things we have been studying is the QCD interaction between hadrons. We demonstrated in the past 2 or 3 years that measuring the correlation in the momentum space between hadrons pairs producing PP and proton-lead collisions at the LHC provides a very precise method to obtain the missing information in the interaction dynamic of any pair, essentially of stable and unstable hadrons. So from the measurement of the correlation function and the independent measurement of the source, we can infer the potential of the strong interaction. Now here I'm showing the results of precision measurement of the proton Xi minus and proton omega minus correlation, which allow to precisely determine the effect of strong interaction of these hadron-hadron pairs. So these results can be compared actually with predictions from lattice QCD with matching precision. So this accurate modeling of the small interparticle distance, which is of the order of 1 Fermi, together with the exact measurement of the correlation function, allows for the first time a detailed determination of the short range part of the nucleon-hyperon interaction, which results in this specific case with an attractive strong interaction in addition to the Coulomb interaction, which is shown here in green. But this is just an example. This has been published in Nature at the end of last year, but we have many new results. We in particular extended this also recently also to the charmed hadron sector and also to lead-lead collisions where we can also vary the interparticle distance. Now, in the last few minutes, I will say a few words about the work for RAM3 and preparations for RAM4 and beyond. Let me remind you that in this moment, we have just completed a massive update of our detector, the preparation of which started nearly 10 years ago. And now we are in the phase of a global commissioning of the fully upgraded detector. Now, these upgrades enable a large improvement of the vertexing and tracking precision and efficiency, especially at low momentum, but more importantly, they enable a 50-fold increase of the readout rate. This is, of course, quite of a large factor, and it's really going to help our physics program a lot as far as rare probes and a variety of other observables on which we cannot trigger are concerned. Now, the key items of this upgrade are listed here, but I do not have the time to discuss any of it in detail. Just let me remind you that the upgrade of the TPC with the replacement of multi-wire proportional chambers with gem-based chambers and completely new pipeline readout electronics is one of the key items to increase the readout rate capabilities. And we have a completely new inner tracking system, which is now going to be fully composed of ultra lightweight modules with monolithic pixels and also a immune forward tracker, which is also pixel based. And this massive increase of granularity in the innermost region of our detector and also the reduction of material budget will give more than a 3-fold increase in tracking precision, which is very important, for instance, for the study of AV flavor at low PT, as well as low mass dileptons. Let me also mention the new fast interaction trigger composed by several detector technologies with different functionalities, including the FT0 detector, which is a major Russian contribution that provides an interaction time with a resolution of up to 7 picoseconds. Now, this is for run 3. But the things do not just stop there. For LS3, so for 2025-2026, we have another exciting update of the ITS in preparation, which is going to involve the replacement of only the inner barrel of the ITS with essentially 3 truly cylindrical silicon maps layers based on a novel technology with much better performance. This again will reduce the material budget by another factor of 6. The LOI is approved, and we are now working on the R&D in view of submitting a TDR in the fall of next year. In addition, we also have plans for a forward calorimeter, the focal, which is going to be able to perform the measurement of isolated photons at forward rapidities. Here, the main goal is to constrain gluon and nuclear parton distribution functions with unprecedented precision down to 10x, 10 to the minus 6. Also here, the LOI is approved, and now we are working on the preparation of the TDR. Now, even beyond Run 4, going towards 2031, a bit more distant in the future, we're preparing an LOI for the so-called next generation dedicated heavy ion detector, Alice 3, which has a tracker entirely silicon-based, ultra-thin and fast, which would buy us another factor 50 in terms of luminosity, but would also have strong particle identification capabilities with TOF, reach, and this will also include a new calorimeter. This will give ultimate performance on the measurement of electromagnetic and hadronic probes of the QGP that allow us to address a variety of physics themes. So this initiative has received positive feedback from the European Strategy for Particle Physics Update. We're now preparing an LOI to be discussed with the DLHCC in the fall of this year. So we are much looking forward to have also this happen in a bit distant future. And with this, I would like to conclude. I have presented a few ALICE physics highlights showing the wealth of results that already came out in runs 1 and 2, and which allowed us to gain detailed insights into the QGP properties, as well as make advances in QCD at high density. But this is not all. There is more coming up, and we are very excited that there is a major LS2 upgrade being completed and on track to start a global, well, essentially, we are already in the phase of global commissioning. And as you have seen, we have more than that coming up during LS3, and we have more ambitious plans far ahead of us beyond Run 4. So that's it, and thank you very much for your attention.
Thank you very much, Luciano, and time for questions. I don't see any hands up. I have a small query regarding the focal. Is it a similar concept of silicon pad detectors with this 8-inch wafer technology, which the CMS HGCAL is implementing? Is that also for ALICE?
Yeah, so it is essentially that technology. So there will be around 20 layers of silicon pad, precisely using, well, whether this will be an 8-inch wafer production or a different one, even from a different vendor, is still to be seen, but it is essentially that concept. We're also targeting the use of the same electronics. However, and that's the peculiarity, there will be 2 layers of monolithic pixels, let's say in the pre-shower region at the shower peak, essentially to be able to separate photons coming from the pi-zero decay, you know, within a distance of a few millimeters. So that is the peculiarity of this detector. It's a combination of silicon pad for the measurement of the energy with very high granularity pixels of 30 micron pitch to have a very high spatial resolution.
Okay, thank you, Luciano. So if there are no more questions, let's thank Luciano once again for this very interesting talk with updates from the ALICE. And we thank you, Luciano. Thank you very much. So we move to the next talk from Vladimir. This is the last talk of the session. Vladimir, can you hear me?
Yes, I hear you. Okay.
Okay, the stage is yours. You may please proceed with your talk.
Okay. So, in distinction with all other speakers at this session, I'm a theoretical guy, so I will not devote much of time to experimental description, and either theoretical description also will not be described very much. And I will concentrate on very narrow subjects, but nonetheless, I believe that they are of interest maybe for everybody who presented this conference and at this session. New features of strong interaction are revealed by LHC. First of all, let me show some maybe not very good understanding which arose in my discussion with some colleagues at CERN, because some of my friends, they are eager to find out new physics, and they consider all the rest of experiment as something routine. But I want to draw your attention that in this part of so-called routine physics, many things are already done, are being done and will be done, while so-called new physics, unfortunately, is still without any firm results. So my personal opinion is that it would be better to spend all the manpower, money, and all that to do this part of it. But it's my personal opinion. I'm not the person who takes decision. So let's go closer to the talk. That strong interaction, certainly this is a very well-known picture from the very beginning of the LHC. It was demonstrated many times at many presentations. And the sigma total and sigma total in PP interactions. I show it just to remind you that all the rest of cross-section which are shown here, if we subtract them from the total cross-section, which certainly contain them, it remains already almost intact in the same. And this shows us, roughly speaking, that total cross-section mostly describes, in spite of all interactions are present, it describes nonetheless mostly, namely the strong interaction. But which strong interaction? Excuse me for elementary facts I try to remind you, but nonetheless I think to be comprehensible I should do that. And the lower energies, we have the very known, started from the Yukawa time, mechanism of exchange by mesons with such Yukawa-like potential. And concerning this part, it was partly consumed in the previous talk in the lower energy hadron interactions very nicely. But here also I remind you that the difference between the strong interaction coupling and, for example, electromagnetic coupling is huge. And so it means that perturbative means absolutely useless in the realm of strong interaction physics. I will say some word about it more later. So at high energies, we are normally consider a situation when the collision energy is very high, so we are in ultraviolet, while the transfer momenta are very low, tilde to zero. So here we are in infrared, and so this is a very peculiar interplay between the two. And if you see this elementary contribution from the spin J meson, you see that if we will limit ourselves with this so simple mechanism, it will be catastrophe, because for spin high enough, we will overcome all the upper boundaries which were imposed by the general principles. But if we, in some peculiar way, which I don't want to go into detail, sum up all one meson exchanges, will come to a very interesting result when all exchanges with fixed spin are traded to exchange with some object which also has spin, but this spin at that time is continuous, and moreover, it is running. It runs with transferred momentum. This so-called trajectories, and the object is called radial. There are two types roughly, plus and minus. Plus means the C odd. For example, this guy is C even, and this guy is C odd. The trajectories are divided roughly in C odd and C even trajectory. C even trajectory is considered as a leading agent of strong interaction and is called Pomeron, according to the Pomeranchuk contribution to this field. And what concerns the C odd, will be subject of our further discussion. Which theory should give us, for example, this expression in order to apply them in our phenomenological investigations, constructing models and so on. This is certainly the official theory of strong interaction is QCD. So we already almost half a century after the seminal work by Gell-Mann and his collaborator, we know that we believe that the fundamental theory is QCD related with this simple, very elegant Lagrangian. From this simple Lagrangian follow a lot of many interesting things related to nonlinear character of the gluon self interactions, which lead to our expectations concerning glue balls and so on. Now I want to draw your attention that the mass which is put here for generality, the mass here is mass equal for any kind of quarks. They are blank concerning the mass. But normally people consider, and this is my point of view also, that if we if we switch off the electronic part of the standard model, the mass should be put to 0, and we deal with massless quarks and certainly massless gluons according to the exact sp3 color symmetry. And this approximation is very good because we know, for example, there are very heavy arguments in favor of the fact that the nucleons, for example, they oblige their masses mainly to the gluon field, not the quark contributions. And so this approximation, this imagination of curious, strong interaction with massless quarks seems to be very feasible. But we should not forget some wise people, as cited here, that we are not to discover the truth, even cited the Taylor. And we see the application of this rule further. But now, prior to compare new features which were discovered at the LHC, I have to have something in mind, in hand, to be compared with. And so let me come back again to by half a century back, and to show you the energy evolution of the basic quantity in strong interaction, high energy strong interaction, total cross section, and the proton-proton interaction. And this is a square root of energy up to 7 or 8 GeV in the center of mass. At that time, it was considered a very large energy. And the question was, to which energy this permanency, this constancy will continue. The constancy and the flat behavior was considered a very natural, because in the Yukawa potential, the range of strong interaction is 1 over mass of the lightest agent of strong interaction. This is pi meson, and so it was considered absolutely even almost inevitable fate of cross section at high energy. Then this expectation would be supported by further step, which was related with cyclical proton synchrotron, which was during 4 or 5 years the most important and most powerful in the world. And that time, at this accelerator, very accurate measurements were made for PP and other channels total cross section, and they seemingly confirmed the constancy of the total cross sections at higher energy, except one dissident case, which was initiated by K plus meson, which is attracted. They grow. They demonstrate statistically significant growth. What was the reaction of those who discovered this growth? The conviction of the constancy of the total cross sections at high energy was so strong that they did not dare to say that this is something absolutely new. And they decided that afterwards, when the energy will grow more, this will come to the flat behavior, but at larger energy from below in distinction with other things. What happened then? A new era, which was opened by FNAL and ISR, showed that this expectation was wrong. And actually, it was 4 millibound growth discovered at the ISR of the total cross-section NPP interaction. And now the question was again the same. What will happen after that at higher energy? Will it come to the flat behavior, will grow forever, everlasting growth, or maybe nobody can exclude it, even decrease it. I want to remind that in spite of that time conviction of the constancy of the total cross-section, it was one dissident work made by Heisenberg in 25, where he argued in the language of very simple model that sigma in elastic and elastic cross-section should grow at logarithm squared of S. And it means that sigma total cross-section should also grow not less than logarithm squared. But that time it was severely criticized by Landau and his collaborators, and they blamed Heisenberg that he violated his own uncertainty principle in this model. And so this paper was put in oblivion for many years. Okay, but after discovery of the growth, all the community which was busy with this physics, they stopped to believe in constancy, and they rebaptized into believers of everlasting growth. Here I show you the point which were obtained, first points at 7 and 8 TeV by Totem, and 1 point was at 7 TeV obtained by the group Alpha from the Atlas experiment. And some people consider this result as not very impressive. They say, okay, we know that, for example, NTPP, antiproton, proton, they grow. And if we believe that Pomeranchuk theorem is good, Pomeranchuk theorem says that NTPP cross-section and NPP cross-section should be closer and closer to each other. So nothing special about this observation. I don't think that is very just conclusion, because actually without these points, for example, imagine for a moment that this point are absent, the data from the cosmic ray with these huge errors, they would give any space for any kind of development of events and any kind of development. That's why I think that this measurement was absolutely important and should be considered as quite new and contributing many to our knowledge. Now, what to do further? Again, this is the question, what to do? And there's some peculiar, very strange, maybe even counter-intuitive point, which I don't want to go into theoretical detail, but let me say you that if you take the Lagrangian with massless quarks, and if you insist that quark masses are given to them exclusively by the Higgs mechanism, by the spontaneous symmetry breaking, in this case, if you will ignore the electroweak sector, it can be proved from the pure chromodynamic with massless quarks that total cross-section should decrease at high energy. And the only possibility to allow the growth is the Higgs mechanism which gives masses to quarks. It seems to be a little bit strange because this is strong interaction, and such great influence of electroweak interaction, which is normally associated with very small coupling and so on, seems to be quite strange. But nonetheless, this is a fact of life, and I think a very interesting fact. Now, I come to the subject which I already presented in the excellent talk made by Christopher Young. It was claimed, announced 3 years ago that the oddball, or Oderon, the different name for oddball, the Oderon is a C-odd partner of the leading agent of the strong interaction of the pomeron, but with a C-odd, made also presumably of gluons. And the measurement showed that this value, I mean the tangents of the phase of the nuclear phase, achieves some 0.1. And from this observation, certainly it's very difficult to say, does it mean that the polygon exists or does not exist? But the reason to believe that this is a proved discovery of the Ron was the coincidence of this 0.1 value for rho retrieved by the totem collaboration coincided with the prediction from this model. This is Nicolescu-Martinov model of Rossaron maximal Oderon model. And this was the reason to say that the discovery was made. Let me be a little bit skeptic because actually it is well known that the rho value, this rho, is not the directly measurable quantity. It is retrieved, extracted from the data with help of some assumptions, and actually is model dependent. In order to extract this rho, you have to take one or another model for nuclear interaction, and in this way, it is. The value of it may be different from what was shown here. It was shown by many authors. So in this point, I disagree with the totem collaboration that this measurement, I have nothing against. I think that the data, the very data of d sigma over dt, the cross section is good, but the interpretation seems to be not very feasible. But good news is that it showed that public is still interested in elementary particle physics. That's very nice news. And Newsweek published a paper devoted to this discovery. Independently, is it true or not? It shows that the public is still interested in scientific research and will support us. That's very good. Now let's come to maybe more essential situation. Because to my mind, that the rho and forward observable, and rho is forward observable related to the forward scattering amplitude, is not the right place to search for the Oderon effect. Actually, the Oderon effect should be searched for in comparison with anti-PP and PP interaction, because only PP and anti-PP interaction, they differ from each other by some odd contribution, which is one sign in anti-PP and different opposite sign in PP. And we see that many years ago, already something was observed. You see that in the diffraction peak and to some extent in high T region, the cross-section, d sigma over dt, the cross-section PP and PPP is coincident, actually the same. And only in the narrow region around the deep, there is some difference which can be prescribed to something which is C odd. What can be C odd? Christoph said that that time it was hope, maybe explanation that this difference is due to secondary region exchanges. I mean, exchanges which are associated with Q and TQ exchange. But I would say that already at that time, if you take the models of that time, the contribution from the secondary mesons, Q and TQ mesons, is at best no more than 10%. But how to quantify this difference? My point is that if you take the ratio of the anti-PP cross section to PP cross section, then at the ISR energy, this constitutes around 3.5, with certainly 30% indeterminacy. But nonetheless, if we do the same thing, if we take the ratio of this excellently reconstructed data by Royon and his colleagues, we obtain thing which does not exceed 1.5. So 3.5 and 1.5, we see that if we enlarge the energy almost by a factor of 40 almost, so the effect of, if we believe that this is real Oderon, the effect of the Oderon decreases with energy. To say that this is a real discovery of the Oderon, I think I agree. This is discovery that really something odd exists, which is responsible for PP and anti-PP interaction, but its qualitative features certainly are to be discovered more. But this is, I think, the most clear evidence that the Oderon exists. Now, let us come to integrated cross section, and here you see the ratio of sigma elastic to sigma total. And at some energy, you have to slow it down, but there is some troubling discrepancy between the measurement made by Atlas and the totem. And this curve shows that with energy growth, the significance of elastic scattering begins more and more important. And in which way we mean that the elastic scattering is related with large distances. Why? Because if before this last attack, because it is related with large distances, and before last attack made here again, I want to draw your attention to I wait that Alpha Atlas collaboration will put the point here, and you see that this is starting. This big error. Don't pay attention to them. This is from cosmic rays. But if you take the Atlas data and the totem data, there is a starting discrepancy between them. They cannot be reconciled. If the data from the Alpha collaboration will continue to systematically go lower than the data from the totem collaboration, it would even indicate that maybe we have to decide who is right, who is not, first of all. But if, for example, the Alpha measurement would right, it would mean maybe the slowing down of the growth, which is very important also either. Now, when I said about the distances at which strong interaction happens, it was also the very nice measurement, a very interesting result from the totem collaboration. I mean, this point and these points also. So it appears that up to 2 or 3 TeV region, the average distance, because it is related very simple, average distance in impact parameter space between colliding protons follows to this linear in logarithm scale linear low, and something then happened at the point related to this measurement. What namely, if we take the distance between the 2 colliding protons in this region, we see that it is very close to quantum wavelengths of mesons, of pi mesons. Is it accidental coincidence? What does it mean? I don't know, because I was. It was very interesting for me to see that this the so close resemblance of the two. But to make some conclusion about that, I'm not ready at the moment. Now, concerning the very energy dependence of the interaction region, we should see that if we enlarge enormously the energy of collision, the growth, in spite of it takes place, it's very, very slow. If we compare, for example, the highest achieved interaction region at LHC at 13 TeV and compare it with the proper size of the nucleons, which can be extracted very easily from the electromagnetic form factor, we see that if we agree with the definition of asymptopia is a region of energy when we can neglect proper sizes of the nucleon. For example, this inequality should be respected, but in this region, if such inequality will be achieved, it would mean that the interactions they begin to become universal. It doesn't matter in this condition what namely you collide: proton, proton, pi, and so on. All cross sections should be the same. But if we can achieve this region, that's another question. If we ask, for example, for this radius not to be very much bigger, but even at least 3 times of the proper size of the nucleus, we find that it will happen at energy no less than 100 TeV. It's absolutely inattainable thing. It means that the evolution is very slow. By the way, if we consider the longitudinal evolution is very fast, it grows almost, but it is less observable because it is hidden when we take amplitudes and all kind of formalism and so on. So it's very difficult to find out the experimentally observed quantity which can say us something about the longitudinal extent. But what concerns the transverse, certainly it is in our hand with help of the slope in the differential cross-sections. Just to pictorially show you what I have just said, this is the transverse plane, and these are proper sizes of nucleons in collision. You see that at BNL, for example, they overlap, and protein they just begin to detach from each other. At us, they detach a little bit, and then LHC also they detach, but not very high, because if you take this size and this size, you have even not the factor 2 there. So what is the physical reason of this extremely slow evolution of the interaction region? I don't want to go into details, certainly it's not the place here to discuss. Just I remind you, for example, to be my argument maybe more comprehensible, if you remember, it still exists, the back model of hadrons, and the back is something with one type of vacuum surrounded by physical vacuum. It means it seems that in the course of PP interaction, there is some trend to expand outside, but it's very difficult because the perturbative vacuum inside the nucleons experiences a very large tension from the physical vacuum, and to come to the growth is very difficult. At infinite energy, certainly, if you will, such a fantasy that we have in hand arbitrary large energy, so we will come to infinite total cross-section if it grows everlasting. Then it will remain the electromagnetic case, because we know that if we take electromagnetic theory, the total cross-section is meaningless because it is always in vacuum. At least it is always infinite. And so there's a long way to the free exchange by gluons. The gluons are massless, but this road to the masslessness and the revealing of this masslessness is very difficult. But nonetheless, it goes, and LHC gives some contribution to this understanding. So now I want to finish my talk with the question which I already used earlier. The question which was the Apostle Peter asked Jesus Christ, "Where are you going to? Who vadis Domine?" We ask not the Jesus Christ, we ask LHC, and we ask the nature which surrounds us with dark matter, something like that. And the LHC general scope may be characterized by the following. The majority of experiments at the LHC, they are concentrated to spend huge energy to penetrate at smaller and smaller distances. But some experiments, for example, the totem experiment and the Atlas experiments concerning the total cross-section and soft processes, goes in different directions. So while here we investigate the inward horizons, here we try to investigate outwards horizon, so to say, and we go far. Now, some people said me, to one of my friends, when I told him about this, and he said me, so why to search for large distances spending so huge energy? One in the normal nuclear physics, we deal with one Fermi very easily, not only one Fermi, even 10 Fermi is not something extraordinary. Why to do? And my answer is that one Fermi at 1 TeV is absolutely different from one Fermi at 100 MeV. And in this unity of two trends, inside and outside, I see the dialectic unity of the LHC operation, and hopefully the last run will show us something which will confirm our position concerning these processes. Thank you very much.
Thank you, Vladimir, for this very insightful talk. Questions for Vladimir, very urgent questions, as we have shot over time by almost an hour now. No questions? If there are no questions, I thank Vladimir for this very nice talk, very insightful. Thank you very much, Vladimir.
Thank you. Thank you.
And before I pass on to Alexander, again, I thank all the speakers of this session for very interesting talks covering a range of wide topics. And I hope we meet very soon at the Lomonosov conference at the next edition at the beautiful city of Moscow. And also I would like to thank the organizing committee and the organizing committee chairman, Alexander, for a very well-organized online conference, which is very difficult for the first time. We are doing this, and Alexander, thank you very much for this robust conference, for the robust program, and very well organization of this conference. Thank you, and I pass on the baton to you.
Well, thank you very much, Samnath, for these words and for your very high estimations and the quality of the event. And I would like to mention that this has happened in a reasonable extent thanks to your efforts as the member of International Advisory Committee, and we appreciate your participation in the preparation of the conference. I would like to thank all the speakers of this plenary session for very exciting presentations. And also, being the organizers, I should be worried about a delay, but I think that this is one of the goals of this kind of events, that to stimulate exchange of ideas and discussions. And so we didn't spend time for nothing, but it was very interesting discussions after each of the presentations. And I would like to thank all the speakers for their efforts to make this conference interesting and important from a scientific point of view. So, but now I would like to say not good things, because we indeed quite late, and the tea break, as it is written in the program, will be only for 5 minutes. I'm sorry to say this, and we shall start as my colleague Konstantin indicated me, and just very actively indicate, because I have an idea to have at least 10 minutes, but he's insisting that not more than 5. So, and we shall start 11:35. This is the Central European Summer Time, or CERN zone time. So thank you very much, and see you just in a few minutes. Thank you very much.
Hey, Alexander, if you give me a chance to share my screen, I already can put my slides up maybe.
Hello. Hello, please do it. Yeah.
Thank you. Yes, I just bring them up.
Yeah.
Thank you. So, Alexander, could I commence with the session? Is that okay with you?
Yeah, so it seems it's high time to start. Yeah, okay.
Okay.
Thank you. Thank you very much.
Thank you. So we'll start with the next session. And as we can already see, Professor Katarina Lipka from Wuppertal will be presenting towards new physics through precision. Thank you.
Thanks a lot for the introduction, and thanks a lot, Alexander, again for the invitation to the conference. Well, I will talk today about the new way of analysis where we improve the precision of the standard model parameters and at the same time impose constraints on the new physics. So I'm talking about the jet measurement in the CMS, and what you see here in this beautiful picture in the background is one of the events of the data taking at the CMS experiment with these two cones showing the jets. So it's a dijet event production. So first, let's consider the general problem of particle production and proton-proton scattering as we have at the LHC. So the cross-section of any process is factorized out into the convolution of the proton structure on one side and the cross-section of the subpartonic process. So if we look first in the cross-section of the partonic subprocess, and you see that the strong coupling and the quark masses are the inputs to the perturbative calculation, these are fundamental parameters of QCD. However, as you know, the value of alpha S at a fixed certain scale and also of the heavy quark masses have to be determined experimentally. And therefore, these parameters have significant uncertainties. The parton luminosity, on another side, is based on so-called parton distribution functions of both colliding protons. And these parton distributions, or for brevity, PDFs, are functions of the factorization scale and of the X, which is the fraction of the proton momentum, which is carried by the parton. While the scale dependence of the PDFs is calculated in perturbative QCD, the X dependence still needs to be determined by using experimental data. So also the PDFs have significant uncertainties. So together with the values of the quark masses and of the strong coupling constant, the PDFs are inputs for any prediction for the LHC cross-section. Therefore, their precision plays the key role in the interpretation of the LHC data. PDFs are mostly determined from the data of deep inelastic scattering, for example, the electron-proton scattering at HERA. And since a decade already, LHC is providing high-precision measurements with additional sensitivity to the PDFs. And today I will discuss jet production at the LHC, which is sensitive to the PDFs and the strong coupling constant, but also the TT bar production, or top quark anti-quark pair production, provides additional information on the gluon distribution, the strong coupling constant, and also on the value of the top quark mass. What is the relation to the new physics now? At the LHC, as you know, we search for new physics either directly or indirectly. And in a direct search, we are looking for possible resonances, for example, here in the invariant mass distributions, where new massive particles can emerge as a bump in a spectrum. On another hand, in the indirect search, we look for the deviations of the measured continuous spectra from the standard model expectations. So, and the precision of QCD in particular plays here a very important role, either for sharpening the eventual bump in a direct search or finding the real excess in the spectrum. And in particular, for the indirect searches, the precision of the standard model predictions is very important, since these deviations might be extremely small. The indirect searches is very powerful method to look for new physics, since we can probe much larger energy scales or masses than the energy available in experiment. Just remember the observation of the continuous spectrum and the beta decay 100 years ago. We have been talking about the neutrinos a lot in the conference. And as you know, this observation hinted to the exchange of the W boson, and to that time, a fundamentally new electroweak interaction. So where do we expect a new physics now? For example, the standard model operates with 3 fermion families, as you know, but the stable matter is made of fermions from the first family only. So this fact is not explained in the standard model. And here the idea of the compositeness comes in. So the fermions could be made of more fundamental objects and obey to a new interaction at the scale, which is much larger than their masses. So either we can observe this kind of 4 fermion contact interaction via the compositeness, or the new interaction can proceed via the exchange of a particle with a very large mass, which would define the interaction scale. And this interaction scale usually we call lambda. So often new physics is modeled by these 4 quark contact interactions, and in particular in the case of the jet production sensitive to the contact interaction. The standard model Lagrangian is modified. So we are talking about the Smeft Lagrangian. So the standard model Lagrangian could be modified by including the dimension 6 operators for the color charged fermions. So here this Ci are the Wilson coefficient, and lambda is the scale of new physics. So in proton collision, such new phenomena are expected to appear as deviations from the measured spectra, for example, the jet spectra, from the standard model expectation. The challenge here, however, is separating the signal from the background, where in the signal we might have this contact interaction interfering with the QCD process, and we have the QCD process as the background. So the prediction for the QCD process is defined completely by the proton PDFs and is limited by their uncertainties. What can happen, we know from the round 1 Tevatron measurement, where basically they claim the observation of the contact interaction in the inclusive jet cross-section. So here you see this famous plot of the difference to the standard model with this excess at the very high transverse energy. In a later analysis, the QCD uncertainties were considered, and these are very large and come from the errors in the gluon distribution. So on this right-hand side plot, you see those are shown by the dashed red lines. So these are dominant ones. So now comparing the data and the standard model prediction, the excess was not significant anymore. And since then, the PDF uncertainties in such analysis are properly taken into account. However, there is also a well-known conceptual problem. You remember the PDFs have to be extracted from the experimental data. And just guess what is the major experimental measurement sensitive to the gluon distribution at high X. This is exactly the jet production at high PT, which we also use to look for new physics. So in such PDF fit, of course, only standard model is assumed. So any new physics effect, if it is there, can be already absorbed in the PDFs. So in a new analysis at CMS, we address exactly this problem. We measure the cross-section of the inclusive jet production at 13 TeV as a function of the jet transverse momenta and the absolute rapidity. So here on the left, you see the data compared to the QCD here on the log scale. And the data are shown as a function of the individual jet PT in the 4 bins of the jet rapidity. So these black points are the measurements, and the red lines are the QCD predictions at next to leading order. So this measurement is a standard candle measurement probing the pattern distribution and the strong coupling. So on the right-hand side, you see the kinematic plane for the PDF determination. So the y-axis is the energy scale, and the x-axis is the parton fraction x of the proton momentum. So this blue triangle shows the reach of the LHC at 13 TeV, and this blue shaded area is the kinematics, which is probed by this new CMS jet measurement. So at the same time, we would expect the contributions from the contact interactions, if any, to appear at high PT and very central Y. So here you see the prediction, so that is the ratio of the EFT improved standard model prediction to the standard model only for the jet cross sections as a function of PT, and in these 4 bins of rapidity as we measure. And these lines of different styles correspond to different models of the contact interactions. We can investigate purely left-handed, vector-like, or axial vector-like, depending on how the Wilson coefficients for the effective operators are related. And on the right-hand side, you see again the same kinematic plane, and now with the additional reddish area, which shows now the pattern kinematics where we expect the contact interaction contributions to show up. So we have to watch in particular the partonic X range here from 10 to the -3 to 0.5 approximately. So here you see the more detailed ratio between the data and the theory. Again, the black points show the data, and the statistic uncertainties are shown by these vertical arrow bars. This orange shaded band is the total experimental uncertainty, which is dominated by the jet energy scale. The theory is centered at 1, and this red dashed line show the uncertainty in the theory prediction due to the parton distribution uncertainty at next to leading order. Here we also compare the data to next to leading order, which is improved by the radius and threshold resummation to next to leading log. And comparing the data to next to leading order, the theory uncertainty also receives a significant contribution from the scale variation, which is shown here by this solid red lines. So you probably see it best here in this area. So these colorful lines otherwise show the next to leading order prediction using different global PDFs as available at the moment. And the spread between them is quite large, which also demonstrates that the dominant uncertainty for the theory prediction for the jet cross-section in proton-proton is due to the parton distribution functions. So having the data on hand now, we explore its sensitivity to the PDFs and to the new physics effects. And this we do in 3 steps. So first, we investigate the impact of the measurement on already available global PDFs. Then we perform the full QCD analysis where the PDFs are extracted simultaneously with the QCD parameters. I'm coming in a moment to that. And finally, we perform the SMEFT fit, so standard model effective field theory, improved fit, where in addition to the PDFs and the QCD parameters, we constrain the Wilson coefficients of the contact interactions. So a general idea of the QCD analysis is sketched here below. So you basically parameterize the PDF at a certain starting scale. Usually this parameterization is a polynomial. And and then these PDFs are evolved in a scale using the Diglop evolution equations. And we can construct the cross-section predictions for the kinematic plane covered by the measurements, either in standard model or also including the effective corrections due to physics. So, and then these theory predictions are fitted to the data, and all assumed parameters can be determined. Also, the masses of the heavy quarks or the strong coupling constant can be determined simultaneously with the PDFs, and their correlations can be then taken into account. So important to note that one cannot extract the PDFs from the LHC data alone. Therefore, one needs the deep inelastic scattering as the basis for the analysis. So here you see the first result of our investigation. Here I show to you the impact of the JET data on the global PDF, here CT14 PDF. And this we evaluate in so-called profiling analysis. Here in these plots, you see the uncertainty in the gluon distribution or in the singlet distribution for the original PDF CT14 next to leading order, which is shown by the red hashed area. And once we use the CMS inclusive JET cross-section, in addition, this uncertainty shrinks almost by a factor of 2 for the gluon in the full X range and for the singlet mostly in the medium X range, which is shown then the result in this band in blue. So we expect a significant improvement of the PDF precision once the global PDF groups use these measurements. Here you see the result of the full QCD analysis. So the full QCD fit in PDFs and the QCD parameters is performed. So as a basis, we use the HERA deep inelastic scattering data. And in addition, we include then the JET cross sections at 13 TeV, which I have just shown, to get the sensitivity to the gluon and the alpha strong. And in addition, we use also CMS data on the normalized TT bar cross sections, and these give us additional sensitivity to the gluon alpha S and also to the top quark mass. So in these colorful plots here, you see the result in PDFs as a function of X, shown at the scale of the top quark mass. And what is shown is the balance for the U and for the D quarks, the gluon and the singlet distributions. And these colorful bands show different uncertainty sources. Red is the fit error. It comes directly from the uncertainties of the experimental data which we use. This yellow band show the uncertainty due to the model assumptions like the masses of the charm and the beauty quarks, the strange content and the proton, and maybe actually the most important, the scale uncertainty. So it comes from variations of the QCD scales in the predictions for the JET and top quark production predictions. So this green band is the envelope of possible alternative parameterization. That's why it looks a bit funny here for the U balance. So together with the PDFs, we also determine the values of the strong coupling constant and of the top quark mass. And these values agree well with the world average and have also very competitive precision. Remember, these values and the PDFs are obtained at next to leading order, since we have only next to leading order for the top quark production data. So, and finally, instead of the standard model fit, we perform the SMEFT analysis. So the JET cross-section prediction is modified now by the effective contributions from the contact interactions. And these are available also only at next to leading order. Therefore, the SMEFT fit analysis is performed only at next to leading order. So the first thing we check is how the parton distributions change. So on the right-hand side, you see the parton distributions from the SMEFT fit with only fit uncertainty. So these are originating from the experimental data uncertainties. So this black line here shows the ratio of the SMEFT result to the standard model only result. So you see maybe there is some change at high X. However, it is well within the fit uncertainties. So we do it to be sure that we have no risk of absorbing any BSM effects into the PDFs. The values of alpha S and the top quark pole mass remain basically unchanged with respect to the standard model fit as expected. however, with maybe somewhat larger uncertainty due to the more freedom in the SMEFT fit. And what is new now in the SMEFT fit is that we also extract the Wilson coefficient of the contact interaction, and we assume different values for the scale of new physics. So here, for example, I show the coefficient C1 for the left-handed interaction, which just corresponds to this plot here, and where the value of the new physics scale lambda is assumed to be 10 TeV. So the cool thing about this result is that now the PDFs, the QCD parameters, and the CI Wilson coefficients are obtained all at the same time. So here you see the summary of the SMEFT result, assuming different values for lambda. So here is the ratio of the CI over lambda squared, which is also expected to remain constant. So for the standard model, it is 0, which is shown here by this dashed line. We have here maybe a slight indication of attention, but we cannot claim any observation of BSM effect because it's within 2 sigma. The conventional way to impose constraints on the contact interaction is a bit different. So usually one scans for the scale lambda for a fixed Wilson coefficient plus minus 1 for destructive or constructive interference with the standard model gluon exchange. And we also can translate our results into the exclusion limits. So if we do so, we obtained here this 95% confidence limit on the lambda for the 3 explored models. So these agree actually very well with the conventional Atlas dijet limit on the left-handed CI, which is 22 TeV. So by this analysis, we did the first step at the LHC towards the global SMEFT interpretation of the LHC data in terms of PDFs, QCD parameters, and the BSM effects all at once. So here I'm already at my summary, which is quite trivial. So thanks a lot for invitation and for your attention, and I'm ready for your questions.
Thank you very much, Katarina, for this beautiful talk. We'd have a few moments for questions if anybody wants to raise their hand or just speak up. Maybe I could start. Could you comment on what the prospects for run 3 are to be able to improve upon some of the results thus far, both from CMS and Atlas?
Well, first of all, the measurement which you see here, it's indicated by the number of the luminosity. That is only 2016 data. So it's not full run 2 analysis. The high precision measurements, as you know, require a bit more time than the searches, for example. So that's why it took us a while to understand the data to the level that we can present this high precision and high PT for the inclusive jets. So we just start the analysis of the full run 2 with the improved calibration. And here, as you see, this orange band basically corresponds to the uncertainties in the jet energy scale. So we are working on understanding the jet energy scale better. We have the new reconstruction in CMS. I think in your talk you mentioned the legacy reconstruction from the CMS. So that is a data which is based on, and now we have the ultra legacy reconstruction where the calibrations are improved. So we are working on the run 2 analysis first. And then for run 3, we have a few ideas to improve the jet reconstruction actually by using the machine learning methods. And that would be the prospects, at least for the CMS.
Thank you. That's a comprehensive answer and very, very exciting to hear this. And of course, I resonate your point that the measurements do take a lot longer to put together, but these are great results that are worth the investment of time. So thank you for the answer. We have time for another quick question if someone wants to raise their hand. I don't see one. Very clear talk. Thank you again, Katerina, for this lovely presentation.
Thanks a lot. And I stop sharing now.
Okay, thank you. We can move on to the next presentation. It's from Professor Dmitry Kipichnikov from the Institute for Nuclear Research in the Russian Academy of Sciences. Dmitry, are you there?
Yes.
I think I saw your name. Yes, good.
Can you see my slide?
We can see your slides, yes.
Okay,
and so the floor is yours.
Slide presentation. Okay,
thank you.
Okay, let me thank our organizers for invitation. In my talk, I'll present you the recent result from the NA64 facility, and I mainly concentrate on the new physics results on A64. Here is the outline of my talk. First, I would like to tell you about the motivation of NA64, which is associated with the light dark matter and the G-2 anomaly. I briefly discussed the vector portal model to the dark sector, and invisible mode stop when particles from dark sector decays into invisible dark matter particles. So I would like to tell you about the axion-like particles which can decay visibly and invisibly. The another motivation of NA64 is the atomic anomaly, and I would like to tell you that NA64 experiment is sensitive to G-2 electron anomaly. So we discussed the new result of NA64, which is associated with the resonant dark photon production, and perform combined prospect results for the NA64 electron and NA64 mu experiment. So next, I'll come to the conclusion finally. So this is the motivation of NA64 experiment. So the light vectors which have sub-GeV masses are very popular candidates for the solution of some experimental anomalies, such as G-2 anomalies, mini-boon, atomic anomalies, Koto, and Xenon. These particles could act as a mediator to the dark sector. Dark sector consists of the particles and fields which are singlet with respect to the gauge group of the standard model. So it interacts with standard model, presumably via gravity or possibly via new interaction transmitted by the mediator. So the most popular models of dark matter is the scalar dark matter, major N dark matter, and pseudo-dark dark matter. So in my plot, you can see the typical parameters which are associated with such types of dark matter in terms of couplings which can be recasted to the dark matter abundance. My next slide is the additional motivation for the NA64 mu, which is stated with the G-2 mu anomaly. So recently, in April, Fermilab, the experiment in Fermilab showed that there is a tension between a standard model prediction, theoretical one, and the experimental one. So if if there is such tension between experiment and standard model, we can suppose that there is additional particles beyond standard model, such as A prime, such dark photon, say, model, and these particles gives the additional contribution to the G minus 2 muon. So, and in A64 experiment can also probe these particles at the one loop level. So, my next slide is the short introduction into the vector portal model. So this model was suggested by Okun and Haldon. So we can see that in this model, dark photon couples to the photon via kinetic mixing. There is also interaction between dark photon and dark matter particles, which correspond to the dark sector. If we get rid of that kinetic mixing, we can redefine the variables, and in this case, a dark photon acquires the interaction with the electrons. So in A64 experiment, we can probe dark photon Bremsstrahlung-like processes like that. So we mainly concentrate on the mostly visible decays of dark photon in our study, when A prime decays into E plus and minus, hadrons, and so on. And another benchmark case is the mostly invisible signature of dark photon, which corresponds to decay into dark matter particles above the threshold of the dark matter. So we also assume that A prime decays mainly to that particles. So that that's this one. Okay. Here is the experimental setup of an A64 experiment. So in our collaboration, we have about 50 researchers from 12 institutes. This experiment was proposed in 2014, and first run was in 2015. So this is the location of an A64 experiment. It locates in north area of SPS. The electron beam is produced by the protons of 400 GeVs, and the secondary electrons of energy about 100 GeV collides with the target of an A64. Here is a photograph of experimental facility. So the A64 experiment is active target facility, and the target of that is the ECAL, and we also install HCALs modules to study the invisible mode decays of the dark photon. This design was suggested in this article. So the main components of the experiment is the clean 100 GeV electron beam. So the electron target system plus synchrotron radiation detectors. There should be very hermetic ECAL and HCAL. So the signature of which corresponds to the decay of A prime is the initial energy. In the initial state, we have the electron beam of 100 GeV. In final state, we have energy deposition in the ECAL, which corresponds below to 50 GeV, which corresponds to the electron which emits A prime, and the prime decays into dark sector, say, in dark matter. So, and there is no energy in veto and HCAL. So a background can be associated with the muons, pions, and K meson decays in the fly. So the background also comes from the upstream interaction of the electron beam. So, or maybe energy leak from the ECAL and HCAL. So we also developed new DMG package, which is fully compatible with Gen 4. And we published the result in the computer physics communication recently. So it can be used in any full simulation program which is based on Gen 4 toolkit. In our toolkit, we can simulate electrons and muon Bremsstrahlung-like processes like that. So we also can study gamma conversion to ALP. ALP is external particles, and annihilation process like E plus or minus to A prime to E bar. So we can also study the dark matter messengers, vector axial, vector scalar, pseudoscalars particles, and study invisible and visible decays to the standard model. For total cross-section, we use the full matrix element. We don't rely on the equivalent photon approach when we calculate the cross-section. So we call it exactly level matrix element. So we also continue to develop the package, implementing more exact Weizsäcker-Williams cross-sections in the simulations. The next slide is the design of an A64 active target facility for the invisible mode study. In the left side, we can see the experimental energy deposition in HCAL and ECAL. So this line corresponds to the standard model distribution of the energy. And an A64 allows to probe invisible decays of dark matter for general X boson. So if the X boson, if the electron emits X boson and X boson decays into dark matter, so we would have the energy deposition in the signal region in ECAL. So the signal box of our setup is no energy deposition in ECAL below 500 GeV, 50 GeV, so sorry, and no energy deposition in ECAL. The next slide is the current and future sensitivity of an A64 to the dark photon in terms of mixing with photon and couplings which are associated with dark matter abundance. So this is the current limit and the prospect limits. Invisible mode data taken we have run in these years. So the combined analysis for this run for invisible mode corresponds to the approximately 3 times 10 to the 11 electrons on target. So there was also a long shutdown, and the data taken. We resume our data taken in August of 2021 during 5 weeks. So our goal is the beam setup and electrons upgrade. We want to reduce the background from the electron-nuclear interaction along the beam line. So, and the ultimate goal is to accumulate then to the 11 electron target in 2021. So, and 5 times to the 10 to to the 12th electron on target before LS3. So my next slide is the setup for the study of dark photon semi-visible decays. This is a new preliminary result, which is submitted to arXiv. So this result is motivated by the G-2 muon anomaly, which can be explained due to the A prime with masses below 1 GeV. So the signature of this setup is the Meson energy events in ECAL and the sound model particles pair production and the HCAL. So the next slide. As I said, the Na64 experiment is also sensitive to the axion-like particles, which are predominantly coupled to the photons. And we can study that with that signature. We can study the production of axion-like particles in the Primakov reaction, which is labeled here. To study that signature, we consider the following requirements: the null signal on Vito and HCAL1. So for the visible decay of axion-like particles into 2 gammas, we want to have decays into 2 gammas in HCAL2 and HCAL3. And for the invisible decays of axion-like particle, we would suppose that LP decays outside the detector. So this is a current result from the experimental data, which is published in VRL. And on the right plot, projected limits for the Na64 before LS3 shutdown. So we also plan to consider invisible decays into dark matter, mainly when axion-like particle decays mainly to the dark matter particles without any visible energy deposition. Okay. So as I said, also the Na64 experiment is also sensitive to the G-2 electron anomaly. There are 2 different results for the for the G-2 electron anomaly. The first one corresponds to the negative contribution. The negative tension between experimental and theoretical result, and the recent result corresponds to the positive contribution, positive tension between experimental and theoretical result. So what can we do? We can suppose that there is additional particles, say scalar or pseudoscalar or vector and the axial boson, which can contribute to the G-2 electron anomaly. So in this plot, you can see the coupling versus mass of generic X boson and an Na64 result for the generic boson, which decays mainly invisibly, mainly to the dark matter particles. So this result was published recently in this paper. So regarding the visible mode of Na64 setup. So recently, the Atomki experiment has reported the observation of 6 sigma excess of events in the invariant mass of the distribution. If we can explain that anomaly by supposing that there is additional bosons, scalars, say pseudoscalar or vector like, which has a mass about 16 MeV. So if this boson exists, so it can decays into E plus, E minus. It can be produced in the Bremse-Strachlung process in the tungsten calorimeter of Na64 mu, and it can decays into fiducial volume of Na64. And on the left side, you can see the exclusion limits of Na64. We can cover almost half of this anomaly, and a red line corresponds to the unconstrained parameter space of atomic anomaly. So on the right side, we can see the coupling, which corresponds to the pseudoscalar X boson, and we only touch this anomaly. The mass is about 16 MeV. So my next slide is the new results, which corresponds to the resonance annihilation channel using the secondary positron, which presents in the electromagnetic shower in the target, and that electromagnetic shower is induced by the initial electron beam. So the resonant process, in this case, we have improvement on the coupling epsilon up to the factor 10 in the resonant region. We also suppose that A prime, dark photon, decays rapidly into fermions and scalars. So the left one, the left plot corresponds to the alpha D fine structure coupling equals to 0.5 or 0.1, and the right one corresponds to the 0.5. So our next goal is to probe the resonance annihilation with positron beam. This plot corresponds to the electron beam, and the plan to perform to improve the limits with the electron beam of an Na64. So my next slide dedicated to the Na64 mu experiment, which is approved by the SPS, and the pilot muon beam run will be in November of this year. So the left side, on the left plot, we can see the expected limit for the mealy charged particles for the Na64E experiment and Na64 mu experiment. So we can see that the Na64 mu experiment is more sensitive to the mealy charged particles. Due to that, the effective interaction of the muon in ecal is larger than the effective interaction of the electron and ecal, so that we gain the more events which is stated with Z prime with mealy charged production in the setup. So our final goal is to probe G-2 muon anomaly within L mu minus L tau anomaly-free gauge extension. We also calculated cross-section without relying on equivalent photon approximation, which is widely used in this setup. So the next slide is combined limits of Na64E and Na64 mu in terms of coupling, which is stated with dark matter abundance. So this is my final slide, and I come to the conclusion. So the dark sector physics is a very interesting framework to explain dark matter. And the Na64 experiment is an ideal experiment to probing benchmark scalars, major random pseudo-direct thermal dark matter models. There is a prospect before LS3, new area at H4 and setup grade to run at high intensity. The main goal is to explore light dark matter parameter space with about 5 times 10 to the 12 Henderson Pentakit. So, and start search to Z prime weakly coupled to the muons at Na64 mu to probe G-2 anomaly. So we also want to increase the sensitivity to probe dark photon decaying to E plus or minus, which corresponds to the visible mode setup of Na64, and cover the remaining parameter space of atomic anomaly. We developed the package DMG4, newly developed. So the exploration of light dark matter models with an Na64 just begun, and full physics potential should be explored in the coming years. Thank you for your attention.
Okay, thank you very much, Dmitry, for this clear talk. In the interest of time, I think we have the opportunity for maybe one urgent question or comment from someone. So if there's anything, a burning question somebody has maybe about this exciting work from Na64. I don't see any hands going up, so maybe we could go without any questions and say thank you very much, Dmitry. This was very clear and very exciting work going forward. Thank you.
Thank you.
And we'll move on with the next presentation. And I believe this is Professor Reinhard Schweinhorst from Michigan State University. Reinhard, are you there? I don't see his name in the list. So I'm a little concerned. I assume if he's not there, we move on to the next speaker. Would that be correct, Alexander?
Yeah, I think yes. Yeah.
Okay, we'll do that. Okay, so that's Fabio Carrillo from Valencia.
Hey, can you hear me?
Yes, I can hear you very well.
Shall I share the slides?
Please do.
Give me a second.
Fabio will be presenting highlights of top quark measurements with the Atlas experiment. Please, Fabio.
Okay, I can also enable the camera so you can see me. Okay. Okay, so yeah, that's a small summary of the highlights of top quark measurements with the Atlas experiment. So yeah, just some words of introduction. So the measurement of processes involving top quarks are very important, not only to check the predictions of the standard model, but also to provide sensitivity to new physics beyond the standard model. So in the last few years, the Atlas experiment managed to measure a lot of these processes with a high level of precision. Not only top quark properties, but also processes including top quarks, which were considered as rare in the past, but which are not so rare anymore nowadays. So I will present one of the most recent studies and one of the most relevant studies released by the Atlas collaboration in the last few months. So namely, this is the measurement of the TDZ process, the measurement of the 4 top cross-section, the measurement of the TD bar events with a high PT, and the polarization measurement of single top quark. So we'll talk about this analysis in the following slides more in detail. Okay, so coming to the first analysis, the inclusive and differential TDZ cross-section measurement. So yeah, some words of introduction, why is this important and what we're talking about if we talk about TDZ. So we talk about production of top quark pairs in association with a Z boson. That's a rare process in the standard model. It's around 1,000 times smaller than TD bar only. But there were already inclusive cross-section measurements performed by Atlas in 2019, but without using the full run 2 data set. And now the idea of the current analysis is to measure this process also differentially, since we have enough statistics with using the full round 2 data set. It's interesting because it provides access to the top Z coupling, which can be interesting in the context of EFT interpretations, but it's also important background for many standard model searches and measurement. And also theory predictions exist already at high level of precision, next to leading order plus NNLL precision, inclusively and differentially. And one of the features of this process is that, as you can see in those Feynman diagrams, it can have leptonic and hadronic decay modes, not only of the Z boson, but also of the TD bar system. So it can cover different lepton multiplicity in the final states. And typically this analysis focuses on the multi-lepton signature, so 3 lepton and 4 lepton, since they provide the highest sensitivity. Okay, so the results of the inclusive measurement. So what's done here is to apply a simultaneous maximum likelihood function in the 3 and 4 lepton channels. There are also control regions for the most relevant backgrounds, namely WZ and ZZ. And the signal strength parameter is obtained. So it's the cross-section measured in data divided by the cross-section expected by the standard model. So the fit is performed in the 3 lepton, 4 lepton channel separately, but also in the combined 3 and 4 lepton channel, as you can see in this table here. And we get consistent results. All of the results imply around 20% upward fluctuation with respect to what's expected from the standard model. And for the inclusive cross-section, then the combination, so the combined signal strength is used to translate this into an inclusive cross-section, which assumes a non-shell decay of the Z boson. And although we have this 20% tension, it's still compatible within 1 sigma within the standard model, but also with the latest CMS measurement in the same fiducial phase space. Okay, so the interesting part of this analysis is, of course, the differential measurement on slide 6. So this is performed for several observables probing the kinematics of the TDZ system. You can see a table of these observables here. Absolute and normalized differential measurements are performed. The normalized just happen in order to reduce some systematics, for example, cross-section systematics, which affect only the normalization. And then the whole thing is unfolded to particle and parton level using the iterative Bayesian unfolding technique. And also the compatibility between the measures in data and the theoretical predictions from different generators is done by computing chi-square and p-values for differential distribution. Most of these p-values are in a reasonable scale. Some of them are smaller. So the largest tensions we see for some plots I put here, for example, the pt of the Z boson. You can see, there are some small differences in the 4th bin and 6th bin, which drive the low p-value. But also, for example, in the plot on the middle, you can see the angular separation between the Z and the TD bar system. There's a small, deviation in the large angular separation. And also, for example, you can see the jet multiplicity in the 4 lepton channel. But this has a rather reasonable agreement. Okay, so coming to the next analysis, which is the 4 top cross-section measurement. Some introduction about this. It's a very, very small cross-section. It's one of the smallest cross-section we ever measured in Atlas. You can see this, for example, in this cross-section summary table here. The T4 top is the last entry. And if you compare it, for example, to TDZ, that's a logarithmic scale. So it's several orders of magnitude smaller than even TDZ. However, it's very interesting because it provides access to very interesting CP properties, for example, the Higgs-Toplicawa coupling, but it's also sensitive to BSM scenarios and EFT operators, for example, operators modifying the 4 fermion coupling. And similar to TDZ, it can also give rise to various final states, since all of the tops can decay either leptonically or hadronically. So we have a lot of different lepton multiplicities in the final state and also different jet and B-jet multiplicities. There was already an earlier published result based on multi-lepton signatures, so 2 lepton same sign and 3 lepton. And recently there was also a measurement of the 1 lepton or 2 lepton opposite sign final state, which contains also a combination with the previously derived multi-lepton result. And of course, as it's the case for other analysis, if you go to higher lepton multiplicities, you have higher purities of your signal, but lower branching ratios. But then if you go to lower lepton multiplicities, you have higher branching ratios, but of course you suffer from more background contamination. Okay, just to give you a small overview on the analysis, so 2 lepton same sign and 3 lepton analysis is selecting these event topologies, and then it's training a Boolean decision tree to separate the 4 top process from the backgrounds. You can see it on the plot on the top. There are control regions for TDW, which is one of the most dominant backgrounds, and also reducible background sources like fakes coming from heavy flavor decays or photon conversions. And then a binned maximum likelihood fit to the BDT score is applied to separate, to derive the signal strength for the 4 top process. In the one lepton and two lepton opposite analysis, there are different regions for one lepton and two lepton defined by the jet and B-jet multiplicity. There are 12 regions in one lepton, 9 regions in two lepton opposite sign. And most of the signal regions are defined by having a very high B-jet or a very high jet multiplicity. So all of the signal regions have at least 3 B-techs. And then also basically the same thing is done. There's a bint likelihood fit to extract the signal strength on the BDT score in the signal region and the HT in the control region. You can see some examples here, the one lepton channel on the left, or the two lepton channel, two lepton opposite sign on the right. And in our case, it's the BDT score plotted here. Okay, so the results. So then, of course, these results are derived separately. They're also combined at the end, and the combination is used for the final statement about the inclusive cross-section. You can see it here. It's 24 femtobarn. Since the most relevant systematics of these two analyses are very different, it's not a big deal to combine them. There are not so many correlations between the systematics. But of course, the higher precision comes from the two lepton opposites, two lepton, same sign, and three lepton, since this is a more precise result. I'm not sure if you can see my mouse, but you can see basically in this cross-section combined tape, you can see since the two lepton, same sign, and three lepton result is way more precise than the single lepton result, then of course this derives the combination. And something which is also worth to mention is that both results imply a cross-section 2 times higher than the standard model expectation, so a signal strength around 2. That's of course a bit more than you expect, but it's still within 2 standard deviations. It's inside the standard model expectation, and it's also compatible with the results measured by CMS. Okay, coming to the third analysis, the differential TD cross-section with high PT. So some words of introduction about this analysis. So this is targeting semi-leptonic TD bar events. So we select one lepton, and the other top is allowed to decay hadronically, but it needs to have a high PT. So that's why it's called boosted analysis, so boosted or high PT analysis. This is interesting because some EFT operators and some BMSM scenarios expect high deviations from the standard model, especially for large top PT or high invariant masses of the TD bar system. And the TD bar system is fully reconstructed either from the final state particle, but also including, for example, large R jets, where all of the decay products of the top are reclassed into one jet, as it's shown in the small picture here. The inclusive and differential measurements have been already measured by Atlas in 2019, but without the full run 2 data and without any EFT interpretations. And the background process of this analysis, so everything which is non-TD bar, comes mainly from TW, which is estimated by Monte Carlo, and multi-jet, so zero lepton, which is estimated via a data-driven matrix method. So something interesting about this analysis is that it suffers usually from very large uncertainties of the jet energy scale. And this is reduced a little bit by deriving custom jet energy scale factors to be applied on top of the standard Atlas calibration. And this is done by doing a matching between the top quark mass measured in data and Monte Carlo in some control region. And this is done for different GSF values. You can see, for example plot here. So this GSF custom calibration is varied. And then the best data Monte Carlo agreement is found in the control region. And then this value is derived, also an uncertainty, and which is applied on top of the standard calibration. And this helps a bit to reduce the jet energy scale factor, the jet energy scale uncertainty. Okay, about the results, also differential measurements are performed. Similar to this set, it's unfolded to particle level with the iterative Bayesian unfolding technique. And also this is done for several observables, probing the kinematics of the top quark, but also which are sensitive to, for example, radiation or parton shower effect. So the full list you can see in this table here, and you can see some results, for example, the PT of the hadronic top, the invariant mass of the TD bar system in the middle, but also the number of jets on the right-hand side. And then also similar to the DT set, the compatibility is checked based on chi-square and p-values, not only for the nominal prediction, but also, for example, varying the parton shower algorithm and varying the FSR and IFR setups of the Monte Carlo generators. And the sum of the bins is usually then the inclusive cross-section measurement. So on slide 14, just a bit more about the results. So you can see on the right-hand side, the result of the inclusive cross-section measurement for different setups of the Monte Carlo generator. And for example, something interesting is that if additional reweighting of the Monte Carlo generators based on next to leading order at parton level is applied, the results significantly improved. You can see this in this non-filled dots here. The agreement between the measurement and the expectation from the standard model is significantly better if this correction to the Monte Carlo generator is applied. But then this analysis is also used to set limits on Wilson coefficients, modifying either the top to light quark coupling or the top to gluon coupling, as shown on the Feynman diagrams here. And these limits are derived either one-dimensionally, as is shown on this table, or two-dimensionally, as it's shown on this plot, and it's also in agreement with the standard model. Of course, the standard model expectation is 0, 0, and you can see the measurement is quite in agreement with the standard model. And for one of these operators, this operator modifying the top light quark coupling, it's the most stringent limit. It's even better than the limits derived from this global SMAFT fit. Okay, so the fourth analysis is the single top polarization measurement. That's a bit different. This targets the polarization of a single top quarks. That's a cut-based analysis. And in principle, the idea is that you measure the single top polarization for single top quark and anti-quark production via exchange of a virtual W boson in the T channel. You can see some Feynman diagrams, some examples here. And the idea of this analysis is you have always a top in the final state, a top and a light quark. The light quark is called a spectator quark. And the spin of the spectator quark should be due to the vector axial vector coupling of the TWB vertex always be aligned in the flight direction of the spectator quark, as it's shown on this plot on the left-hand side. So this analysis is performed by selecting one lepton and jet events. And the top polarization vectors are accessible via the angular variables of the leptons in the top quark rest frame. So if you transform the whole system to the top quark rest frame, you can derive these three angular variables, this cosine theta x, y, and z. How this is explained, I put a reference here. So if you follow this link, you can find more details how exactly this is done. It's done via a likelihood maximization procedure. So in principle, you take the angular variables as input, and then you determine the polarization vector for the top quarks and the anti-quarks via likelihood minimization after, of course, the selection of the signal region. But of course, also the angular variables, there are also differential measurement performed at particle level for the angular variables themselves. You can see the measurements here for this cosine x, y, and z. And you can see that it's also done for data, but also for the standard model prediction for different Monte Carlo generators. And you can see all of them are quite good in agreement. Differences between the Monte Carlo generators are typically covered by the uncertainty of the measurement. And so these differential measurements, they are the first part of the analysis, but of course, the more interesting part is then really the measurement of the polarization of the top quark. You can see this here on the plot on the top. So basically, what you see on this plot is this black circle implies the physically allowed values. The red star is the prediction from our nominal Monte Carlo generators. And then the measurement obtained from data. Of course, from data we obtain only limits. So 68% and 95%, 68% with statistical only in green, and 68% with statistics and systematics in yellow. So these limits are obtained from data, and you can see the limits obtained from data are in agreement with the standard model expectation and also move into the physically allowed range. So the naive expectation is, of course, -1, 0 for the anti-quark and 1, 0 for the quark. But of course, if you consider next to leading order effects, it's not exactly like this. But you can see the standard model expectation and the measurement in data and the physically allowed range are kind of meet at the same point. So of course, this analysis can be also used to obtain limits for Wilson coefficients, modifying the TW coupling. So there are two Wilson coefficients. The best fit values of the Wilson coefficient are then used to derive the limits. You can see the one-dimensional limits in this table here, and the two-dimensional limits in this plot on the right-hand side. And you can see, although that's basically at the edge of the 68% confident limit, you can see the data, the measurement, the limits obtained in data are quite in agreement with the standard model. Again, the standard model value is 0, 0 for these operators. And you can see that's still in agreement within the 68 confidence interval. So far, these are the most stringent limits for this TW and ITW derived simultaneously. There are more stringent limits for these operators where they were derived separately, but the most simultaneous limits for these operators are obtained from this analysis. Okay, so slide 19 is already my summary. So I presented 4 of the most recent ATLAS measurements on top quark related processes. Most of these results are really new, so they have been released in the last 2 or 3 months. The TDZ analysis and the 4 top cross-section measurement are already on arXiv. The TDZ was published also 2 days ago. And for this differential measurement of the TD bar system for high PT and top polarization analysis, these are only exist as conf notes yet, but I also hope to have papers very soon about this. Of course, there are more interesting results about top physics in Atlas, which can be found on the top public results webpage on the Atlas collaboration. I presented only the most recent and most relevant measurements in this talk. But if you're interested, you can have a look at the Atlas top webpage and get informed about more analysis, which are happening in the collaboration. Okay, that's everything. Thanks a lot for your attention.
Thank you very much, Fabio, for this very detailed, comprehensive overview of top physics in Atlas. We do have time for some questions. If anyone has something, just raise your hand. Is there a question? I see someone's unmuted. Hongguo, so no.
Oh, sorry.
No, no problem. I think everything was too clear there, Fabio, which is never a bad thing. But yeah, thanks very much for showcasing these nice results. Again, thank you.
Okay, thanks.
So I think we are moving on to you next, Hongbo, if that's okay. Don't believe our scheduled previous speaker has arrived yet. So we can move on with your presentation. Thank you very much. Hongbo Liao from IHEP Beijing. Yes, we can see your slides. And please feel free, the floor is yours.
Okay. I represent some recent semester results on top quark physics. Top quark has several features that make it very interesting, such for example, it is a heaviest particle. It is decayed before hydrogenization with a large coupling to the Higgs boson. Now HC is a top factor below it. We have overall 200 million top quark pairs in HC run 2. And this could allow us to process measurement of top pair and single top production and do some observation of rare process involved top. Use the top quark as a tool to study the standard model. As the theta cross section, it can provide a strength test of our level of understanding of the QCD and allow us to extract several standard model parameters such as top mass, allow us to improve the discriminant of the PDF. Same as recently we have one such a differential and a double differential such as theta cross sections in the lepton plus jets. This is the hypothesis.
Hello? Alexander, could you please mute? I think we can hear you in the background.
Yeah, thank you. Okay, I can continue. Okay, this is one hypothesis measurement of differential and double differential cross sections, and it's the first time for the first spectrum. This combines resolved and boost theta topologies. This is the score test of the measurement. Most of the productions are in very good agreement with our measurement, except such as several such as two double differentials show a little bit larger disagreement. And at the particle levels, there are several observable are difficult to describe by less busy orders. And also the inclusive cross-section has been measurement. This is the most precise measurement in the lepton plus jet channels. And this measurement dominated by the JS and the BTAGIM. Recently, there's another interesting measurement is about such TDCC, TDBB, and TTJJ productions. Here, JJ means such as light quark. This is a test standard of the production at the less leading order. And this kind of process is a reducible background to the very important TT Higgs and TT Higgs to BB. Fourth measurement is the TDBB and the TTJ measurement. It is extracted simultaneously from the 2D discriminant. The second measurement is a fourth measurement of the TDCC productions. Simultaneously extract such as cross-section of TTBB, TDCC, and TTLL. Here, LL means light quark and or gluon. Use the one template feed procedures. This kind of measurement, position dominated by such as Monte Carlo modeling, JS, and C-targeting. This plot shows such as what we imagined with the top failure state. We can see we reached to the very rare process with high precise. Those kind of precise measurement on those kind of rare process, such as we can provide such a strength test also for the electroweak process. And we can also achieve several coupling such as T gamma, TWTH, which is sensitive to the new physical effect. First measurement is TW production lepton plus jet. This is categorized based on jet multiplicity and one beta jet. And one BDT is trained per lepton flavors into single regions. Similarly, mathematical food fit performed in all categories use the BDT discriminators. And this measurement dominant by background estimation, challenge scale, and modeling. The measurement cross-section is well agreement with the standard model productions. And this is fourth observation of TW production in the lepton plus jet channels with 7.4 sigma. Another process is TTQ. We applied such an inclusive and differential measurement with the 4-run tool. This is the three, we asked for the 3 leptons with improved lepton MVA and constrain such long prompt background, and then use the multi-class neural network or BDT. This analysis includes a lot of interesting results, such as inclusive TTQ cross-sections. This new measurement improved 30% compared with the earlier measurements. And this is the first time to measure such partial TTQ cross-sections and ratio. At the same time, extract spin correlations, we can see the results is agreement with the standard model prediction. As the differential TTQ cross-sections also measured at this work, in general, observed good agreement between measurement and the production. Boson associated TT bar is another rare top productions, such as same as measured such as the TTJ productions, target 3 or 4 isolated lepton channels with J to the lepton pair. Inclusive cross-section already system limit, which is dominated by the singular background Monte modeling. And also the differential cross-sections are measured first time. Another one is the TDCAM production. This is measured in the lepton plus jet channels with 4-run 2 data. And the precise is still limited by such a Monte Carlo modeling. Also, the differential cross-sections measured in several kinematic observables. This is show 1, and we can see it is good agreement with standard model production. Now, we know LGC is possible to reach the high positions for the properties of the top measurement. For example, top mass, and such as coupling, and such as another top quark forward backward asymmetry. CMS has one new result about the measurement of the top quark coupling in TDBAR productions. This explored a large effect that the radiation of the richer Higgs boson has on TDBAR differential distributions. The TDBAR productions for different values of the coupling obtained at the event-based multiplicity correlation used factor. The comparison with additional approach is taken as uncertainty. This analysis use the data with ferrostate dilepton channels and at least 2 BGS. Variables were used based on the partial system reconstruction, such as the system of dilepton and the BGS, and the difference of the eta of the B and the lepton requires correction match to the B quark and the lepton. This measurement given us such as the coupling is 1.16, which is comparable with the previous result in the lepton plus jets ferrostate. Net leading order inference term in TD-bar productions from the QQ initial state creates a forward-backward system. Okay. CMS used the variable sensitive to the difference between the QQ, Q gamma, and gamma gamma initial state to build template and separate the QQ. And then we can extract such as forward-backward asymmetry, animals such as thermal electricity and thermal electromagnetic dipole moment. This analysis uses the event collected in the lepton jet channels, used both resolved and both topology. Applies the profound likelihood to the 3D template to extract these three, and we can see the measurement is values is here. All the measurement consistent with the standard model and also consistent with previous CMS results. And recently, there's combination results about the W polarization between Atlas and CMS. This is combined is applied on the such as 4 measurement based on the run 1 data. This combination we can see improved a lot, at least 20% with the most precise measurement, Singapore measurement. And this kind of measurement used to set a limit on the animal coupling in the TWB vectors. Top mass is another very important parameters. We most such as methods such as top mass from the TT bar events. Here we reached such as high precision top mass measurement in single top events. We use the BDT discriminators and do the optimization. And the QCD background is data come from data driven and also extract from the data. Similarly, maximum likelihood fit used by the such log top mass distribution in muon and electron ferrostate, and this fit already validated in the control region. From this kind of single top event measurement, we can reach such a sub-G with precise of the top mass, and also we measure such as the measurement of from the quark and anti-quark, and also the mass ratio between quark and anti-quark and the difference. This measurement is still sub-GeV position, but the position is limited by such limited by the JS and the modeling. We know TOP could be one good tool to search the new physics. Many BSM models are expected to involve top quark, possible performance such as direct search for new resonance and such as for the FCNC. And we can use the well position measurement of the top to set limit on new operators in such as in one EFT framework. FCNC allows for transfer between quarks of different flavor by the same electric charge, and it processes are highly separated in the standard model due to the geometry. This needs small contribution appear at the 1 loop levels. We know many extensive of the standard model productions present such as FCNC and give reads to detectable of each. So we see if any evidence of FCNC were the extent of the new physics. Recently, CMS performed one search for efficiency by THQ interaction. First one is ask Higgs to decay to gamma gamma. This search can be includes production and decay. Singular regions include such leptonic top decay and hadronic top decay. The analysis strategy used a lot of such as BDT and the categories defined by BDT's core. This analysis, the dominant uncertainty is beta-gain and photon edification. And the data comparable with absence of the FCNC singular. So we can see the limit has been set with the ratio of the top to the Higgs mu and the top to the Higgs C. Another FCNC THQ interaction applied by the Higgs BB is also include such production and decay. Singular region asked at least asked one lepton, at least 3 Gs, and at least 2 beta act. This analysis, deep learning work is used to associate the reconstruct object, and BDT are used to separate such a singular from the background events, and all the BGS categories are combined. Finally, low significant excess with respect to the standard model background. This result is significantly improved with respect to the earlier run-to search. Let's go turn to the such as EFT interpretation. First new results is come from top associated with leptons. This is considered at the same time yet from several singulars such as TT Higgs, TTJ, TTW, TTQ, THQ, and divided the events with such a number of jets, BJets, lepton flavors, and charge. And finally, obtained such as 1D and 2D profound and divided limit for likelihood fit. This analysis is dominated by the systematic uncertainty about serial modeling JS and lepton side, such as the edification and isolation. And we can see such as the good agreement of the all worsening coefficient with the standard model protection. More new results is come from at least such as 3 leptons fellow state with 4 run-to side. This made process is TTQ and TWJ and TTJ. Here asks the top and J lepton decay. This analysis used the extensive MVA. First is used such as deep learning work to determine the standard model process between such as TTQ, TTJ, and the backgrounds. Second one is separate such as standard model events and BSM events. Singular extraction with 1D, 2D, and 5D likelihood fit. Systematic uncertainty dominated by the serial and lepton ID and isolation. This is a little bit better limit than earlier results from the TTJ cross-section measurement. In generous agreement with standard model productions in 2 sigma. The more recently, such as EFT search is applied in the TT gamma final state, and this is also one for run-to analysis, asked for 1 lepton bind in lepton flavors. And due to time, I didn't introduce too much detail. Currently, this is the best limit. Same as also searched for the such as charged lepton flavor validation. In the standard model, lepton flavor is conserved in all interactions. Many new physics promoted induce sizable charge flavor, charge lepton flavor validation. If the new physics response for it, HC can direct probably. The standard model algorithm can be extended by dimension C operator like here. This search is applied in the forerun to data with emu fed state and include productions and decay. A singular includes 3 kinds, is about vector, scalar, and tensor. BDT is used to determine the singular from background events. Finally, the result shows state consistent with the standard model expectation, and finally set the limit for it. The failure one search with top is about simulation. A simulation in standard model is insufficient to describe the matter and antimatter asymmetry of the universe. In the standard model, simulation in the production and the decay of the top quark raised is predicted to be worth more. Simple CP observer can be described as here. Charming electron diploid moment of the top quark in top pair productions induced such CP relations. This search applied in the lepton failure state with forerun to data. There's 4 observers, and the top quark and anti-quark candidates are reconstructed with the used one category method. The background and contribution in the single region is determined from the feed to the mass distributions. Finally, there is low significant evidence of the CP relation each observable. The result is still consistent with standard model production. Okay, let's go to a short summary. HC is the top factor, and CMS is exploiting the large samples collect maximally. Here we reduce the uncertainty on inclusive measurement, performed such a differential measurement, searched for very rare process, measured the top properties and coupling with new techniques, and set constraint to the existence of new physics, for example, FCNC, EFT, charge lepton flavor relation, CP relation. Okay, here, just several exciting new measurements at the past half year have been present, but stay tuned since more results are coming. Okay, thanks for your attention. If you would like to know more detail of the results, here is the reference, mainly is CMS, and also you can look at the Atlas and HC Topo group. Okay, thanks again.
Thank you so much for this very detailed and clear talk. We have time for some questions. If anyone has something, please raise your hand. Yes, Fabio, so your hand is raised.
So just one small question about, I think it was slide 8 or something, the TCQ measurement. So you state there on inclusive cross-section. Is this inclusive? Do you require any on-shell requirements on the set boson for this? Because I mean, for the TD set, which you present afterwards, I know there's an on-shell requirement for the set boson invariant mass to be between 70 and 100, I think. Is the same the case for the T set?
Okay, these are good questions. For this kind of detail, I need to check. Okay, thank you. I'm sorry.
Okay, thanks.
I think the cutoff is not 70 at the low mass, but I think it's 10 or 20 GeV. So it's not just an on-shell Z.
Okay, so it's basically C2, it's basically TLL, what you mentioned.
Exactly. We had several discussions on that in the LHC top working group, and I think that was the agreement, is to do exactly what you just said. TQLL.
Yeah. I mean, I remember this discussion because we had a similar discussion when we measured the TD set, because initially we stated in the conf note basically a TTLL measurement with just a very low cut on the invariant mass of the leptons. But in order to be in agreement with the CMS measurement, and also for some internal reasons, we decided then to constrain the diffusional measurement to the invariant mass between 70 and 100 or 110. I just was wondering whether there's a common policy how to state those measurements, these institutional measurements for a process, including Z bosons in CMS, and whether you always require something like an on-shell requirement. But if that's not the case for TZ, yeah, it's good to know.
Okay, thank you.
Yeah, thank you for this question and the discussion. That's really useful feedback, actually. Are there any further questions to Hongbo? If not, I think there's a lot of information that was advertised at the end from CMS there for us to go and read. So thank you for that. And we can move on to the next presentation. So with a slight reordering of the agenda, I think we can have Reinhard Schweinhorst from Michigan State University presenting to us single top quark measurements at the Tevatron and the LHC. Thanks, Reinhard.
Yeah, thank you very much for reshuffling the schedule. In fact, I had two confusions. My first confusion, I thought, was that the agenda was in Moscow time, not CERN time. And then my second confusion that even though it was, I then figured it out, I still missed it. So thank you very much. Oh, I have to go to the beginning, to shuffling the schedule and giving me a chance to still present, even though I missed the beginning of my talk. So yeah, it's actually very nice that I'm now presenting after Fabio and after Hongbo's CMS talk, because my goal is sort of to put both of those into context also with the Tevatron. So I will talk about not all of top quark physics, just single top measurements at both the Tevatron and the LHC. And in the comment that you just asked about TQZ, I actually have a slide on TQZ as well. That was about something that's being negotiated in the LHC top working group. And so this is also an advertisement for the LHC top working group. Anyway, let me start from the beginning. Here are the Feynman diagrams for the basic modes of single top quark production at both at the Tevatron and at the LHC. We have the T-channel mode, the associated TW mode. That's what we just heard about. And then we have the S-channel mode that I'll mention as well. At the Tevatron, it's mostly T-channel with a little bit of S-channel, and then we can't measure the associated TW production. At the LHC, all three have a relatively large cross-section, but now S-channel is so small that it's really, really challenging. And I'll say a little more, but you actually heard about this already, that the top quark in general, but single top also, is really a window to all kinds of new physics. And it's shown up in many, many talks, also at this conference, just not with the top quark as the designated particle of interest, but as a vehicle to study much other new physics. Okay, so now let me go to the two colliders and start with the Tevatron collider. The Tevatron is a proton-antiproton collider that stopped running in 2011. It ran at 1.96 TeV in this run too, and recorded roughly 10 inverse femtobarns per experiment. So that's where we're putting ourselves, 10 inverse femtobarns, but proton-antiproton. And that's why certain processes are much nicer at the Tevatron than the LHC. And so one of the things you see here, these are the two dominant production modes at the LHC, at the Tevatron. At the left is the S-channel, and I'm showing a theory curve of just what the momenta of the particles look like. And in fact, this is nice because you have tens of GeV in momenta, which is also exactly what we see at the LHC. So the final states are actually similar. Because we have proton-antiproton, we know where the quark versus the antiquark comes from. So we actually can figure out the direction. And that's what you see here in the pseudo-rapidity distribution of the light quark. And this light quark is really the key that will come back later when we talk about the anomalous couplings as well. But here in particular, you see that it's very much following the direction of the proton. And at the LHC, the plot looks the same, except everything is mirrored at 0. So it has a peak both in the forward and in the backwards direction. So at the Tevatron, we had the single top discovery. So this was the first time anywhere else, anywhere in the world that single top was observed. And that was done with 2 and 3 inverse femtobarns. And you can see here, this is really, it's combinations of multivariate analyses to really get to this level of precision, just squeezing as much information out of the limited number of events as possible. We get much nicer when we get to not just the end of run 2, but then combining the two experiments. So this is a plot that I'm very happy to always show because it really has several multivariate discriminants in several channels with two different final states, all summarized in a single plot that includes both experiments and hundreds and thousands of underlying bins. So here, maybe you stare at this for a while. On the left-hand side, we have the T channel, and on the right-hand side, we have the S channel. And the peak in the middle is where the background is dominated. And so this background is mainly W plus jets, TT bar, and multi-jet production. And then on the left, you can clearly see where the T channel dominates, except in the very highest bins where we have statistical uncertainties. And then on the right, you can see the S channel has lower statistical precision and larger backgrounds, but it's still clearly there. And then for the S channel, we actually had a follow-up separate combination because the only way to get to 5 sigma for the S channel was through the combination of CDF and D0, and that's what you see here. So this is really, again, combinations of multivariate discriminants to really get to the discovery level. Okay, and one of the nice things that I claim we did at the Tevatron was to make these two-dimensional distributions, which I'll show you more of later on as well. So here we have S channel on the horizontal axis and T channel on the vertical axis. And you can see not just the measurement, which is the black dot, and the 1 and 2 and 3 sigma uncertainties on the measurement, but now you see also the standard model, which is the red cross, and all these new physics models. So if we have flavor changing neutral currents, in this case, flavor changing neutral currents of the gluon, then that would enhance the T channel, but not so much the S channel. Whereas if we had any type of resonance, then resonances would appear along the S channel direction, which is this a triangle here, for example, for a top pion, which is just a resonance that decays to T and B, or it would modify the coupling itself, where then you get these other, the two ones that actually reduce the S channel cross section, or one of them reduces it anyway. Okay, so that was the Tevatron. Now let me go to the LHC, where I want to show you the data collected every year, because remember I said 10. 10 is the level that the Tevatron was at. So we have much, much, much more data, but it's a proton-proton collider. So we don't have this very nice asymmetry in the direction of the beams. And one of the things that we put together for the LHC is this same idea. So this is a paper where we looked at the 8 TeV measurements by Atlas and CMS, and we put them together in this same idea, the same two-dimensional picture, but because we have T channel, TW, and S channel, we actually had to have 3 distributions instead of just 1, and that's what you have here. So on the vertical axis at the top is T channel, and on the vertical axis at the bottom is TW. On the horizontal axis on the left is TW, and on the horizontal axis on the right is S channel. And here you can very nicely see in the bands, that's the measurements, either Atlas or CMS, to really keep these as independent as possible. And then we're comparing to the predictions. And then the same idea, we have the standard model as the star, and then we have these new physics models where you can see how they affect S channel, T channel, and TW differently. And here in particular for the TW, that's not obvious how something like a color triplet, for example, that is a resonance, the way that it would affect TW. And here you can see that it has very little change. But we would need to get a B prime, which is a copy of the standard model B quark just at a higher mass, and that directly affects the TW process. Okay. Very nice. So that's something that's a plot that I was responsible for. Now we can look at a plot that really summarizes all of the LHC single top measurements. And now we have 3 different center of mass energies: 7 TeV, 8 TeV, 13 TeV, and then we have the horizontally at the top we have the T channel, in the middle we have TW, and in the bottom we have the S channel. And I should note that the result that you just saw on TW in the lepton plus jets channel at 13 TeV is not in here yet. So here we just have the most precise TW measurement from each experiment. And for CMS, that's still the dilepton final state. So that's the CMS TW point here at 13 TeV. But this very nicely shows you everything that we're learning, right? We're very much still in agreement with the theory predictions, even for TW, where there are two theory predictions that are a little far apart. And there's some work that can be done on the theory side, but also we need to reduce the experimental uncertainties. And you can see for the S channel at the LHC, this is a challenge, and this continues to be a challenge. At 13 TeV, this is something that I'm very much looking forward to. Okay, so these are the three channels. And one of the very interesting parts about studying these single top production modes at a Hadron Collider is that they give us direct access to the CKM matrix element VTB. And I'm showing you the T-channel Feynman diagram again here on the left. So it's exactly here. It's an incoming bottom quark, and then the W and the top. And so this, by having it in the production, we don't have to make any assumptions about other constraints in the top decay, branching ratios. We're really directly sensitive to the coupling. And compared to B physics, for example, we don't have to make any assumptions about the absence or presence of new physics. And this was done at the Tevatron. I will just give you the number here. It's within 5% for the absolute value of VTB, which is great, but we can actually do better at the LHC. And so this big plot that I just showed you of all the LHC measurements, here is the summary of all of that. And here, in fact, we have gone through a big combination of the 7 and 8 TeV single top measurements and extracted VTB from all of them. It's really just the 8 TeV T-channel measurements by Atlas and CMS. Those are the ones that dominate in this combination. And you can see that we're at 4% or so for the combination of all channels for VTB, but we're also still very close to a VTB of 1. And in fact, if you look closely, we're actually slightly above 1, and that just tells us that we're letting it float. So we're really looking at the ratio of cross sections here. And so we could have a change in the coupling, for example, which is why this says F, which is the coupling to the left-handed vector coupling, like in the standard model. And so if you put in an assumption here, then we have a limit that's much closer to 1. Okay, so those were the three modes that are the default production modes. I said we have so much data. We have so much data that we can look at production of single top quarks in association with other particles. And the largest one of those is the associated production of the top quark in the T channel, where we just attach a Z boson to one of the lines somewhere, either to a quark line in the initial state or in the final state or to the top quark. That's very interesting. In fact, you've already heard about that. I'll say a little bit more about that TZQ. And then we also have THQ, where it's exactly the same idea, just rather than attaching a Z, we're attaching an H. And you can imagine the cross-section for this process goes down accordingly. And this is what I'm showing you on the left here. So if you look at the 13 TeV line, which is roughly where I wrote this, we have 500 femtobarns for TZ, and then 300 femtobarns or so for anti-top and Z. So that should be doable. But then we have around 50 to 80 femtobarns for the cross-section. So that's going to be much more challenging for TH. And so TH you don't see in these talks because that's usually included in the much larger TTH measurements as one additional signal channel. Okay, so let me highlight the Atlas TZ measurement, where we go back to just having a discriminant here. It's just a single discriminant, very well, simple, straightforward. But in particular, the background is very much under control. And that's because we're looking for a Z boson decaying to 2 leptons, as you heard in the previous talk as well. That means you have 3 leptons in the final state, which there's not many things that can produce background to that signature. And so we get a reasonable background, and then we have a very nice signal region over here already with 30, 40 signal events clearly separated from the background. And so already with the full run-to data, we can measure this cross-section to 15% or so. So this is very nice. And this was published last year. And then as you actually saw in the previous talk, CMS has done the same thing now, I think the third time over, and now has not just the cross-section measurement, but also the two ratios. So I just showed you that top and Z is about a factor of 2 higher than anti-top and Z. And you can see it's not a factor of 2, it's more like, 2/3 or so. And then also looking at the ratio, right? So it's 1.23, that's the dot that you see here. And the measurement is actually close to the, well, sorry, I'm not saying that correctly. So for the inclusive cross-section, the CMS measurement is slightly below the standard model expectation. That's what you see here, whereas the Atlas measurement is slightly above the standard model expectation. And then for the ratio, this ratio for top is slightly above, for anti-top it's slightly below. So then if you take the double ratio, that's when you end up here, where here you see this, that it's a factor of 1.4 or so, which compared to this standard model prediction is quite a bit above the standard model prediction. Okay, now I said it correctly. And the interesting part here is to figure out what's going on there. It would be nice to take the next step. And in this analysis, the next step was already taken because it includes differential measurements, where here you see the differential measurements of the Z, of the PT of the Z boson. And this is the first time that's been done. So the uncertainties are still large, but it's very good to look at this because we can already start to differentiate models and try to understand some of the features. And then let me talk about the polarization, because this is something we did at the Tevatron, and this is also something you'll hear about, not just in the top talks, but in general about effective field theory and interpretations in effective field theory. Here, we specifically talk about the top quark sector. You'll also hear about that in electroweak and Higgs sectors. In T-channel single top, we have a very nice situation where I again show the Feynman diagram for T-channel single top on the left, but now I include the top quark decay as well. And so now if you stare at this long enough, you can actually see how we're analyzing the spin direction. So we have the top quark in the middle, then we have a W boson attached to it on the right, and we have a W boson attached to it on the left. And then we're looking at the lepton coming from the W on the right, and we're looking at the light quark in the final state coming from the W boson on the left. And it's really this symmetry that you have to look at. So we're looking at the correlation between the light quark there and the lepton on the other side. And that's how we'll measure top quark polarization and the correlation between production and decay in single top T-channel. I'm showing you here how we do this in practice. So we have in the top quark rest frame, right? So then we really put the top in the middle. Then we have these different directions. We have the lepton from the W, from the top decay gives us a direction, and the light quark gives us a direction. And now that gives us the two directions, and that defines the a coordinate system, and we can measure the different angles. And the direction of the W boson in particular is the Z-axis, and we can measure angles with respect to that. And I will not go through all of the details, but I do want to show this because the Atlas 8TV analysis had this very nicely, not yet in the EFT language with Wilson coefficients, but in the anomalous couplings. And here we're looking at the tensor couplings of the right-handed tensor couplings, and those are really directly proportional to the Wilson coefficients CTW. So there we can really make a direct comparison. And here you can look at the 2D plot again. You can see I like 2D plots of the real part of this coupling versus the imaginary part, where we can see very nicely how we improve from the 7 TeV measurement, which is the blue and the orange, to the 8 TeV measurement, which is the green and the yellow. And you can see I like this plot because then I can go to the next page and I can add the Tevatron information. So here we have in this red, I add a D0 measurement, which is a combination of T-channel single top measurements and top pair production. So there we're only looking at the decay. And you can see that's actually not that much larger compared to 8 TeV. Yes, the Tevatron circle is much larger, but compared to 7 TeV, actually we were already we were still competitive. But then let me add one more. So this is now the CMS one that you can see here. that's already getting smaller. And now let me add the result that Fabio showed. So this very latest came out this summer, and that's this one here. So note this is roughly me drawing a circle of where the measurement is, that's the star. And then you can now see the 2 sigma uncertainty band is shrinking quite a bit, right? We're now in this range here, shrinking both in the real and in the imaginary part. And then also in this same way. So what I've done now is I've taken the ATLAS result, which is really a limit on CTW. One of those ATLAS limits is on CTW, and I've translated that into this couplings plane. And we can do the same thing in the other direction as well, translating limits in this coupling plane for the tensor coupling, and then going back to the Wilson coefficients in the EFT interpretation. Okay, so maybe just briefly, because we worry about the future and what can we achieve in the future. So here I have all the different couplings between the top and different particles, where we are in terms of the limit on the coupling and where I think we can go, but then also which mass scale that corresponds to. And what I want to point out is even at the LHC, if we run to the end of the HL LHC, we can be sensitive in the TeV range, even in the 20 TeV range and tens of TeV range for some of these couplings. We're indirectly sensitive to new physics at that scale. And then finally, the last result I want to just flash is the top quark mass measurement, looking at T-channel single top events and then measuring the mass. This is a CMS run 2 measurement with early run 2 data with 36 inverse femtobarns, and already the mass is measured to better than 0.8 GeV, so very, very precisely. And this is going to be an important channel also because it provides some orthogonality, in particular in future combinations where we're dominated by systematic uncertainty. So we need alternative channels that allow us to reduce those through other measurements. Okay, in conclusion, single top continues to be important. It was really important at the Tevatron, where we made many observations and first measurements. Even at the LHC, we're making observations and first measurements, first differential measurements, and so on. And this is all still just going on. TZ is something that we've only been measuring over the last 2 years. We're now already measuring TZ and many other couplings and processes with very, very high precision, and this will continue. So single top is a growth field in that sense, where we have many more channels and will constrain many more EFT parameters. And I haven't mentioned PDFs, but we'll also be looking at PDFs and constraining those. Thank you very much.
Okay, thank you very much, Reinhard, for this very comprehensive overview of single top quark. We have time for some questions. Maybe I have a curiosity with I suppose searches for THQ. Are they more sensitive in single top quark processes as compared to TT bar?
Those are more sensitive in TT bar, right? So you have it's roughly, what is it? The cross section for T channel versus TT bar is a factor of 5, and the same is true in TTH. So, you know, whatever you do in TT bar, if you're getting barely to the 10% uncertainty level, then you're going to be that much less sensitive, right? So by the time TTH is a few percent precision measurement, then single top plus H will also be at the few percent level. But right now, while we're dominated by statistical uncertainties, that's not the case yet.
Okay. Good to know. Any further questions or comments? Curiosities about anything single top related while we have an expert on the line? Doesn't seem to be the case. So thank you again, Reinhard, for this lovely talk.
Thank you again for reminding me and for shifting the schedule around.
I think it's worked out quite well. So we can move on, thank you. And to a different, equally exciting topic now, the physics overview of the BESS-3 experiment.
Oh, can you hear?
I believe we have our speaker here. Yes, I can hear you very well.
Okay, so yeah, let me try to share my screen. Can you see my slide?
Yes, we can see them, and they've just gone full screen, and I can see your transitions. So please take it away.
Okay, then I start. Okay, so first, sorry. So thanks a lot for the opportunity to introduce the BESS3 project, and I would show some highlights of BESS3 results. Yeah, but due to the time limit, I will not go to comprehensive one, but you will see a few parallel talks from BESS3 to give you more details. So you know that different from the previous 3 talks on the high energy level. So the BESS3 project mainly focus on the low energy, but very high statics data. So it's basically to probe the non-perturbative QCD effect, and also to constrain the electroweak parameters, and also even to search for new physics. And as introduced actually in the first session of this conference by Yifang, that the BPC2 actually located in Beijing, and it's the first large-scale scientific facility in China. And so it's this collider actually now is the 2nd generation, and it runs the 2 separate electron and pair positron beams from 1 to 2.45 GeV. So mainly covers the charmonium region from 2 GeV to 4.9 GeV. It already run for almost 10 years. And it's the detector actually locates only one interaction point, and the BESS3 detector locates around here. And it's a generic purpose detector, and very efficient for this energy region study. The collaboration includes around 500 members from 76 institutes from 16 countries, from Europe, from the many Chinese universities, and also Europe, and also some other Asian countries, and also USA. And recently we have one South America member just joined this collaboration. And from 2009 until now, every year we run quite smooth, and we took quite high quality data with roughly around 32 inverse finibar. And we have publication around 350, and with one fourth is around the PRL publication. So it's a very efficient collaboration, I would say. So the physics are according to the beam energy. So it's that covers the energy from 2 to around 5 GeV. So includes the low QCD precision study, and the parameter measurement, including the fractionation function, and also the Hyperon and other baryon form factor studies. And also we have the lead hadron spectroscopy and global search, and also other exotic study, and also new physics search, and tau lepton mass measurement. At a little bit higher energy region, we have the charmonium spectroscopy study, and also including the XYZ particles, and also very high statics on threshold data, D meson or lambda C meson or DS meson, and the quantum correlation of the D0 D0 bar mixing to study the D0 strong phase measurement. So it's a very unique data set actually in the world about this near threshold production. So it have a few many energy points which correspond to the two particle mass threshold, so which could provide a very unique advantage in the one is the kinematic constraint, another is very interesting physics correlation. For example, the quantum entangle the pair production of the charmed mesons of the in the production, and also the spin correlation of the Hyperon or charmed baryon near the threshold. So for the analysis technique, so since the threshold production, so you would expect that this pair production would provide something like not only the electron-positron initial energy and momentum constraint, but also the so-called tagging technique, and also using this full knowledge of the full momentum of the reaction. So we could using the missing mass technique to study the neutron and also neutrino and the K-long and so on. So it's very powerful method. So one topic is about the charm bihadron decays. So as you know, this near stretch production of the DLDS or lambda C hadron production near threshold. So for example, for the D or DS decays, there are actually 3 categories of these decays, which could be useful to study different aspects of the physics in the QCD and also electrowave theory. One is the purely lepton decay, which the weak force can be well decoupled from the strong force. So here, so you have very clean environment to study the QC dynamics of this during this purely lepton decay, and also with a very precise lattice calculation in this for this so-called decay constant, you can provide a very precise direct constraint on the CKM metric elements VCD or VCS. Another is called the semi-lepton decay. So it also can decouple the weak force from the strong interaction, but somehow the strong force became a little bit more complicated. So it means that the lattice QCD became more complicated and difficult to control its uncertainty. So it's been this way that this decay can be used to really constrain our non-typical QCD if theory calculation. And the third one is the hadronic decay, which also very important to study the iso-spin effect, also SU3 flavor symmetry, and so on, and also the final state interaction involves. So it's become more complex from the left to right. So, but different way that we can it provides it's useful information to understand the dynamics in this charm hadron decay. So one of the main purpose of this charm hadron decay is to constrain the CKM matrix. So BES3 provides direct measurement of this VCD and VCS using the purely lepton decay, and also provide the constraint to this VOB, VCB, and VTD, VCS through the gamma angle measurement by inputting the D0 decay strong phase. So the over-constraint of this CKM matrix would be important to find a kind of new physics beyond standard model, the source. So from this chart, you will see that using this purely lepton decay, the left one show you the direct measurement of the VCD at BES3 and compare with the previous results. You see that the very precise results from the D plus to mu at BES3 provide the most precise direct determination of this parameter by inputting the lattice QCD of the constant of FD. And in the future, with the 20 inverse Fennebar D Mason results, which is around 6 times more of the current data set, so we would further improve the precision down to like 1% precision. And also we can use the VCD from CKM filter to constrain the decay constant, also quite price, and show a little bit of deviation from the lattice QCD calculation. And future more price results from BES3 will show more clear clue about this deviation. Similar logical happens for DS decay. So we can extract the VCS And the recent 4 publications from BEST3 gave very precise results of this VCS measurement. And you will see that the error bar was largely reduced according to the recent BEST3 measurement. And also we can also on the other way, we can extract the constant by input the CKM filter results of the VCS. And you will see that the current lattice QCD agree with the BEST3 results. And using the semi-lepton decay of the charm meson decay, so at this, so we could input the VCS or VCD into the BEST3 measurement, and then extract the form factor of D2K or D2Pi. So the BEST results published in recent years that show that we really reduced dramatically the error bars. And however, you see that this yellow band is the lattice QCD calculation. So it means that we could really provide a very price constraint on their calculation. And this means that in the future, the lattice QCD need to improve their calculation in the future in order to make really tight, very tight test. And also, according to the quantum entangled DD bar data, so we tracked the strong phase from the charm data, and we measure this D2K0 pi pi, K0 KK, and D2 K3 pi and D2K pi pi. So with this strong phase, it's important input to the gamma angle extraction from the B to DK or the similar using the GGSA method. And the best results is provide important input data to really constrain the gamma measurement uncertainty for this part of the systematic, which will be important for run 3 at the RCB, or even the coming 50 inverse Fennebar data at Bio2 to really reduce this gamma angle uncertainty down to 1 degree. And also for the charm biome, it's also been thoroughly studied at BEST3. So we really using only like 35 days of data taking, with half inverse Fennebar of the lemon C pair threshold data, we published quite a few papers on its decays, especially the absolute branching ratio measurement of the lambda C to PK pi and the other 11 tabular field modes, which provide important input to the B factory studies. For example, the lambda B to lambda C mu nu to direct extract the VUB results, and also we published the first absolute branching ratio measurement of the lambda C to lambda E nu, and important to probe the dynamics of the lambda C decays. And as you see that in the PDG table, we are shown gradually to show break impact on the lambda C data. You see this star points show the star show the BEST3 results quoted in PDG, which somehow like the Clio C, they dominate the DSDK data in PDG when the Clio reduce its energy down from the B region to the charm region. So now BEST3 gonna keep producing more and more price data for the charm biome decays. And also another topic is about the spectral copy. So for the hadron spectral copy, BEST3 use 2 ways to study. One is the light hadrons, which through the chernium reduced decay or electron positron annihilation direct production. Another is a heavy hadron, which also it only can through the direct production, and also even from the radial decay and hadronic transition from the initial state and to the exotic or the conventional heavy hadrons. So above the DD bar threshold from the 3.8 GeV to up to 5 GeV, we collect quite a lot of data around the 23 inverse Fender bar. So one example is that in recent years, we really provide more and more details and more observation of the new decay of this very famous first exotic candidate of the X3872. So we published observation of the X3872 to pi0 Chi-C1 and also omega GSI and D0 star, D0 bar star. And also the transition study the transition of X3872 to gamma GSI and gamma Psi2S, and their ratio show the it's only upper. We don't see this its decays to gamma Psi2S, and which agree with the bio data, but somehow conflict with the Barbar and FCB results. So these things are important for us to understand the intrinsic structure of this X3872. For the so-called Y states, it's a vector charmonium-like state, which was firstly being observed at Barbar or bio experiments from the electron-positron annihilation. And you see BESS3 actually in recent years, they improve this and the knowledge of this Y4260 and Y4360 and Y4660. So you could see that from the below two plots, the BESS3 has a very precise data for pi GSI final states and pi Psi2S final state, and much improved our knowledge on these three Y states. So, however, we need to also check other final states. So BESS3 looked for electron-positron annihilation to eta GSI and pi HC and pi DD star and omega Chi-C0 and also and others which I didn't really explicitly list here. So we see that from all these final states, we see their cross-section line shape show non-trivial shape. That's they all many of them have the peaking structure around Y4260, but actually this 4260 is not really perfect Breuer shape, but it seems like it includes two structure. One is around 4220, another is a little bit higher around the 4300, some even higher. So you see that by fitting to them, we see one bump around the 4220, another a little bit much higher around between 4300 and 4400. So anyway, these things are new findings from BESS3, and we need more further careful investigation. Another is we call the tetraquark candidates. It's called the ZC family, which includes the constant quark components. Is CC bar, UD bar, and for this kind of this family, we actually observe the low mass state is the ZC3900, and also by decaying to pi GSI and also DD star, and their mass are quite close, and we see the neutral one and also the charged one. Another is the higher mass ZC is called ZC4020. We also see charged state and also neutral state, corresponding neutral state, and also it's decay to pi HC and also D star. So we have no concrete conclusion on their connections, and the more detailed study are still ongoing, and not only at batch 3 but also at other experiments. And we also determine the spin parity of the ZC3900, and by doing this very complicated partial wave analysis, and the speed JP is determined to be 1+. Besides this CC bar UD bar, we actually also looking for its SU3 partner of this ZC. So it's quite common. We like a CC bar U bar S. And to perceiving this states, so we analyze the data point energy between 4.628 and to around 4.7 GeV. And in the process, OE plus minus go to K D star DS star D0 and K plus DS D star 0. So we in order to improving the detection efficiency, and so we doing the partial reconstruction by only detect the K plus and the DS. So you see clear signal of DS and also the recurring mass of KDS, which show this D star 0 peak. And by slanking out this this process, so we see around enhancement around 4 GeV in the recurring mass of the K plus. So we interpret it as a Brey-Wigner resonance, and with the 1+ hypothesis of this JP, and show its mass is we call it is a kind of like structure of ZCS 3985, and weighs around 10 MeV. And so it's the first candidate with the hidden charm tetracard with stringness. And this state was also being spotted at RCB experiment by analyzing the B2 KGSI5, and it's just be published. And they also see a structure around 4,000 MeV, and in the gypside K mass region. And so we see that their mass position are close. However, the weights are show quite a large difference. So I mean that they could have some connection, but more study are needed. Additional one is this light hadron spectroscopy, which including the UDS quark, not heavy quark. So the famous one is XPP bar or X3872, this X1835 at bio at best 2 published quite some time ago, and they are confirmed with best 3 data, and now around this PP bar mass region, we actually not only see this 2 structure, but we analyze the more modes. So we analyze the photon plus Kishore eta, and photon and the radial decay to omega phi, and the 6 pion, and omega eta pi, and gamma phi. So all these decays, many of them we perform the partial wave analysis. Some are not, but many of them show some structure around the PP bar mass region, from the 1800 to 1880 MeV. And also we see quite interesting feature that for the X1835 observed in gamma eta prime pi, we see some line shape distortion around just at the PP bar mass threshold. So that show a hint of that this XPP bar and X1835 they should have some strong connection. In addition to this, that in this gypside to gamma eta prime pi, we see 2 higher mass states above this X1835. So it's called X2120 and 2370. So it could be kind of state with the gluonic component. So we also actually seeing this, it's this state in the Jip side goes to gamma KK eta prime or gamma K short eta prime for the X2370. However, it's not been observed in the KK bar. It's not in the KK bar eta prime, and also 2120 is not being observed. Another thing is that we also see some kind of like a strontium-like state called Y2175, which is now noted as Phi 2170. It could be explained in many ways, like the Y states I mentioned in the previous slide. And also BAS3 using the E plus E minus direct expression of these different hadronic final state like KK and also Phi KK and Phi eta and KK pi pi and Phi eta eta prime and Phi prime. So all these final states, you would see its cross section also show some enhancement around this 2.1 GeV to 2.2 GeV. So these states, which are not easy to be accompanied in this SS bar quark model predictions. So it's quite still a mystery what are these states. And also the strontium and also strange methane can be studied in the very high statics of the partial wave analysis of the psi or psi 2s decays, as the example shown here. So I will not elaborate the detail. The last topic I would show is that is about the baryon form factor. So at BAS3.
So if you could finish up quite quickly, please. You're a few minutes over time already. Okay,
thank you. So for the form factor of baryon, so we could study through the E plus E minus annihilation. So we see the threshold enhancement for the PP bar, and also the neutral production cross section also show the enhancement near the threshold. Interesting still that its form factor actually show the oscillation from the modified pole model. And seems like there is some feature of this oscillation which happens for PP bar and also neutron, anti-neutron. So similar, but they have different phase. With this form factor, we see that there are the electro one and the magnetic one, and their phase difference is shows some polarization effect. So we would really see this polarization for the first time at BAS3. And using this E plus E minus production of the hyperon antiperon spin correlation, we using their spin correlation and also the transverse polarization, we can precisely determine the decay parameters of this lambda, which solve over a long history and estimation of this lambda decay asymmetry. And also cascaded to lambda pi, we firstly determine its weak phase for the first time in experiment, and also very high precision. And similar analysis can be done for the Chang baryon, and I will not elaborate in detail. Okay, so for the future, we would increase the statistics more, and you would see that we have planned to upgrade the BPC2 energy to 5.6 GeV, which is still with very blank data here for the R. So we would for sure provide more data, and the luminosity will be increased by 3 times. Okay, that's all for my talk. Sorry for the little bit delay. Thank you.
That's great. Thank you very much for these very exciting developments at BAS3. If there's a very urgent question or comment, we could take it. I don't see any hands being raised, so I think in the interest of time, we should move on. Thanks very much again. It was a lovely talk. And I think we move on to the the last presentation of this session by Chengzheng Huan from IHEP Beijing.
I should stop sharing.
Yes, please.
Can you hear me?
Yes, I can hear you very well.
Okay, great.
Okay, so if you could please share your slides. Thank you.
So, can you see my slides?
Yes, we see them perfectly well. So please, the floor is yours. You have 20 minutes. Thank you.
Okay, thank you. First, let me thank the organizers for inviting me to give this review talk. I'm going to present to you the recent progress on this exotic XYZ state of the non-conventional quark model hadrons. So I will limit my talk on harmonium-like states only. And we know we have observed a lot of harmonium states since half a century ago in 1974 from the discovery of GSI, and then we observed a lot of harmonium states. We also observed a lot of harmonium-like states which decay to harmonium and other hadrons, and they have a very exotic property. So very probably they are exotic states. But in my talk, I will limit my talk to only a few of them. I only reveal these 3 states with information available from 2 or more experiments that you have already heard report from individual experiments. I will talk about X3872, Y4660, and the ZCS. Information on more of the similar states can be found in this recent review published with Nara from Bela and so on in this report. So first, let's start with X3872. This state was discovered in 2003 by a bio-experiment, and it was confirmed shortly by CDF and D0 experiment. This is a very clear peak. Over the almost 20 years, many experiments measure the properties of this state. Here I show the mass measurement from all these experiments, including the most recent one from L2CB experiment. The average of all this measurement is 3871.65 with 60 keV precision. We can compare this with the sum of the mass of D0 and the D star 0, which is only about 40 keV above this, this mass, with a precision of 120 keV. This indicates X3872 very probably is D0, D star 0 bar molecule state. If so, this state has a very large size calculated here. The size must be larger than 5 fermion. So it's very strange. For the weight measurement, it's even harder because it's very narrow. If one assumes it's a Bert-Wegener, it's a symmetric Bert-Wegener function to fit the distribution, one finds the weight around 1 MeV. In fact, this state, since it's very close to D0, D star 0 bar threshold, it can be, it should be parameterized with the Flaty formula. This is the denominator of this parameterization with contribution from D0, D star 0, rho GSI, omega GSI, and other decays. In this case, the parameter or the weight depends strongly on the G. This is the coupling to D star D0 bar. Unfortunately, L2CB cannot distinguish between these 2 parameterizations as shown here. If the intrinsic distribution like this, by convolving this mathematical solution of about 3 MeV, one cannot tell which one fits the data best. In any case, with the input from other experiments on this G, L2CB can determine the full weight at half maximum of 0.22 MeV. We can see this and this are quite different. In fact, the BAS3 can really supply information on this coupling factor. If you look at this plot, this is the inverse mass distribution of D star 0 to 0 bar with D star to D0 pi 0 or to D0 gamma. In this case, the mass resolution is only around 1 MeV or even better. So what you observe here is the real line shape of this X3072 to D0 D star 0 bar. So BAS3 can supply such information combined with high statistic measurements in pipette GSI from SCB. We can finally measure this weight better. The X3072 can be produced in many different ways. Here are lists the different production modes. From BDKs, this is the discovery mode. From BIS-BAS decay measured from CMS and LHCb, lambda BDK from LHCb, also from PP accretion, we have mentioned from D0 and the CDF experiment. And the PP accretion has been measured in ATLAS, CMS, and LHCb. Most recently, CMS also report the ladder-led accretion result as shown here. This is a 4.2 sigma evidence for this signal. It is interesting to compare the production of X or the production of Psi2S. We can see the ratio is around 1. If you compare with the same the production in the PP accretion, it is quite different. If this is confirmed, we must have a way to understand why it is so different, and this may supply us insight on the structure or the nature of this X3072. Another observation is E plus E minus to gamma X3072 from BAS3, shown here. This was first observed in 2014 with around 20 events. Then it is improved to around 80 events with small luminosity. So BAS3 can also measure a lot of branching fractions of this X3072 decay because the background level is very low. So in principle, BAS3 can measure of all the decay mode of this X decay. And the Bell tried to measure this X3072 in 2 photon collision. In fact, this production requires at least one photon is real and another one is virtual. So here, Bell observed the 3 events with a significance of 3.2 sigma, and we can determine the partial weight times the branch ratio to pipette GSI, which is 105.5 electron volts. The production of this X3072 in BD case is now measured in an inclusive way so that we know the inclusive production rate of B to K plus its X. With both B, with one B reconstructed and the recoil side, we look at the momentum of the cam, you can see there are a few small peaks corresponding to this germanium or germanium-like state. In the Barber data, you can see here that small peak around 3 sigma significance corresponding to this X3072. So Barber determines the branching ratio of this inclusive decay of 2.1 times 10 to minus 4. Bell did the same analysis, but the signal significance is smaller. It's only 1.1 sigma. And the branch ratio was determined as 1.2 times 10 to minus 4. In principle, we can combine these 2 branching ratio with this inclusive decay branch ratio and the sum of the product branch ratio of the B decays to Kx, X to some final state, and also the ratio of the branch ratio measured from BAS3. One can determine the branch ratio of X3072 decays. This state can decay into open charm final state like D0 bar, D star 0, or DD pi, DD gamma. Also can decay while hadronic transition to germanium final state or with a photon plus harmonium state like gamma J psi and gamma psi prime. Also, there could be hadronic decay or relative decay to light hadron, but this is expected to be small. In this slide, I show all the measurements related to this X32 production and decay. In this paper, this information are combined to chi-square phase to extract the branch ratio of X decays to different final states, including the possible unknown branch ratio of X decays. The results are shown here. We can find the decay branch ratio of X to rho J psi and omega J psi are almost equal at 4% level. This indicates great isotopy violation, since these two channels, as one has isotopy 1 and this one has isotopy 0. And the relative transition has a 1.1% branch ratio. And the open channel decay is about 50%. And we also know this unknown branching fraction is around 30%. So this needs to be further searched for at the Plenary and also Bell2 and other experiments. It is interesting to notice that the X32 gamma psi prime was reported as evidence more than 10 years ago by Barbara, but Bell could not confirm it. And later, L2CB reported an evidence even with higher significance, but the Plenary still cannot confirm this. So it is still not clear whether this X3872 decays to gamma psi prime or not. So with more data, in fact, with existing L2CB data, this can be further measured to say whether this is a real signal or not. So for this X3872, what we know recently is it's very close to D-star D0 burst ratio. It's very narrow, but we need to understand it's how narrow it is. Its quantum numbers is 1++, and isotopy 0, G parity plus. It can be produced in quite different modes. And the decay branching ratios with still 1/3 missing need to be further searched for. And this gamma psi prime needs confirmation. For its nature, we still don't know. Most likely it's exotic, but we need further theoretical efforts to understand this. So we move to the vector states, the Y4660. Here we have information from Bell, Barbara, and the Plenary experiments. We still don't know whether it is carbonium, it's the F0980 psi prime molecule, or it's a lambda-C bar molecule state. These Y states, in fact, we have a lot of Y states. They were discovered by initial state radiation from Barbara and Bell. Here in pi pi GSI, we observe this Y4260. In pi pi psi prime, we observe the Y4360 and this Y4660. Both Barbara and Bell observed this state. And there's another state observed in lambda-C bar close to threshold. So we focus on the state around the 44.6 eV. So here's comparison of updated Bell result and Barbara result on pi pi psi prime. You can see this peak is a little bit above 4.65 GeV, while in lambda-C bar, the peak is lower at around 4.63. There could be a hint of such state in E plus E minus the KKGSI, but not very significant. And recently, Plenary measured this pi pi psi prime cross-section with the data between 4.6 and the 4.7 GeV. You can see here the measurements are much precise than previous Barbara and Bell measurements. So Plenary also confirmed this structure at 4.66 eV. We try to fit this structure and extract the resonance parameters. Plenary also measured lambda-C bar cross-section, but only reported now the cross-section very close to threshold. We can see the measurement agree with bioenvironment, but with much improved precision. Best 3 has more data beyond the 4.7 GeV. So this cross-section and also lambda C bar can be further improved. We can see, expect better measurement of this cross-section up to 4.95 GeV. Bio trying to search for such states in open charm final state with charmed meson with string plot. Here is the observation of the structure with around 6 sigma significance in DSBEST 1, 25, 36 final state. You can see here a very clear peak with the peak cross-section around 100 picobar or so. There's also evidence for another structure in DSBEST 2 star 2575 3. You can see here the cross-section is similar to this one with large error bar. Pastor also measured the other open charm final state. The signal are shown here, but in these 3 final states, we could not find very significant structure around the open state. So if we put all these things together, we can find in psi prime final state, we still find this peak around the 4.65 or so. While in open charm final state, in lambda C bar, or in DSBEST 1, DSBEST 2, the mass is still lower than, but the weights are comparable, also with very large error. But that means there's still tension between the 2 final states, 2 different kind of final states. We still don't know whether there are 2 states here or they are the same state, but suffer from some problems in parameterization of this resonance shape. Finally, I will speak about this ZCS state. We have observed a lot of ZC states with quark component CC bar, UD bar, as shown here, including ZC 3900, observed at best 3 and above in Pipette GSI, and also in DD star final state. This ZC 4020 in Pipette HC, and also in Pi D star. And this one ZC 4030 from Bell and LTCB. So if it is easier, we can try to search for states if we replace this D quark with S quark. So this state can decay to K plus K minus GSI, or D star bar DSBEST and D bar DSBEST star. There have been 3 different analyses available. One is from bioexperiment with initial state relation produced C plus E minus KKGSI. This is Dahlia's plot. We try to see whether there are structure around mass square around 16. It seems that no significant structure. And this is the recent best measurement you have just heard from previous talk. There is structure very close to threshold of D star DSBEST. The significance is 5.3 sigma, and the mass width here, the width is very narrow. In a recent LTCB environment, this B to GSI 5K in the partial wave analysis, observed 2 structures correspond to ZCS, one at 4000 MeV with a very high significance, this one, and another one at mass of 4.2 GeV with up to 30 MeV or so. We can find that the weight of these 2 lower mass states, in fact, are quite different. One is more than 100 MeV, and the other one is around 10 MeV or so. So very probably they are not the same states. And in the best 3 data, in this analyzed data, there must be E plus E minus to K plus K minus GSI with higher statistics compared to the bioexperiment. So we need to wait for best result on KKGSI to see whether this state coupled to KGSI or not. So this is a summary of my talk. There are a lot of progress in the experimental study of the XYZ state. The X72 weights to be refined by experiment. There's still around 30% decay to be discovered. More data available for the Y4630 and the 4660 state, but still it's not very clear whether they are the same or what the nature is of these two states. There are 3 ZCS states discovered recently that need the confirmation from other experiments. More results to come and a lot of opportunities and challenges ahead. And showing this slide, we will have shown a lot of data from BIO2 experiment, from BEST3 and also the upgraded BEST3 experiment, and also L2CB, Atlas CMS will accumulate their own 3 data very soon. So we expect a bright future for the study of this XYZ state. So that's all. Thank you very much.
Thank you very much for this very clear talk and clear overview of these exciting results. Any questions or comments? I suppose just a comment on your final slide here. This is very nice to see that the near future is going to yield a lot of data sets from different experiments that will hopefully shed some light on this interesting puzzle.
Ну, 45 минут, да?
If there are no more questions, then I think maybe we can thank all the speakers again from this session, and I can hand back to Alexander to let us know the next steps.
Yeah, thank you. Thank you very much for all speakers and also for Paul for just conducting this session. So now it's time for lunch break. Well, sorry to say it will be very, very short. So, and we shall start 2:45, a quarter before 3. Yeah, same time. Yeah. Well, thank you very much.
Hello, everybody. I hope that you can hear me.
Hi, Ivanka.
Hi, that's great. Okay, perfect. So I would like to welcome everybody to the session dedicated to future linear collider projects. According to the organizer, we have a few minutes more to wait, possibly for more people to join. The first speaker is Manshi. So maybe you can already set everything, Manshi, and show us your slides.
Okay, but I think probably the screen sharing from the hoster now need to be switched off in order for me to share.
Needs to be switched on. Okay, our colleagues from the organizing committee can hear us. So yeah, you can share.
We shall just do everything. We have done it, but I suggest to wait.
Of course, we are going to wait. No, just
also we are too late,
ready.
but I think it's probably 2-3 minutes will be reasonable to wait. But thank you.
Thank you, Alexander.
Yeah, thank you.
Okay, so I guess my screen can be seen.
Yeah, it can.
Okay, cool. So we just wait for more people. So.
Well, it would be great to enter the full screen mode. That's perfect.
Absolutely.
Thanks a lot. Thank you.
Okay.
Alexander, may I ask, was it very interesting discussion that is the reason for the delay we are currently experiencing?
Well, Ivanka, you are not the first time participating in the Lomonosov conferences, and we are quite happy and we are proud of this. And you know that everything in the Lomonosov conference is very interesting. So.
Well, the pleasure is mine. I'm looking forward for the next time in person in Moscow.
Yeah, sure. But you see, as I just told in the beginning, or probably my comments, we were waiting for the last moment to announce this very sad decision that the conference will be online. If you remember, initially we hoped that the conference will be in person, totally in person. Then we just slightly softened this statement, saying that parts and parts, or part is in and partly online. And then when really it has become obvious in probably in the beginning of June, I suppose, that it's quite not realistic to have this conference in person, but we were waiting for some, probably 1 month to officially announce that we will be not able to invite people here personally. Yeah, but nevertheless, I think that in a certain extent we managed to organize this event in a regular time, not postpone it for 1 year or just for a few months, like some conferences used to do this. Well, and we are thankful for all speakers who just not write but participate, and also to conveners and also to the members of organizing committee who just, in particular, your contribution is very reasonable, and we are thankful to you for support of this event.
Well, Alexander, the pleasure is mine that we are going to have a dedicated session to future Higgs factories, and we now have both circular and linear machines. We are going to start with circular within a few minutes, and my prominent colleagues from the experiments are here, so I'm also in depth to them.
Yeah, we are also very happy that the future prospects will be discussed, and
let us wait for 2 more minutes to,
I think,
to stick to the schedule, and then we will start. 20 minutes is foreseen for talks and 5 minutes for discussion. Of course, we can tolerate a minute or two more, but I kindly ask the speakers to stick to this time frame.
Of course. It's,
presentations.
So now we are late for, I think, more than half an hour, I suppose. Yeah, Kost, we are waiting. We are late.
We are 40 minutes late. We should start at and 2:05, so 40 minutes.
Yeah, but we have changed this. We just added one talk 2 days ago and in the morning session. So, and we just make a shift here in the program.
We have a stable number of 28 participants, so people are apparently not joining anymore. Our speakers are here, and I would like to give the floor with pleasure to Manshi Ruan from the CPC Physics Group to give us CPC Physics at a glance. Manshi, 20 minutes are yours.
Yeah, thank you very much. Thank you for organizing this wonderful event, and also thank you for this invitation. So in my talk, I will basically telling you the physics motivation and the physics capability of this future circular electron positron Higgs and also a Z factory. So, so let me first start with a very straightforward motivation introduction. We all know that the standard model is tremendously successful, that it's fitting desperately well with almost all the experimental data from Collider experiment. But on the other hand, especially from the cosmos and the neutrino frontiers, we know there is a lot of problems. Despite that the standard model itself, in the theoretical point of view, I think it still have some flow. But anyhow, see here, I just listed a handful of the problems, the known unknowns of the standard model here, including the inflation, mass hierarchy, neutrino mass oscillation, etc., etc. But in all these questions, if you just look careful enough, you would find that the mass seems to be a key word. So that is a common clue in behind all these questions. So that is also to say, in this sense, that the origin of the mass, the Higgs field, would be a good place to look, to study, if we're trying to further understand those questions and maybe even find the new principles underlying the standard model. So that is the key ideas behind the Higgs factories. And actually soon after the Higgs discovery, people come to the idea of having a circular collider. So on page 4, I simply listed the orders of magnitude of these facilities here. So being a circular collider, that is the CEPC will have a total circumference of 100 kilometers of that order. And then in 10 years of operation, it will be able to produce 1 million Higgs boson together with close to 1 tera Z boson, or maybe slightly more than 1 tera Z boson. And meanwhile, you will have 100 million W bosons for free directly coming from the Higgs operation. And this can certainly also run in the W spectral scan, which will produce you more W bosons. And meanwhile, in the long term, being a circular collider, that can be upgraded to a proton-proton collider with very high central mass energy. So if we will be able to make the critical technology R&D to make the 20 Tesla dipole field, the dipole magnet, then this size of the circumference will allow us to reach 100 TeV central mass energies. And the interesting thing here is that the electron, positron, and protons are, well, they generate very different physics processes. So they actually provided very different informations and are highly complementary. So in this sense, that the circular electron-positron collider or electron-positron collider, they will provide a lot of very valuable information on top of the current ongoing LHC Higgs studies. And in the far future, then the SPPC or 100 TeV PP collider will also continue this complementarity and bring us a lot of new informations, including the direct search for new physics and also very high precision measurement for example, for the Higgs self-coupling, etc. So this altogether is certainly very ambitious and provides a scientific program of maybe half a century. Okay, and being running at the E+E- collision mode, then the circular, the CEPC will mainly be operating at 240 GeV central mass energy. And at this energy, then the majority of the Higgs boson will be produced through the ZH process, the Higgs stratum process. And the beautiful part of the E+E- Higgs factory is that in the ZH process, you can basically using the recall mass method. By identifying the decay product of the Z boson, you can tag the Higgs event, and in such a way that it allows you to measure more independently the generation cross sections of sigma ZH. And this then becomes an anchor, then allows us to measure the other Higgs parameters in a minimum model dependent way. Okay, so this will also allow us to reach, I will explain in one slide, the absolute Higgs width. Okay, and on page 6, this shows basically the timeline of the CEPC project. So people begin to talk about this concept right after the Higgs discovery, and in the 2015 and the 2018, we released the pre-CDR and the CDR of this project. Basically, at the published conceptual design report, we define the baseline parameters and baseline setups of the accelerator, detector, etc. And now we are in the pre-construction phase where our accelerator colleagues are working very hard trying to finalize the TDR. Meanwhile, with a lot of key technology R&D, and we're trying still to enhance our international collaboration. Then if everything goes smoothly after we receive the green light from our government, we hope that we can construct this facility in roughly 10 years of time, and then we can start the data taking. And meanwhile, we also investigated significantly in the 20 Tesla dipole magnet R&D, and this has been started at a very early stage. So we hope that during this cultivation for several decades, then the technology will be mature enough for we to construct the SPPC with acceptable cost. Okay. And page 7 shows you that this is basically a release of the CDR in 2018. And here we baseline of everything, and we also give we quantify the core physics potentials. And we need to say that the write-up, the work of the CDR, actually including very significant international participations. Okay. And this I show basically the configuration of the accelerator. So the accelerator was composed of 3 key ingredients. That is the NINAC, then the booster, and then the storage ring. So the NINAC was shared by both the electron and positron beams. They accelerated electron and positron beams at a different time, and then they injected into the storage ring. This storage ring, they share, in the storage ring, the electrons and the positrons are separated, except they share to use the IF station. Because of the IF stations, the supercavities, superconducting cavities are pretty expensive. So such a configuration actually allows us to control the construction cost. And at the CDR time, basically, the lower table listed the luminosities at the different operation mode. So at the CDR, then we hope that, oh, sorry, I listed it wrongly here. For the Higgs running, that it will have instance luminosity of 3 to 10 to the 34 and 10 for the WW threshold, and for Z, that will be roughly 1 order of magnitude higher than Higgs operation. And our accelerator colleagues continuing to trying to still enhance these numbers. So now we believe at the Higgs operation, we can reach an instance luminosity of 5 to 10 to the 34. So roughly 60% of improvement. While for the Z operation, then the instance luminosity can be increased by almost a factor of 4. Within the same IF radiation power. And then for the baseline detector design, at the CDR time that we use a PFA-oriented design, where we have very high granularity calorimeters to separate the final state particle showers. So this design was originated from the ILC-ILD design, and we make necessary modifications of optimizations to make it to be compatible with the CEPC collision environment. And such a baseline setup basically allows us to see the very detail of all the Higgs event. So here you can see 4 different event displays corresponding to the different Z Higgs final state. And you can see that it's very easily to be distinguished even with human eye. So you can do this at the human eye, so you can certainly do this at the software level. And you can certainly also do this not only for the signal, but also for the background. All this together actually allows you to characterize very precisely your physics event by distinguishing their natures. So basically this setup allows us to see very clear Higgs signals in all different standard model Higgs decay channels. And this one basically leads us to a very good measurement for the Higgs boson properties. So here on this page 12, I show you probably the most characteristic measurement of the Higgs measurement at the electron-positron collider. That is to using the recall mass method to determine the absolute cross sections of the ZH process. And because of the Z decays into dimuon and dielectron and also dijet final state, so you can basically measure them all independently. And the combined accuracy needs to 2 Pamir level accuracy of the Higgs to ZZ couplings. And of course, once you tag the Higgs event, you can look into the decay side. And this basically allows you to measure the correlated Higgs decay branching ratios and the Higgs couplings to this decay final state, etc. So here I listed a few of the examples, for example, the Higgs to the ZH in the right up plot, and the W fusion process with the Higgs to VB final state, and also the Higgs to tau-tau final state. So actually we almost made a full coverage of the Higgs decay final state at the CDR time. And the combined accuracy was listed in the lower plot with this so-called 12 parameter EFT feet. And the precision here is compared between the CEPC and the high luminosity LHC in C extrapolation, where you can see that for many of the parameters that the CEPC can improve the accuracy by roughly 1 order of magnitude. And some of the parameters is actually very hard to be measured. For example, the Higgs to CC couplings, but it can also be determined to percentage level of accuracy at the circular electron positron collider. And of course, if you can get access to the Higgs decay product, you not only can measure the Higgs to standard model couplings, but you can also searching for the exotic decays of the Higgs boson. So here, basically, this plot shows you the upper limit you can get with Higgs boson, with Higgs to different decay final state, exotic decay final state, including the missing energy with a pair of B jet, with a pair of jet, a pair of tau, etc., etc. So in all these exotic decay modes, then you can see that really the sensitivity is improved by orders of magnitude with respect to the high luminosity LHC. Another advantage of the CEPC or CE plus E minus Higgs factory is that you can measure the Higgs boson width, or you can derive it in a model independent way, more or less. So basically the trick is to combine the different measurement and derive the Higgs widths accordingly. And there are two methods that is relatively promising at the CEPC. That is combining the Higgs the sigma ZH measurement with the branching ratio of Higgs to ZZ measurement. And if you combine them together, we will get a precision of roughly 5% to determine the Higgs total width. And there is an alternative method, is combining 4 different measurements together, including the W fusion with Higgs to BV or more general Higgs to dijet, and also the Higgs to BB with the sigma ZH within the Higgs stratum channel, etc. So this channel basically gives you a precision of 3.5%. And if you combining all them together, then you will be able to reach a final precision better than 3% to determine the Higgs total width. Okay. And all these studies had actually been summarized into what we call the Higgs white paper, And in this paper, we also discussed the capability of determining the first order phase transition that is essential for solving the matter-antimatter asymmetries. So we also believe that the CEPC can do a very good job in telling us that if the universe is going through first order phase transition in the very early universe. Okay. And in the recently, we have studied upgrading option. So that is to running the CEPC at 360 GeV central for mass energy. And we started with a nominal luminosity of 2 inverse atavar. So at this energy, of course, we opened basically the TT bar threshold. We can do a lot of important measurement with respect to the top polarity and also self-coupling and also for the new physics as such. So this motivation is very nicely explained in the middle plot where I taken from Alain's presentation. And meanwhile, for the Higgs boson, it is also have significant impact. So first of all, we will have 30% more Higgs events. That is for all the Higgs couplings that it will be improved accordingly. But more attracting is that we can improve very significantly the Higgs width measurement because at the 360 GeV, then we will have a lot of W fusion event, while the W fusion event determination is the bottleneck for the Higgs width measurement at 240 GeV. So with only 30% more Higgs bosons, then the Higgs width measurement can be improved by 2 times using this additional data at 360 GeV, making it very compelling, very attractive for our Higgs program. And of course, the CEPC is not only a precision machine just to measure the Higgs boson properties. So using the tera-Z and hundreds of millions of W bosons, we can also perform very precise electroweak measurements. And the left-hand plot basically shows you the anticipated accuracies of the measurement for the electroweak parameters and the comparison to the existing, to the current accuracy. So basically, we can also see an improvement of roughly 1 order of magnitude, and in some of them is close to 2 orders of magnitude. And this potential is also displaced in the right-hand plot, where it is showing you the counter of the oblique parameters, and you can see this counter, the area is significantly shrinking with the CEPC input and compared to the current counter. And another thing pretty interesting is that the CEPC or accelerators of this kind can probably share light on the new physics, on confirming the new physics behind the new GMIS2 experiment. So the picture is very simple. So if there is new physics, then this new physics will perturbate to the mu parameter. So basically it's a Z to mu decay branching ratio. And this perturbation will be of the order of 10 to the minus 4 level, which is at the accuracy of the CEPC that can be achieved. So that is to say, basically it can provide the information at least for confirming, cross-check this very interesting observation. And another thing we noticed very interesting is the potential on the flavor physics at the CEPC. So being a TerraZ factory, that the CEPC can actually produce a lot of the heavy flavor hydrons like B0, BS, BC, lambda B, etc., etc. The right-hand plot, the right-hand table basically shows you a comparison of the anticipated statistic at the TerraZ and with respect to the existing flavor facilities like the BEL2 and the HCB. So it is actually quite characteristic. So versus the B factories, then the CEPC or TerraZ can have much higher B quark or C quark boost and can also produce much heavier B hydrons that exceeding the central mass energy of the BEL2, for instance. And versus the LHCb, that the CEPC have much cleaner collision environment, but of course the yield is 3 orders magnitude lower. But meanwhile, the CEPC detecting systems can detect the neutral final state and also the missing momentum measurement very precisely, which is unique, which is quite a significant comparative advantage of the TerraZ factory. So this flavor factory can actually do a lot of interesting physics. And one of the very important topics it can explore is to study the lepton flavor universality, the RK star, RD star problem, because we all know that currently there exists quite some sizable tensions in between the standard model prediction and the experimental observation. So for the advantages that I had stated before, then actually we found the lepton flavor universality can be explored in many of the promising channels, mainly through B decays. So for example, for the BC to tau nu decay, then at the CEPC, it can reach absolute precision of 10 to the minus 4. It can also study the B to S tau tau transition decay, and the absolute precision is of the order of 10 to the minus 6, which is 3 or to 4 orders magnitude improvement comparing to the current limit. And also you can use the very difficult channels for the BS to find new. This channel will be pretty difficult at LHCb, but at the CEPC, that we believe it can reach absolute precision of the 10 to the minus 7. And we also studied the relative topics such as IJ psi and B star, etc., etc. And for all these channels, we compose them and into a EFT framework. And basically the final conclusion we get is that in this EFT framework, this lepton flavor universality can be basically able to tag the new physics up to 3 TeV at that new physics scale level. And meanwhile, this flavor factory can certainly be used to searching for the lepton flavor violation from the Z decay and the tau decays. So this can basically also be sensitive to the new physics up to 20 TeV, 20 TeV or even much higher new physics scales. And certainly that this facility can also be used for the QCD studies. So here I put a few of the key questions that we grabbed from the discussions and the studies with QCD experts. That is how to achieve the ultimate precision of RFS measurement. And can we see gluon spin interferences to how to observe entanglement from the non-global observables such as the energy correlations. And yeah, very interesting is how well can we understand the process of the hydrogenization, etc., etc. So all these questions can be actually explored and probably quite efficiently at the CEPC. And the conclusion is that, yes, the CEPC can do a lot of things with respect to the QCD and can open the new potentials for ultimate precision and can really solve or address the deep theoretical puzzles, such as in the hydrogenization process. Okay, so now I come to my conclusion. I think the CEPC is not only a high precision Higgs factory, but certainly a discovery machine. So what we know is that it can boost the Higgs and electroweak precisions by orders of magnitude with respect to the high luminosity LHC or the current boundaries. And it also have huge potentials on the QCD, flavor, and the BSM. So to better understand its physics potential, we are actually currently promoting the dedicated physics studies to further quantify its potentials with benchmark analysis and global interpretations. And those studies is also provided the useful information to guide the design and optimization for the facilities to maximize the physics output. And certainly, if you have ideas, please let us know. It's more than welcome. And also that given the importance of the electron positron Higgs factories and its deep link to the very important questions that I mentioned at the very beginning, so that we hope that at least one of those electron positron Higgs factories can be realized. Thank you.
Thank you, Manchi, for this very comprehensive talk on CEPC. We have a few minutes for discussion. Are there any questions? Yes, Mikhail, please go ahead.
Yeah, hello. Thank you for this talk. It's very nice to see what we can achieve with this machine. Do you have some estimate when the decision will be made if you are going to do it or?
That is what we literally lost our prediction power to some extent. No, I cannot really give you a very, very dedicated answer on that. But we are trying pretty hard through the different channels to promote this, these processes. So the thing I can say is to stay tuned, and it can occur at any time. Yeah.
Okay, thank you.
Any other questions?
Yes, I would have a question to Manchi.
Yes, Alan, go ahead.
Manchi, thank you very much for that great talk. Did you converge on a particular place where to build this machine?
Not yet. Actually, we contacted at least 6 or 7 different local governments, all showed very high interest in to host this machine. And meanwhile, we all studied the civil engineering studies with the local geology, and many of them actually have pretty good geological conditions. So I think the final decision is yet to be made. It is actually waiting for the green light from the central government, and then it is a bidding game to some extent.
Okay, great. Thank you.
Thank you, Manchi. I have just one question. Previous speakers asked to some extent what I also wanted to ask about the possible timescale. My other question is on the level of technical details, because we learned from all these plus machines that the level of details of simulation, the fact that you introduce the full list of possible backgrounds really can affect the estimated precision of your results. So for instance, in terms of Higgs couplings, can you just give us a word more on the level of details that these individual measurements are performed at? Is it a fast simulation? Is it a full simulation? So what is the situation there?
Yes. So for the Higgs measurement at the CEPC, for actually most of the studies that we presented in the Higgs white paper, it is based on the full simulation. So of course, the full simulation can still be a little bit ideal. For example, we didn't really include in beam background, since we believe the beam background will be not really severe at the circular colliders. And also the material budget, etc., can always be discussed. Maybe it's a little bit more optimistic. But what we had done and had put into both the CDI and the white paper is mainly based on the full simulation. That is to say, one of the biggest uncertainties, meaning the uncertainties from the reconstruction, etc., had been already taken into account. And meanwhile, for the simulation of the background processes, we believe we included all the leading important standard model background. So at this stage, I believe that those numbers we get from in the white papers is pretty reliable, I think. And meanwhile, for some future further studies, for example, for the physics potential estimation at the top threshold at the 360 GeV run, there's a combination of both full simulation and faster simulations.
Thank you so much once again, Manchi. And we are now moving to our second speaker, which is again from the world of circular machines. Alain Blondel will give us a talk on FCC-EE. So as soon as you can, Alain, please share your slides with us.
Unmute. I'm there.
You're back. We can hear you.
Yep. You should be seeing my slides very soon.
Yes, perfect. Just go to the full.
Okay.
Full.
So I am in a place which has no internet and no Wi-Fi, so I hope you can understand what I am saying. I will go through the highlights and challenges of the FCC-EE with many thanks to all the FCC collaboration. This is a view from the top of the Jura mountain, which shows a sketch of the FCC. We do have a site. In fact, we have only one site, which is the around Geneva and CERN, and around that mountain, which you see there, which is the Salève mountain. We have extensive siting discussions right now with the authorities and all the legal staff. So what is proposed is the FCC integrated program, just as Manchi mentioned for the FCC-EPC. We start with the FCC-EE as a ZW Higgs top machine, which is also a flavor factory, tau and bees in particular, with high luminosity. And that will be followed by the FCC-HH, a 100 TeV machine continuation at the energy frontier. Now, the two machines fit in the same tunnel. So the tunnel has been designed to fit both machines. In fact, right now, we have a tunnel that could host the FCC-EE with 2 or 4 interaction points. The European strategy of 2020 gave the following recommendation. Europe, together with international partners, that's you guys, should investigate the technical and financial feasibility of a future hadron collider with a center of mass of at least 100 TeV, with an electron-positron Higgs and electroweak factory as possible first stage. Such a feasibility study of the colliders and related infrastructure should be established as global endeavor and be completed on the timescale of the next strategy upgrade, which is 2025, 2026. That represents the feasibility of the colliders, EE and HH, and the related infrastructure. So that is clearly the highest priority after HL-LHC for European particle physics and its international partners. That's called the Plan A. We have changed the logo a little bit, and we need to be a planetary project, as you can see. There were some recent news which I want to share with you. In June 2021 was a CERN Council session, and the FCC feasibility study 21 to 25, so 5 years, was proposed to the CERN Council and approved unanimously. They also added a little present to it, which is there is 100 million francs for over 5 years in the CERN spending plan. I give you the links here to the council documents related to the organizational structure of the FCC feasibility study and the main deliverables and timeline. The financial study agreement was not so easy, but there was one very clear condition. The financial study will focus on the tunnel and the first stage collider. It was felt by many state representatives that it wasn't reasonable to do a financial study of the FCCHH yet. So the FCCE and FCCHH design with their injectors, key technology, technical infrastructure will be done, but the costing will be given for the FCCEE and the tunnel. Also MDI and energy calibration for the FCCEE. Physics case and detector concepts will be consolidated for both colliders. Intermediate review, mid-2023, delivery of the feasibility study report at the end of 2025. First collisions in 2040 or shortly afterwards. Okay, there's a big stress on the importance of communication towards the scientific community, you guys, governments and funding agencies, industry, and general public. So it's really an all-out effort at CERN. Work has started on placement in Geneva, reduced the number of surface points to 8 from 12 in the CDR. That saves quite a bit of civil engineering. Layout consistent with the later choice of 204 IP for the E+ E- collider. If you have 4 IP, I will show you number of events, etc. for 2 IPs. For 4 IPs, you have to multiply this number, overall number, by 1.7, almost a factor of 2. In parallel, you have the high field magnet R&D for the FCCHH will be carried out with high priority, and that was given another 100 million Swiss francs over 5 years. So the CERN has gone all out, and I think this is an important step, both for FCCE and FCCHH. They are now getting one step closer to reality. There are several steps to do, of course. This is the plan of work for the feasibility study in the next 5 years. We are here. We'll have a physics workshop beginning of February 22. We have a next workshop, implementation scenario in June 22. And we have a workshop and midterm review, which will check the general coherence of the project and the CDR cost update. And then we'll have a detailed design phase until the final state feasibility study report will be produced in 2025. So this seems like a long time, but this is of course a large project. So I felt it was important to compare this timeline with that of LEP and LEC, which is a similar scenario. The first yellow report on LEP was 76, and the construction took place between 81 and 89. Then we had 12 years of operation, this 9+ installation until 2010, and 30 years of operation until 2040 for the LEC. That's a total plan of 66 years. So if we are here in 2021, we start operation in 2040, and then 10 years of operation for the FCCHH. The system of access to the ring has been designed so that it can be installed fast enough. 25 years of operation, you end up with 70 years. It's not all that different. Okay, so that's what we're trying to do, and it's another, if you wish, same victorious plan which is proposed. I give you a page with documentation. I'm not going to read it. And a page with an overall book that we are going to produce soon on Higgs and electroweak factory challenges towards discovery. I think it's important to understand that these are not easy experiments to do. And I will show you one particular reason why these are not easy experiments to do. It's just because the machine is very good. And so the experiments have to be done very well. Okay, a little bit of general motivation. I think this is very similar to what Monkey said. The important point to notice is that it looks as if everything is consistent with the standard model, which dates back from 1976, has been completed. That is, all particles which have electric charge, QCD charge, or weak isospin have been discovered. What's important to note is that the precision measurements done at LEP were useful to predict the top quark and Higgs boson masses, assuming nothing else. So we have to be ready for a situation where there's no more standard model coupled particles. Okay, that's the same. Another point which is really interesting is that the standard model can be extrapolated all the way to the Planck scale, provided there's no new physics in between. Of course, you can always tweak this new physics so that it matches this constraint, but it's already there. So, of course, it's not the end of particle physics for all the good reasons that Monchi described. Dark matter, baryon asymmetry in the universe, neutrino masses are not explained with the standard model as it is today. So we need to understand more. Of course, direct observation of new particles is great. History shows that before doing that, new phenomena have been discovered that point to those new particles. Neutral currents pointed to the Z boson. Neutrino oscillations point to heavy neutrinos, in particular right-handed neutrinos. CP violation pointed to 3 families, etc. Deviations from precise predictions have been used all along in history since a very long time. And recently we have G-2, flavor anomalies, etc., starting to make a puzzle that might be the sign of new physics, which is not similar to the one we already know. Okay, so the thing that we are advocating is that the FCC, thanks to synergies and complementarities, offer the most versatile and adapted response to today's physics landscape. That's the FCC running scenario. We want to start at the Z peak. The machine has been designed to produce a luminosity of 4.6 10 to the 36 per square centimeter per second at the Z peak, and we will go one step after the other, all the way to the top quark, 360 GeV, 265 GeV, with luminosity of 3 10 to the 34. The center mass energy errors are very small. That's thanks to the large ring, which allows the buildup of transverse polarization. And I will spend a bit of time on that. Okay, so the physics at FCCE, Higgs factory, electroweak precision, we will go from 10⁻³ to something like 10⁻⁵, sometimes better than a factor 200 precision increase, as I will show you. And of course, there's a very interesting program at the Z factory, as Monchi insisted. We have been a bit more ambitious with the luminosity. This is the famous specialty of the E plus E minus Higgs physics, which allows to make all measurements at the Higgs model independent. You measure the total width and then you normalize, all the branching ratios become couplings. I have put here the precisions of a number of Higgs couplings to the known and unknown particles. And of course, you have here a description of HLLEC, and in red, I mentioned that some of the important branching ratios are not measured, and the total width, of course, not measured at the LHC. So everything that comes out of the LHC has a degree of model dependence. As soon as you put in the FCCE, the Higgs width will be measured with the precision of the percent level, and everything else will become model independent, although the Hadron Collider brings in the precision for a number of rare channels. This first column is the FCCE by itself, and this is when you add the LHC to it. And you can see that some measurements, particularly the gamma gamma, the Z gamma, the TT, and of course the triple Higgs coupling, are better measured. At least the statistical precision is much better at the LHC. The FCCE will make those measurements model independent. Then when you add the FCCHH, which has much higher Higgs production, all these measurements, the green ones up there are all coming from the EE machine, and those here are coming from the combination of EE and HH machine. One of the measurements has a big contribution from the EP option, which is the W coupling because of the charge current production of Higgses. So it's a very interesting combination to put together EE and HH in the same program. Now, it's very important because I should stress that there is actually no plan to build FCCHH alone. Mention, because I'm talking to a Russian community, mention the beam polarization and center of mass energy calibration. This is a work we've done with this working group here. And we had very strong contributions from the Novosibirsk group with Bogomyakov, Kopp, Levichev, Mushnoy, Nikitin, and Shatilov. The energy calibration is crucial for the measurement of the Z mass, the Z width, the forward-backward asymmetry slope. Okay, the slope is a measurement of alpha QED of MZ, and the intercept at the Z mass is a measurement of sin squared W effective for the forward-backward asymmetries to muons. They will measure also the W mass. And one thing that we're trying to do, which will be very interesting, is to measure the Higgs S-channel production, which is a measure of the coupling of the Higgs to the electrons. That's going to be a very hard measurement. It has big demands on the energy calibration of the machine. You have to run all the time with a center of mass energy, which is known to a better precision than the Higgs width, which is only 4 MeV, so 4 10⁻⁵. Okay, so that's another description of this. We need to use a monochromatization to reduce the energy spread of the beam and have a continuous monitoring and adjustment of the center of mass energy. We are not completely certain we can do that measurement. And so if you are really interested in challenging things, this is a good place to make a contribution. Center is a problem. There are, in particular, there
I have to ask colleagues from the organization committee, what is going on? We cannot see any more Alain's slide. That he's having some difficulties with internet.
Is that okay now?
Yeah.
Okay. I was disconnected for I don't know how long. When did you lose me, Ivanka?
I think it was on the previous slide, but please, Alain, speed up because you have officially 1 minute more to go, but let's say a few more minutes.
Okay.
We will add to you. Thank you.
Okay, I'm trying to come back to my own. I'm screen sharing, yes. Okay. All right, so I come to the interaction region, and the design is quite specific. You made a question before whether we're using full simulation of the backgrounds. The answer is yes. When we're talking about 10 to the 12 events, we are not using full simulation of 10 to the 12 events. We are using modeling. I should point out that when you do full simulation or not, you have to sit down in front of a piece of paper and think about the systematic errors in a different way. Okay, the big challenge is these precisions on electroweak observables at the Z peak, because the statistics is about 2⁵ times more than the Z. Typically, we have a factor 500 better statistical precision than at LEP. One important comment is that for some observables, like the B observables, RB, the ratio of hadrons, the B to all quarks, the ratio is 2000 because we gain not only from the statistics, but also from the higher efficiency due to the much better B tagging we can get with the small beam pipe. The same is true for the tau lifetime. That should be improved considerably, as well as the tau mass and the tau leptonic branching ratio. These quantities allow you to measure G Fermi with a precision which is similar to that with the muon, which is a great test of lepton universality. You can see all of those things. The theory work on this is extremely important because it's easy to predict these quantities with that kind of precision. So this is a more detailed table which you can contemplate at your leisure. Do mind the statistical errors. My experience is that good physicists always come down to the statistical error unless there's a very, very good reason. Okay, so this theory challenges have been already realized, and several workshops have already happened in looking at the theory requirements and possibilities for FCCE and other future high energy and precision frontier lepton colliders. So these people say, we can do it, but give us 500 man-years over the next 20 years. That's a nice and precise estimate that was given in our CDR. That should be taken into account very seriously. Okay, if you do that, reduce those errors, you'll diminish. You see, this is the plot that the orange thing is what Manchi showed you. That's what we get where if we have the systematic errors at the level of the statistics. It's really a big, big improvement. I should mention one last little bit, which is dark sector as a Z factoring. And this has been mentioned already several places. The most interesting maybe item is the possibility to produce heavy neutrinos, which would be the partner, the right-handed partners, Majorana particles of the left-handed neutrinos. And typically, we get down to this between 10 and 90 GeV, we get down to the levels which are those expected for the baryon asymmetry to be created by resonant oscillations. So it's a really very fundamental aspects of the program. Okay, that's a good plot simulation of a heavy neutrino where you see just the heavy neutrino decaying about 60 centimeters from the primary vertex, and then a neutrino opposite to this. The background to this is essentially nothing. And we think we can search for it down to 10⁻11 branching ratio. Okay, so conclusions. The FCC technical and financial feasibility study has been launched. The first stage of the FCCE, has great physics opportunities as a Higgs factory, also as Z, W, top and heavy flavor factory. High luminosity, clean environment, and effective MDI. We have a 10mm beam pipe, and I should mention it, 100 microns dead space, dead angle in the forward direction on both sides. The big challenge is to match experimental and theory systematics to the statistical precisions. And I give some conditions for being successful there. Just say that history has shown that systematic errors are usually statistics limited. The FCC is a global collaboration, so now is a good time to join the feasibility study. Thank you.
Thank you, Alan. We are a bit short with time. Are there any urgent questions to Alan? Oh, everybody is impressed, Alan. Apparently no questions. I would just have a tiny one. I would suspect that your uncertainty on electron coupling would be of order of 10% at least, and presumably much higher. What kind of new physics hint are you expecting from this particular measurement?
That's a very good question, Ivanka. Yeah, I think you are even optimistic. I think we can get this measurement to within a factor of 2 or so. But that would still be much, much, much better than anything you can do even with the FCCH. Okay. You have to understand this is a coupling which is 10⁻8 or so. This is the electron mass. So any new physics that couples to both electrons and the Higgs would produce a loop effect that would completely blow away that branching ratio. So there are some examples and some references which you can find in the article which I show here. The article by David Anteria, Measuring the Electron Yukawa Coupling by Resonant S-channel Production, which I show on my slide 9.
Thank you very much, Alan. I'm sorry that we have to rush, and we are rush again to the future with Jenelist from the perspectives from linear colliders. So Jenny, please go ahead, share with us your slides.
Yes, hello everybody. Okay.
It's a full screen mode now, please go ahead.
Yeah, hello everybody, and many thanks to Ivanka and the organizers for inviting me. I'll switch gears now from the circular E+ E- machines towards the linear ones, in particular the ILC. So here. So I think we heard a lot of excellent physics motivations for Higgs factories in general, both today and also actually on Thursday in your talk, Ivanka. So let me directly come to what is the key point about the linear colliders. So while of course the Higgs program at 250 GeV is very similar to those of any other Higgs factory, the important difference, of course, with the linear collider is for once that you can make it longer, so you can upgrade it to higher energy. And therefore, even in its baseline program, the ILC comprises this 500 GeV stage, where one can really also aim to cover the double Higgs production directly and TTH production. And the other big difference is, of course, that you can have longitudinal beam polarization for physics measurements, and in case of the ILC, both beams are foreseen to be depolarized. So this is really a rather unique feature of linear colliders, as you can see here. The key is, of course, that electroweak interactions are really highly sensitive to the chirality of the colliding fermions due to the subscript L of the SU2, as you all know. So with both beams polarized, this means that basically the ILC is in this respect 4 colliders at one, because you get not only electron and positron collisions, but you get right-handed on right-handed, left-handed on left-handed, right on left, and left on right. So why do we want to do this? Well, there are 4 categories of reasons for that. The more trivial ones are on the top. You can suppress backgrounds, you can enhance signals, but I will give you also during the talk examples of the more interesting features, namely that you can use this to analyze the chiral structure, both of standard model processes and if you find them, of course, also for BSM. And it actually also introduces redundancy and control of systematics, in particular if the machine is designed like the ILC to provide a flipping of the beam helicity, which is much faster than any typical drift or so of your detector calibration, alignment, and what have you. So starting not with the Higgs, because Ivanka told us already a lot about the Higgs at linear colliders, but what we can learn about our old friends, starting with the most basic thing which one can do, namely difermion production at the Z-pole. And again here highlighting what is different between polarized and unpolarized collisions, namely that you gain direct access to an additional quantity, namely the left-right asymmetry of the total cross-section, which gives you directly basically the couplings of the Z to the electrons, and you can separate them from the fermion asymmetry. So this is a clear example for the chiral analysis part. But then, of course, this is all tree level, and of course, we all know that real life is not a tree level. But if you calculate the radiative corrections to these, you realize that actually this polarized forward-backward left-right asymmetry receives 7 times smaller radiative corrections than the unpolarized forward-backward asymmetry. So this is an example where you trade a theory and certainty basically for polarization. And then, of course, if you go do the same process at higher energies above the Z-pole, then you don't have only 2 couplings here, but you have 4, because you have to take the photon and the Z-gamma interference into account. So then you really need beam polarization to disentangle really these four couplings in fermion anti-fermion production. So what does this give you? Rather recently, this was studied in some detail by ILD. And this plot shows you some of the important standard model parameters, with in blue the lab and SLC precision, which is what we know currently, and in red what you get if you operate the ILC at the Z-pole, which is only about a giga-Z, a bit more, but about a giga-Z, not a tera-Z. And I would like to highlight here in particular the charm asymmetry, which is nearly 100 times better than it was done at lab. And actually, if you look at how this, what is behind this, this is actually, again, a special linear collider feature, because at linear colliders, the beam spot is much, much smaller in order to achieve a high luminosity in one shot. And this means you can, you know the beam spot very well, and you also can move the vortex detector very close. And what is also special here in case of ILD, you really use here the K1 identification via its specific energy loss in ILD's time projection chamber. Then, of course, you can also look at, again, what polarization gives you. So the gray bars show projection from an unpolarized TerraZ. And of course, 1,000 times more Z's gives you, of course, somewhat better precision, but it's typically only a factor 2 to 3. So this means that at the end of the day, the fact that the GigaZ is polarized buys you a factor of 100 in luminosity, roundabout, if you go through the math. Okay, but then what happens at higher energies? Moving to the 250 GeV stage, here one example from the bottom quark. You all know about this long-standing discrepancy between SLD and lab measurements. And one can speculate a lot whether this is new physics or just a mismeasurement. And yeah, so this is highly interesting to remeasure this. And yeah, this has been studied, that in particular, this coupling of the Z to the right-handed bottom quark here, this can really be improved by nearly an order of magnitude, and would definitely resolve this puzzle. And as I showed you in case of the Z-pole already, of course, this also works in principle on the charm. We also expect an even larger improvement. And these kind of numbers then would, just to add a house number, would probe new physics up to 60 TeV. Okay, so then we can go to even higher energies, namely to the 500 GeV stage, where one can produce TT bar pairs. So of course, you can do this already at 360 GeV, but then you have nearly no boost in your tops, which limits the sensitivity to the axial couplings, which are of course proportional to the, or whose effect is proportional to the momentum. So this is something which you can see here in this projection of the CP conserving TT bar form factors. In red is LAP and LHC combined, and the blue bars is the 500 GeV stage of the ILC compared to doing these measurements at threshold. And you see here clearly, while for most of them they are rather similar, for, as I said here, for the axial coupling, you really see important difference due to the higher energy. Then, of course, clearly these measurements can only be done really if you have the beam polarization to disentangle the Z and gamma exchange. So really to reach this level of a per mil precision roundabout for all the couplings really requires both the high energy and the polarization. And again, if you want to translate this into your favorite BSM model, this typically reaches also in the multi-10 TeV regime. You can then do the same game with CP violating form factors, and again you see that being significantly above the TT bar threshold helps you a lot on these couplings. Note that here now the green is click and not a circular collider. Then, of course, you can also interpret all this in full standard model effective field theory. I spare you the plot because it has even more Manhattan bars. But what one sees on these is that 500 GeV improves many of the coefficients by 2 orders of magnitude. And of course, especially the 4 fermion operators profit quadratically from the higher energies. So this you can also see here. You can, of course, also for these 4 fermion operators define something equivalent or similar to the S and T parameters, which you know from the Z pole. So called then Y and W. And again, what you can see here is that already ILC 250 outperforms the Halumi LHC. These are these two lines. And also, if you compare then in the line below 500 GeV with the 500 GeV without polarization, you see that the correlation gets significantly reduced by the polarization, which then of course also reflects into the individual uncertainties here. Yeah, I can of course not completely ignore the Higgs, although of course I refer you a lot to Ivanka's talk. So just very quickly, we can of course use Higgs coupling measurements to fingerprint whatever BSM model might be out there realized by nature. See here a few examples with all having different patterns. If you work through the math, you typically end up with a few percent deviations from the standard model, which you expect in the Higgs coupling. So this means you need at least percent level precision on any of these couplings. I think I can again be very brief here because Manchi explained this very beautifully. Of course, the key really is to add 250 GeV at the peak of the Higgs-Strahlungs cross-section to use this this recoil method to get an absolute normalization of all your of the total cross-section and thus all your couplings, which then enables the minimal model-dependent measurement of all the couplings. And I, of course, also refer you to Daniel's talk later today about the CP measurements in Higgs to tau-tau. So let me again only point out where polarization comes in here. And that is namely that the left-right asymmetry of this Higgs-Strahlungs process is actually very important to disentangle different SMEFT operators. So for the Higgs-Strahlung, we have in the standard model this diagram, but in full SMEFT, you can add two more. One of them is very tightly constrained by electroweak precision observables even today. So these are the two main guys which need to be disentangled, and actually they have an opposite behavior under spin reversal of the incoming electron. So the standard model flips its sign and the other diagram keeps its sign. So this means if you measure the left-right asymmetry, this lifts the degeneracy between these operators. And this then reflects in the observation which we did a couple of years ago, namely that despite the somewhat different integrated luminosities, actually all the Higgs factories come up with more or less the same level of precision on these couplings. So in red, you see what you get with Halumi LHC and 5 inverse autobahn of unpolarized 250 GeV running, and in green is 2 inverse autobahn polarized, and you see some are better in one and some are better in the other, but overall they have a very similar behavior. Then again, if you add 500 GeV here and you get down to the blue, so this is typically another factor of 2. So takeaway message is that 2 inverse autobahn polarized are the same as 5 inverse autobahn unpolarized for Higgs physics, and adding 250 GeV improves a factor of 2. Let me then comment a bit on the Higgs self-coupling, which is of course something where one needs at least something like 500 GeV to produce 2 Higgses. So this has of course been studied a lot for the European strategy for all kinds of colliders. It's very challenging to do at high luminosity LHC. For E+, E-, we know at least we have a very clear observation of double Higgs production. And at the highest energy stages can get down to the somewhat 10% level in full simulation, noting that the fast simulation was 3 times better originally. for FCCHH, there are also a few percent level predictions only from past simulation and single parameter extraction. However, whatever you think of those, all these apply only if the Higgs self-coupling really has its standard model predicted value. And one important notice is that for all hadron colliders, the cross-section drops if the self-coupling is larger than in the standard model. So this means if you take, for instance, the high luminosity LHC projection and fold in how this would change for different values of lambdas, you're reaching up to 2 times and going down to half the standard model, you see that in particular on this side, error bars grow. And actually, this is, of course, the region of interest if you want to, for instance, verify something like electroweak baryogenesis or so. In green, you see what happens to the 500 GeV ILC number, where there is a completely different dependence of the cross-section on the coupling, and you see actually that they really get actually more precise. You can then, of course, also add the 1 TeV stage, and you see that you then shrink mostly on the other side here for smaller couplings. So this means that the combination of double Higgs Strahlung and double Higgs and double Higgs production from fusion really ensures an at least 10 to 15% precision for any value of lambda. So I think that is really important to realize. Of course, then you can also do the top Yukawa coupling, and this is actually something, a very good reason why one should revisit whether 500 GeV should really be the energy of the second stage, or whether 550 or 600 wouldn't be better, because you are really, with the Higgs mass as it turned out to be, you are really still in this steep cross-section rise and actually should sit a bit higher in the energy. So this is something which will probably in due time be considered. Yeah, maybe a few brief words, if I may, on direct discoveries, because many people think, well, 250, this is only marginally more than the 209, which we have seen at Lab 2. So can we at all expect to see anything new? Isn't it all covered by LHC? And well, I think as we are talking here about something like a factor 1,000 higher integrated luminosity, we have the polarized beams, which especially for searches suppress some of the important standard model backgrounds by 1 to 2 orders of magnitude. And last but not least, we see tremendous advances, of course, in detector technology with much better momentum resolution, vertexing, very high calorimeter, granular calorimeters, better hermeticity, and so on and so forth. So some examples on purpose, choosing some complementary to what we saw from the TerraSat. For instance, searches for additional light Higgs bosons with reduced couplings to the Z, and of course, SUSY particles without color. So all the electroweak SUSY particles can also do things like stereo neutrinos, and of course I will show you something about generic WIMP searches. So, but at the end of the day, any search channel which was limited by rate at Lab 2 will really explore new territory at ILC 250 already. So here, this is an example from ILC 250. You can use the same recoil method, which is used for the total Higgs Strahlungs cross-section measurement. You can really use this also to search for new peaks. And this is, of course, a sort of a toy thing where one, just for illustration, many of these peaks are put in. But I mean, you see here in green the Z, you see in green the standard or the Higgs boson, which we know, but maybe one of these other peaks could pop up as well. So this has been studied in full simulation, and this is actually what one finds. So exactly the same search was done at Lab by the Opal experiment. This is this blue thingy here in terms of mixing angle and mass, and the red thing is where ILC 50 would bring you down, so everything above the curves is excluded. You actually see here that there are some parts where one should think about the detector or the reconstruction still to get where one could theoretically sit in terms of sensitivity. Some examples from electroweak new particles. So there are actually many reasons to which point us to the fact that there could be small mass differences involved, which make things very difficult for hadron colliders, and where it comes really handy in that you can operate linear colliders in triggerless modes. So this means, one can basically, for all of these, cover basically up to the kinematic limit of the machine, here drawn for the 500 GeV ILC, where you see that even today, there are many regions where there is actually still today no improvement above the lab limit, which is this light cyan on the left. Similarly, for slapdowns, for instance, where there are many regions where there is nothing above lab which is probed, and even the existing limits often assume that all slapdowns would have the same mass, which is of course not an idea which is realized in any realistic model. And similar also here in this case, for the stows, you see only very small slivers up here and down there are probed for low delta M stows. All this area here would only be covered by a high energy plus E minus machine. And finally, again, one part on dark matter and the polarization. So very famous channel to look for dark matter is just the production of one photon recoiling against something invisible, with the main background, of course, coming from standard model neutrino production. And actually, these diagrams here are strongly reduced with polarization. As you can also see here, black is unpolarized and the others are various polarized configurations. And also the shape of this distribution changes with the polarization sign, as you can, for instance, see here between these colors. So this means that actually a combination of samples with the different polarization signs, remember the 4 colliders in one, really beats down the effect of systematic uncertainties. So this you see here, this is in this time now higher is better. So this is probe new physics scale, not precision. So you can see here that that you can, even with 10 inverse autobarn unpolarized, you do not get any better than 2 inverse autobarn polarized give you. But of course, energy does really help a lot for these cases. And this, of course, extends. So as a guiding over to, sorry, this was too fast. Oh, no. To Aidan's talk, right? So of course, if you think about 3 TeV at click, this really brings you to probe 10 TeV new physics scales. Yeah, this brings me to the end of my talk. So I think there is a clear and significant physics case for E plus E minus collisions at 250 GeV, but also at 500 GeV and above. And this is really complementary to proton collision. And therefore, the next E plus E minus collider should be energy upgradable with both click and ILC fulfilling this criterion. So the exact physical or operational energy stages beyond an initial Higgs factory mode can then, in case of a linear collider, still be defined, taking into account then the physics needs after what one has learned from a 250 GeV run, and of course also technological innovations. So if you want to get involved, there's still a lot of interesting things to do, both on the physics and on the detectors, and I just put you here some links where you can find information, and I'll leave you with this nice little movie to ask some questions if you have any.
Thank you very much, Jenny, for this very interesting talk. We are still, well, pretty much in time, so there is a room for a question or two. Are there any questions to Jenny? I see no hands, but I have one question, letting people some time to maybe ask their questions. So we know already from the detailed simulation that Higgs performance between linear and circular machines will be comparable up to the Higgs self-coupling measurement, of course. Can we conclude from your talk that linear collider could offer the same when it comes to electroweak precision observables? Can we say that the
exactly right? I mean, as I told you, if you really talk about the Z pole, yeah, and of course you have to distinguish between things which actually care about the couplings of the Z itself, right? Because then, as I told you, it depends whether you call a factor 2 or 3 the same or not, right? But it's at least not as a big factor as you would expect, right? Between if you just hear giga and tera, you would expect a larger precision than a factor 2 or 3, right? So clearly, if you are looking for things like B physics, right, where you don't care about the initial polarization, but you just want a huge number of whatever B sub S is produced, then of course you see the full difference between giga and tera. Yeah, but that's not so if you really talk electroweak in the sense of couplings of the Z and the W, yes, then I would say in principle, yeah, they are rather comparable, but obviously not in the full TeraZ program, including flavor or what have you.
Thanks, Jenny.
Can I make a little comment?
Of course.
Yes. Okay. This is true. For the quantities that are shown here, which are mostly left-right asymmetries of couplings. If you look at partial width, then it's clear that the statistics really is important for the determination of the partial width of the Z into electrons, muons, taus, etc. Also, I warned you about the systematics that we give on the FCCE so far. These are just first estimates. I believe they will go down by another, at least order of magnitude.
Let me reformulate my question, referring to a talk that was once held at CERN by a theorist, I don't remember his name anymore, concerning the Higgs mass. So you can measure something at a precision level, but do you really need it? What is your sensitivity to beyond the standard model scale? For instance, we learn that we actually, for instance, for the vacuum stability with tens of MeV, which are achievable at future plus or minus machines, it is far beyond what is needed to say at which point we are. So how about precision electroweak? What is that clear gain in our understanding that could be provided by circular machine? And let me then, or linear, maybe both Jenny and Alan could answer.
Well, I mean, I think first of all, it's completely wrong to say that we do not need to measure the Higgs mass with great precision, because the Higgs mass, of course, goes directly into the standard model predictions of the partial width of Higgs decays to ZZ star and WW star because of the star, right? This is highly sensitive to the exact value of the Higgs mass. So if you want, if you want then to compare any measurements of these decays to any sort of predictions, you really need the type, the type of precision which you get on the Higgs mass. So don't let you be fooled by theorists that you doesn't need to know the Higgs mass precisely, right?
Yeah, for us, it's if you want to do the E plus E minus to Higgs direct measurement, then we need to know the Higgs mass better than to a precision that is smaller than the Higgs width.
Yes.
Okay, so that's 2 to 4 MeV.
Yes, clearly.
We have enough statistics to do that. It's not, I don't think that's a problem. The problem is really to get the beams to have a small energy spread. So we have a challenge there, but it's not about the Higgs mass itself. The more important quantity for precision measurements is the top quark mass. That has bigger effect. It's the electroweak measurements have a quadratic dependence on the top mass. So it's very important to know the top mass precisely. But you know, as soon as you go play the game of precision, everything matters. So you have to attack the problem by all aspects and get it through. And we are only at the beginning, and I'm not claiming that we know for sure we'll get these errors down, but we will. I'm pretty sure those smart guys, when it comes to it in 20 years from now, they will have figured it out.
Thank you. Thank you both. Actually, of course, my point was not that we do not need to know Higgs mass precisely, but it was rather a general question. Are we aiming towards infinite precision, or we may say that for certain understanding, there are limits that are acceptable. But let us stop at this point now and switch to our another speaker, again from ILC, but for a very good reason, because he is going to present actually the superior measurement of the CP violating effects that may took place in the Higgs mixing. This is Daniel Jeans, and he's sharing his slides with us. Thank you, Daniel, and please go to the full screen mode. The floor is yours. Daniel, I cannot hear you. I don't know if other people can hear you.
No.
No, well, we are trying to, probably the microphone is switched off.
Yes, my microphone is switched off. Can you hear me now?
Now,
yes,
okay,
yes.
Okay, sorry, this was my local problem. Okay, my talk will be much less general than previous talks. In this session, I'll talk about the particular analysis where we looked at how well we can measure CP effects in the decays of the Higgs boson to tau leptons. So, okay, we already heard that the electron-positron Higgs factory is a wonderful opportunity to look for new physics, particularly in the Higgs sector. So I won't belabor this point. This study I'll talk about now is maybe quite general, can be carried out at probably any electron-positron Higgs factory. However, it was in this particular case specifically done in the framework of the ILC, which you heard about in the previous talk. So I again won't mention it so much. And even more specifically, it was studied in the context of the so-called ILD detector concept, the so-called International Large Detector, which is one of the two detector concepts being developed for ILC. So this is shown on this picture here. So at the very center, we of course have the collision point surrounded by a very precise and low mass vertex detector, giving an impact parameter resolution of a few microns, and a large low mass tracking system, mostly consisting of a time projection chamber, plus some additional silicon layers, giving a momentum resolution, relative momentum resolution of a few times 10 to the minus 5, and surrounded by highly segmented calorimeters, which will give us a jet energy resolution of a few %. We also have almost full coverage around the interaction point, and everything is sitting in a magnetic field of 3.5 Tesla. So let's move on to this particular study. So as we know, and as we've heard several times in this conference, the sources of CP violation we know about today are insufficient to explain electroweak baryogenesis. So this motivates us to look for how we can, motivates us to search for effects of CP violation in the Higgs sector. We can maybe think of this in two probably related ways. And we can ask, is this 125 GeV Higgs we've seen, is this an eigenstate of CP, or is it some mixture of CP even and CP odd states via some mixing angle I call psi CP? Or maybe do these Higgs couplings to fermions conserve CP, or do they perhaps explicitly break CP symmetry? So we can write down the Lagrangian term in this way, where we include this I gamma 5 term, which would violate CP. Again, parameterized in terms of this mixing angle psi CP. So in this talk, I will discuss looking at the couplings to fermions. Of course, one can also look at the CP nature of the couplings to gauge bosons, but I won't cover that in this talk. I believe there was a talk earlier in this conference on that subject. So in fact, a couple of days ago on Friday, there was a very nice talk by Dr. Pokorski from Warsaw, where he made exactly the point that if we want to see if electroweak baryogenesis can be successfully explained, then it's really essential to look for CP violation in this decay of the Higgs to taus. And this is maybe the only window remaining which could explain electroweak baryogenesis. So this is very nice to have this extra motivation in this talk, earlier in this conference. So how can we do this at ILC or at E plus E minus colliders? So to probe CP of the Higgs, we have to think about the correlation between the spins of the fermions produced in the decay of the Higgs bosons. So we need to find some fermionic decay of the Higgs in which we can reconstruct the orientation of the fermion spins. So the decay to tau leptons is one of the most suitable for this. It has a relatively large branching ratio for the Higgs, around 6%. And maybe more importantly, we have this sensitivity to the orientation of the tau spins, thanks to the fact that the taus decay rather quickly, and that the orientation of the decay products of the tau reflects the orientation of the tau lepton spin. So let's go in a little bit more detail. So as I said, we can use these decay products of the tau to reconstruct what we call a polarimeter. So this is an estimator of the orientation of the tau spin. And this is in some decay modes of the tau, this is really rather straightforward to extract. In particular, the decay of the tau to a single pion neutrino, around 11% branching ratio. And then this 2-pion decay, pi plus pi 0 neutrino decay, which makes up around 1/4 of tau decays. So for these tau decays, which we've concentrated on here, it's rather easy to extract these polarimeters. Now, how can we, once we have the polarimeters for these two taus, we have to look at their correlation. So we look at this cartoon here on the left top picture here. We are in the Higgs rest frame. We have the tau plus and the tau minus, and then this red and blue arrows are the polarimeter vectors we've extracted from the tau decay products. So these are then characterized by these two polar angles, theta plus and theta minus. Then on the bottom, we look at which is the view of this top picture. When we look from A to B, we can look at these azimuthal angles, phi plus and phi minus. And in fact, if we look at the difference between these two azimuthal angles, phi plus minus phi minus, we can get this distribution on the right-hand side. Okay, if we look at, maybe first we should look at this little equation at the bottom, where we look at the distribution of events in terms of this theta plus and theta minus, and this delta phi observable, this green one here. So we have this cosine delta phi minus twice this CP mixing angle, which is the angle we want to extract from this analysis. This is then modified by a factor which depends on theta plus and theta minus. So let's go back to this plot on the right-hand side. Here we see three curves on this, showing the distribution of events in this delta phi observable. The CP even case is a black curve, which you see is a nicely modulated curve with its minimum at the delta phi equals 0. If we have, that's for a pure CP even state. If we have a pure CP odd state, we get the blue curve, which is just flipped or shifted by pi. And if we have some mixed state, for example, this red case, where we have a mixing angle of pi over 8, we see there's some shift of this sinusoidal modulation. So the idea of this analysis is to reconstruct this delta phi observable and to measure the phase of this modulation, which will then allow us to extract this CP mixing angle. So for the optimal, to get the optimal polarimeter vectors, I give you for reference here the forms. So if we are working in the tau rest frames, then you can see we can express these polarimeters in terms of the momenta and energies of the pions and potentially also of the neutrino. So the point here is, in order to get this optimal sensitivity to the polarization, we need to know the exact rest frame of the tau, or equivalently, we need to reconstruct the momentum of the neutrinos. So, okay, so how have we done this analysis? So as I said, we are trying to reconstruct this distribution here. We are using a full GEONT 4-based simulation of the ILD detector I talked about before, together with realistic reconstruction of this simulated data. The signal, we're looking at this Higgs-Stralung process we already talked about several times in the previous talks, where we produce Higgs associated with the Z boson. We look at the cases where the Z decays either to electrons, muons, or quarks. And of course, where the Higgs decays to a pair of tau leptons, which decay into one of these two decay modes I talked about a couple of slides ago. We consider a full set of backgrounds, so either other processes where we produce a Higgs boson, other for fermion processes, or also two fermion processes, which provide large sources of standard model backgrounds. And we assume this canonical two inverse autobands of data collected at 250 GeV. So this is the first stage of ILC, around 11 years of ILC operation. So a few slides ago, I told us we need to know the tau rest frames exactly, or in other words, we need to reconstruct the tau neutrinos, the momentum of the tau neutrinos. So this we can do. So in our events, if we have this sort of event here, we have two neutrinos from the taus which are unobserved. So we have 6 unknown quantities in the event. But thanks to the properties of electron-positron collisions and also of a very good vertex detector, we have enough information to solve for these 6 unknowns by considering the visible tau momenta, by the production vertex of the taus, and also the impact parameters of the charged tau decay products are also important. So this is possible to do this theoretically. In order to do it experimentally, we of course need an excellent detector. Particularly, we need very good charged particle and photon reconstruction. And one of the most key aspects is the measurement of the impact parameter of the tau decay products, and also of the energy of hadronic jets. This I just flash a few plots of how these events look after some simple pre-selection at this full simulation level. Here we see these blue areas of the signal we are after in various of the different subchannels we look at, and you can see they are very much dominated by these various different gray backgrounds. So we can use these to make these sort of observables to make a more stringent selection, and the number of events we expect to see after these 10 or 11 years of running summarized in this table here. So the 3 columns we see here for the different decays of the Z boson, either to electrons, muons, or quarks. So we can see our signal, which we are after. we get maybe 30 or 36 events in the electron and muon channels, and much more in the hadronic channels, thanks to the large branching ratio of the Z to hadrons, of course. We also tabulate the various different background processes we have. We can see that in these leptonic channels, we have maybe a signal to background typically of around 1 to 5, and much worse in the case of the hadronic channel. It's just some distributions. I can maybe skip this in the interest of time. One important thing to extract these polarimeters, I showed you the form a few slides ago, is that we must identify the decay mode of the tau. The form of the polarimeter is different if the tau decays into 1 or 2 pions. So in this analysis, we implemented a rather simple selection just based on the number of photons and the invariant masses of them, and together with the charged particles in the tau jet, to separate the different decay modes of the tau pairs we have in the event. So the sort of migration table is shown here. So we can see that in this top table, in the case of Z decays to muons, we get a correct identification of the tau decay modes in around 93% of events. Where the Z decays to hadrons, it's slightly more complicated. It's have a lot more activity in the events, but we still have a correct identification efficiency of around 90 or 85%. We have some additional steps to group events according to the expected sensitivity to the CP effects. This could be intrinsic to do with the orientation of the polarimeters, how well we think we've reconstructed the events. This is particularly to do with how long the tau flew in the detector before decaying, how much background we think we have, and whether we think we've got this tau decay modes identified correctly. Then we can split up the events into various different categories. Here we split into 4 different categories. Here the gold medal category is the cleanest category. Here in red we can see the distribution we expect to see from the signal with a background. All these backgrounds I talked about before in this blue distribution. So here in this category, while the number of events we expect is not enormous, we can see a very clear modulation sitting on top of a rather small background. The silver medal position, the modulation is a little bit smaller, the background is higher, but still we can have some sensitivity. Bronze medal down here, probably we can still get a little bit of sensitivity, but not so much. And finally, the rest, we are completely background dominated, and this is not so useful. But using these top 3 categories, we try to estimate how well we can extract this CP phase. I remind you, this is the phase of this red sinusoidal distribution we see here. So to do this, we do an unbid maximum likelihood fit, where we simultaneously fit several of these distributions. To test everything is going well and to estimate the sensitivity, we run a number of toy pseudo experiments using the simulated distributions. And we get plots like this, where we show the uncertainty coming from this maximum likelihood fit, and the fitted phase here on the top, showing us that we don't have a significant bias in this measurement, and that our estimated uncertainties are reasonable in this pool distribution. So what are the results? So this table on the left summarizes the sensitivities which are achievable in this analysis. So the top part of this table assumes a canonical 1 inverse autobahn of data, and usually no beam polarization. So this could be applied, for example, quite accurately, I guess, to a circular E plus E minus machine. If we do the full analysis, we can see an uncertainty on this CP mixing angle around 160 milliradians. And we can see how this is distributed amongst the different Z decay modes here, showing that the hadronic decays of the Z are dominating the sensitivity. So this sort of underlines that we need to reconstruct these hadronic final states very well in order to make use of this of these data in an optimal way. We can also split it up according to the different tau decay modes here, where again the statistics wins, and we can also look at this bottom, this line I'm pointing to now is what happens if we ignore, or if we assume we can remove all the standard model background and have perfect efficiency and perfect reconstruction of the polarimeters. Then we can go from this 116 milliradians down to 25 milliradians. So there are many, many different experimental effects which further work could, I think, get significant improvements to the projections I showed today. So this was all for one inverse autobahn, usually unpolarized. In the bottom part of the table, I show what is our current ILC 250 scenario would look like. We have two inverse autobahns split amongst these four different colliders, as Jenny said in the previous talk, with the different beam polarizations, where we can expect, after a full combination, of around 75 milliradians precision on the CP mix. So, okay, that's the end. So, precision Higgs, studies of the Higgs, are of course of great interest in our task, or in our task to look for physics beyond the standard model. And CP properties of the Higgs are one important aspect of this, particularly when we are thinking of electroweak baryogenesis, for example. Electron-positron colliders are really an ideal tool to do this. And in this analysis, we studied the prospects for measuring CP violation and the Yukawa coupling using the ILC and ILD setups. And we can measure this mixing between even and odd components of the Higgs, or in the Higgs couplings, to a precision of a few degrees, maybe around 4 degrees. I suspect that with more work, this can be significantly improved to, or maybe, I don't know, 1 degree or close to 1 degree or something like this. Okay, thank you for your attention.
Thank you very much, Daniel, for this interesting talk. Do we have any questions for Daniel? It seems that we do not.
I have a question, Ivanka.
Go ahead, please.
Hello. Hello, Daniel, that was really very nice. Can you show back to slide 19?
Yes, I can try. Yes.
Okay, my understanding is that the longitudinal polarization doesn't help that much for this, does it?
Here, I think a longitudinal polarization does not help very much. Of course, some of our data will have a slightly higher. If you selected the polarization to minimize backgrounds and emphasize the signal, then it would help a little bit. But since we have this mix of different things, it doesn't help. I think here the main thing which is important is just number of Higgses we have, yes.
And the quality of the detector for taus.
Of course, of course.
Yeah, yeah. Okay. Now that's a very good point. Well, book yourself for a talk to the FCCE meeting.
I wait for the invitation. Yes.
Okay.
That's the best, when the conference is apparently a field for new friendships.
That's right.
Thank you, Daniel, once again. And now we are moving to the last talk of Aidan Robson from CLIC, being the ultimate highest energy linear collider that we have on the market. So Aidan, please go ahead.
Super. Thanks very much, Ivanka. Can you hear me and can you see my slides okay?
Yeah, it's all good.
Okay, great. And I'm not quite sure how great my bandwidth is, so perhaps I'll just switch the video off while I'm talking. Okay, well, thanks very much to the organizers for including this Future Collider session and for the invitation, and to the previous speakers, Manchi, Elena, Jenny, and Daniel, for doing a lot of the scene setting. It's a pleasure to talk about the Compact Linear Collider, CLIC. I'd like to give you just a short overview of the project and then a little bit of its status after the European strategy, just to give you the context for the ongoing work, and then try to spend most of the time talking about the physics reach. And I'm talking on behalf of a large community approaching 100 institutes across the accelerator and the detector and physics collaborations. And we're very glad to have collaborators participating from Russian institutes, from Jüner, from the Budker Institute, and from the Institute of Applied Physics. So at the highest level overview, the Compact Linear Collider is a high luminosity multi-TeV electron-positron collider. We have a site identified. It's planned for construction at CERN in 3 energy stages in a region where the geological conditions are very well known. So it extends from an initial phase at 380 GeV and about 11.4 kilometers in length, up to a final third stage of 3 TeV and 50 kilometers in length. And so at that initial stage of 380 GeV, the focus is on precision Higgs boson and top quark physics. And then at the higher energies, we expand the Higgs and the top studies, including sensitivity to the Higgs self-coupling, and of course, opening higher sensitivity, both directly and indirectly, to BSM effects. So the nominal physics program lasts for 25 or 30 years, but of course the manifest benefit of a linear machine is that the length and the energy staging plan can be updated, so it would be approvable in stages, and plans could change in response to the developing physics landscape. So CLIC has been going for quite a long time. Conceptual design report in 2012, an updated staging baseline in 2016, and then the big effort of 4 CERN yellow reports as inputs to the European strategy in 2018. So CLIC's really a mature project now, and going into the European strategy, we gave a technical timeline of construction readiness in about 2026, with first collisions in 2035. And I'll say a little bit about the changes after the European strategy just in a minute. So here's the principle of the machine. CLIC uses high gradient room temperature structures to construct a relatively compact accelerator that reaches very high energies. The radio frequency power for the main LINAC is provided by a high current, low energy drive beam that runs parallel to the colliding beams. And so the drive beams generated in a central complex, and through passing through delay loops and combiner rings and interleaving pulses, you end up with a beam that's at high frequencies of 12 gigahertz. So then the drive beam passes through resonant structures like this one here, and is decelerated. It generates RF power that's then transferred to the accelerating structures by waveguides. And throughout this accelerating chain, the beams are kept very small, the emittance is kept very small, so that the beams have dimensions of about 3 by 149 nanometers at the interaction point. And so as I said, this is a staged proposal, and what I'm showing here is the layout for 380 GeV. This layout gets up to up to 1.5 TeV just by adding length, but then to go beyond 1.5 TeV, we need to add a second drive beam complex that you see there. So briefly on the accelerator challenges, there were 3 main technical challenges that had to be demonstrated. First of all, producing this high current drive beam at 12 gigahertz, and stabilizing the drive beam arrival to 50 femtoseconds that's needed for the synchronicity of the machine. And that's what you see demonstrated here from the CTF3 facility that's now running as clear at CERN. To demonstrate the extraction of the RF power from the drive beam and the 2-beam acceleration scheme, and we were able to do that at CTF3, to be able to maintain the very high accelerating gradients in the main beam cavities. So we need about 100 megavolts per meter, and that's been achieved in many different structures now from different sources across the world. And also demonstrating many aspects of the monitoring and the stabilization that's needed for this machine. So altogether, the key technologies have been demonstrated now. And so as I think everyone knows, the European strategy for particle physics was updated in June last year after a process that went on for a few years. And an electron-positron Higgs factory is prioritized as the next collider. That's why we're here in this session. The strategy also articulates the ambition to operate a proton-proton machine at the highest possible energy and mandates a technical and financial feasibility study for that. But alongside that, as Alain was saying, the strategy mandates intensified accelerator R&D, and that includes on the high gradient structures for CLIC. So over the next 5 years, CERN is going to continue the investment in R&D for the key CLIC technologies so that CLIC is maintained. And if the next strategy update in 2026, the feasibility study doesn't converge for FCC, then CLIC could be implemented quickly. And that timescale would be for a project approval in 2028 and tunnel construction starting in about 2030. So CLIC is consistent with the European strategy. It's the least expensive Higgs factory proposed for construction in Europe. And then it leads to a really unique physics potential with its potential for high energy running. So over the next few years, the accelerator development will proceed in several different directions. First on the X-band technology, on manufacturing and studying the structures. Second, on the technical and experimental studies for the machine, so including beam dynamics and beam tests. And then also separately on applications, other applications of the X-band technology from CLIC. And just to give you a few examples from the news recently, this X-band accelerating technology is finding uses in medical applications. There are a couple of news releases that you see here from last year announcing the new collaboration with Lausanne University Hospital on a new electron radiotherapy facility, and a more recent release from a few months ago with just developing the understanding of how our very small electron beams interact in matter in human tissue like samples. And so it's great for the project. I think that there are these other applications that are interested and can help to bring the X-band technology to industrialization. Okay, so on to the physics. And so you see here the interesting physics processes across the 3 TeV reach of CLIC. And what you see is that, of course, different processes dominate at different energies. So you have threshold turn-ons for some processes which decrease with increasing energy, and processes which are growing with increasing energy. And so I think it's clear that this landscape is best explored in several energy stages. And so that's why we have this staged approach that I talked about, 380 TeV, 1.5, and then 3 TeV. We intend to collect about 1 inverse atabarn at the first stage, and then 2.5 and 5 inverse atabarns at the later stages. And the CLIC baseline gives plus or minus 80% electron beam polarization, and we benefit from that in a number of studies. So to go along with the accelerator, we have a well-developed detector concept, which grew from the ILC detector concepts, ILD and SID, but optimized for the slightly different CLIC environment. So there's a 4 Tesla coil, 3 double layers of vertex detector, a 1.5 meter radiance, all silicon tracking system, and then very finely segmented imaging calorimeters. And there are some very particular environmental considerations for the CLIC detector, in particular, the very short bunch crossings, so half a nanosecond apart, which means that we need around about 10 nanosecond time stamping for the hits in the tracker, and 1 nanosecond accuracy for the calorimeter hits. So in particular towards that, we've had a dedicated detector R&D program, particularly on vertex and tracking. And we've had success developing sensors specifically for CLIC. So thin sensors giving good efficiency, and reducing the detector mass. Interesting results from integration technologies, and also going along with that, advanced simulation and analysis tools, which are being picked up by other users. So Understanding Higgs physics in a detailed way is clearly one of the highest priorities in particle physics. So to understand whether this particle is the fundamental scalar of the standard model or a more complex object, part of an extended Higgs sector. And so we've studied many different channels at CLIC at all three energy stages. And this is done in full JONT-based simulation with full beam backgrounds included. And from this, I just really want you to take the number of channels that we've studied. So on the left here, we've got the initial energy stage. And what you see here is that at 380 GeV, there's already a significant contribution from the vector boson fusion production mode of the Higgs, as well as the Higgs Strahlung. And that's really helpful because it helps to disentangle the couplings. And then here we have the higher energy stages. Different BSM scenarios result in different patterns of modifications to the Higgs couplings from their standard model values. And so as I think Jenny already said, for new physics at the TeV scale, it's typically at the percent level. And so that's the target for precision Higgs couplings. And so I'm showing you an example of the sorts of sensitivities that we could expect for the Higgs couplings here. And in this red box are two CLIC scenarios. On the right-hand side, we have the baseline, which is 1 inverse atabarn at the initial energy stage, followed by the second energy stage. However, if for some reason the second energy stage didn't go ahead, then of course we would run the first energy stage for longer. And we've done studies that show we could actually get more luminosity by doubling the bunch train repetition rate. So for a slightly modest time at the initial energy stage, so 13 years instead of 8, we could have, under that scenario, 4 inverse atabarns. And so what you see if you compare these scenarios with the HLLHC and with the FCCEE predictions is that really all of these options give rather similar Higgs performance. They're all very competitive. And I think any of the options we've been talking about already in this session would be a super Higgs factory to have. And so what I want to go on to do is to look then at beyond the Higgs factory physics, what's unique to CLIC. Now, of course, we're particularly interested in the Higgs self-coupling, and high energy running gives direct access to that. So at the two processes, this double Higgs Strahlung process and the vector boson fusion process here. So they're complementary at the lower energy stage at 1.5 TeV, and we could have evidence for both of those production modes at 1.5 TeV, and then at 3 TeV we would see an observation of the vector boson fusion mode. So these are for just the rate only analyses, but then when you also add differential distributions, you get these final sensitivities of the order of 10% sensitivity to the Higgs self-coupling from the full CLIC program. And we recently confirmed some of our earlier fast simulation extractions for the fully hadronic ZHH mode through full simulation, and that's gone into this fairly recent publication. Processes involving the top quark provide unique opportunities to test the the standard model, and to probe signatures of beyond standard model effects. And so far, the top quarks produced only in hadron colliders. So the study of the production and properties in E plus E minus should provide a new set of complementary and improved measurements. And CLIC's the only proposed E plus E minus collider to include top quark physics already at the initial stage. So as well as the initial run at 380 GeV, we're intending to do a threshold scan around 350 GeV. And so the baseline would be to take around 10 points separated by a GeV over a year. But some recent work has been done to optimize the spacing of these points, and that's what you see here. So this uses a genetic algorithm, and you can optimize against the mass, the width, and the Yukawa coupling sensitivity. So what we're seeing here is the optimum separation for the mass and the width. And this is a really nice study that shows a 25% increase in the mass sensitivity from the 25 MeV baseline. And I'll give you the paper there. There are lots of other things that we can look at. We can look for flavor changing neutral current effects. We can look at the CP properties. We can measure the cross sections and forward backward asymmetries, all energies, and then put all of that together to understand all of the top quark couplings. And we've done the first studies of boosted top production in E plus E minus, which was written up in this recent paper here. So CLIC occupies a kind of special position, having both the precision capacity of a lepton collider, but also very high energies. So it's the only currently proposed lepton collider that reaches multi-TeV scales. And so you really benefit from that in BSM direct searches. And so I wanted to include two very recent analyses here to try to illustrate the range. The first on the top here is a dark matter search for WIMP pair production using a monophoton signature. So this is a simplified model, but just intended to capture the essence of the full models. So it's got two particles, the dark matter particle X here and the mediator Y. And so you're seeing an exclusion limit in the plane of the masses of those two particles. And this is shown for a particular value of the electron mediator coupling, the coupling just at value 1, but we've done it for different values just for comparison. New for this analysis was the use of both electron beam polarizations, and whether the electron beam is left or right polarized significantly changes the irreducible standard model background. Also using the ratio of these two cross sections significantly improves the sensitivity. So for a benchmark value in the middle of this range, the photon energy spectrum can differentiate between the different mediators, whether it's a vector or an axial vector mediator. And we also looked at how well the mass of the dark matter particle could be reconstructed. And it's at the level of about 1% for a 1 TeV particle. And then the second search is for a heavy neutrino as a propagator, shown in these diagrams here. And we chose a fully visible final state to allow full reconstruction. So here a boosted decision tree is trained to discriminate between the signal and the background. And we're assuming a universal coupling between the heavy neutrino and the electrons, muons, and taus. And as noted, I think on this plot, there's slightly different assumption for the LHC search, where the tau coupling is set to 0. But as you see here, the CLIC 3 TeV sensitivity in green extends further across the plane than the other colliders. And just to note, it looks as if the ILC cyan line here is more sensitive. In fact, if I understood right, that doesn't include the photon-induced interactions. So probably the sensitivities are quite similar here. So those were more direct searches, but potential new physics can be probed indirectly using our precision measurements, and it's useful to use the standard model effective theory for that. So adding higher dimensional operators to the dimension 4 standard model. So that means it's implicit that there are new particles that are light enough to affect the observables, but maybe too heavy to produce directly. And so we can probe lots of theories at the one time in a model independent fashion. And so here I'm plotting the coefficients C of these operators. And in this case, small is good. It's more sensitive. So you see the HL-LHC projections under 2 systematic scenarios, and then the sensitivities in red, purple, and green for the 3 CLIC energy stages. And you see that we put in the Higgs, the top, the WW, and the 2 fermion production. And then in many cases, you're getting more than an order of magnitude better sensitivity than the HL-LHC. And you see also for some of these operators, and you really strongly benefit from the high energy running of CLIC. These are ones that grow with energy. So we're more sensitive to those. Those results can be interpreted in the context of particular scenarios. And so here's the result of interpreting these EFT limits in the context of compositeness, in this case Higgs compositeness, where the Higgs is a bound state. And what you see here is that even under pessimistic scenarios, Higgs compactness could be discovered up to a scale of about 10 TeV, or even up to 30 or 50 TeV in favorable conditions, and that's well above what the LHC could exclude, never mind discover. And then on the right here is a completely different example. This is looking at d sigma d cos theta for 2 fermion production. And so that's sensitive to new states that modify the distributions. You can look at the sensitivity for all sorts of different kinds of particle as shown here. And I've just highlighted this particular one because for these particular quantum numbers, it's a mass of about 2 TeV that would be required to account for the dark matter relic density. And so we would be sensitive to that. So I've tried to give just a few examples of searches that were very general. There are more. So, for example, this Higson heavy singlet, where you look for a heavy singlet decaying to 2 Higgs and 4 Bs. So this behaves a bit like a heavy Higgs. So we can explore its parameter space and then also explore the parameter space through the Higgs couplings in a very complementary way. And again, you see the click 3 TeV line projecting out into this parameter space. So we've looked at very many different new physics scenarios, and many of them are gathered together in this yellow report, the click potential for new physics, which I do recommend. So as I said, the accelerator R&D is continuing, which makes the click physics still very relevant. And there's growing interest, I think, generally in high energy lepton collisions, for example, a potential muon collider. But click is by far the most advanced of the multi-TeV scale lepton colliders considered, and the only one where we've done detailed physics. So in the next years, we'd be very keen for people to work a bit more on the importance of top quark physics of several energy stages, and looking at novel elusive signatures from direct searches and ways of constraining new physics from precision measurements. And so there are various efforts going on just now, collaborative efforts, including, for example, the snowmass process. And so if you've got a favorite model, we'd really be glad for you to identify the sensitivity to that at click. And we've got several tools available for that, a Delphis card and some instructions, which I've given the link there, and also a contact email address if you're interested in doing studies. And I think you've seen throughout this session a lot of coherence and the things that different proposals are doing. And I think historically we've really benefited from synergies among these projects at the technical level. So you see here the CLD detector is essentially click det adapted for FCCEE. There's a click det adapted for the muon collider, and all the different projects are moving towards a similar software future. So I think we can really benefit from this coherence and this collaboration, and I hope that can continue. So to finish off, Click's a mature project. We're ready to provide a Higgs factory and a subsequent multi-TeV lepton machine, both for precision measurements, sensitivity to elusive signatures, and at the multi-TeV reaches, we really get the extended sensitivity through the energy range. CERN's continuing its investment in Click Accelerator R&D for the next 5 years. And so far, we've provided the most detailed studies for the really high energy lepton collisions where there's increasing general interest. So I'd really like to encourage you to continue exploring synergies in the accelerator technology and the detector technologies and the physics studies, and also to contribute to Click if you'd like. Thank you very much.
Thank you, Aidan, for this great talk summarizing Click continuation of Click efforts. We are more or less on time, with our host being so generous towards speakers and maybe not so hard chairs of our session. So I do believe that we have a question. Time for question of 2. Yes, Jenny, please go ahead.
Yeah, thanks, Aidan, for the nice talk. I mean, we heard from Alain that the FCC gets 100 million Swiss francs or even 2. Can you indicate the level of funding for Click, which is foreseen?
Yeah, so the funding for Click is going exclusively to the accelerator collaboration. So there really isn't funding now for detector and physics. in the next period. I'm afraid I can't remember the number off the top of my head, but yeah, it's significantly less.
Okay, thanks.
Any other questions? If you allow me to comment following maybe not so well formulated example on the Higgs mass, but what Ivan pointed out, and I would like to comment it here, it is really needed to study BSM models that could be probed with future linear colliders if we would really like to understand what is the meaning of gain in precision of 2% or 3% or 2 per mil. So what is really a base, a mathematical base for our understanding of new physics signatures. So I think it was really nice point from your talk, Aidan, and these kind of studies are indeed needed. If there are no further questions, I would like to thank all the speakers for their wonderful talks and to kindly remind them to send their talks to the organizers so they can be uploaded on the conference site. Thank you once again. And what I can say, I think apparently it was a very successful session because we are ending up with more participants than we started due to our speakers. So thank you once again, and then talk to you soon.
Well, thank you very much to all the speakers of this very interesting session on the frontiers of particle physics, high energy physics, and special thanks to Ivanka for just very nice presentation of speakers and also the comments. And so we would like to announce that the next parallel sessions, 3 of them, will start at 5:10, so within 8 minutes more or less from now. Well, thank you very much once again.
Sergey, can you hear me?
Yes, I'm here. I believe it's time to start.
Yes, we can start.
Okay, thank you very much. So let me open the last session for the day, and now we start discussing the results from the collider physics. The first talk from Beijing Electron Positron Collider from De Jong. De Jong, do you hear me?
Yeah. Can you hear me and see my screen?
Yes, it's okay. Go ahead, please.
Okay, I'm very glad to be here at this very prestigious conference with all of you. I will report to you the latest new physics search results from Bay 3 on behalf of the collaboration. As you
Dayan, your microphone is off. Can you?
Okay. Yeah.
No, it's fine.
As you have heard from the plenary talk earlier today, you have heard the introduction to the experiment, so I won't go too much of it. But I want to tell you that the experiment is in very good shape. We have reached the design peak luminosity several years ago, and in recent 2 or 3 years, we are increasing luminosity continuously with the top-up injection, and also the center mass energy also increasing, so that we can cover more interesting wide phase ranges. We also have a concrete upgrade plan. So with this accumulation of statistics and good performance, together with a clean E-plus environment, and so it's now possible to search rare decays and probe new physics directly at Bay 3 as extension of the physics program. So today I will show you. So basically, we have performed several aspects of such searches. Here, I just give you an overview. So basically, we can search for the symmetry breaking processes. We can search these very surprise rare decay processes. We can also search the exhaust phenomena of particle that are predicted by various beyond standard model predictions. So there are several recent reviews. You can look more detail in that, and you can also follow our publications. So today, I will show you what is the major features of our new phase search at Bay 3. So basically, as I said, the event is very clean with very low background, and also the statistics is very high. You can see this is the world's largest data set from the charmonium. This is the GSI sample. We have obtained 10 billion by the 2019, and with great effort from software and reconstruction and calibration, and the data quality is very good. And we have a unique data set of charm hadrons near the threshold for both charm meson of D0, D+, D sub S, and also charm baron of lambda C, etc. All these provide us very good opportunity. Traditionally, at the charm threshold, we can do double tag technique to cancel many systematic uncertainty and provide absolute branch ratios. You could also, using similar double tag analysis, in the GSI decay, for example, GSI could produce coherently the hypon pairs. We can utilize similar technique and have a very good performance on that. So we have recently published more than 20 papers of new physics, so I couldn't go through all of them. I could just show you several selected results, mostly published this year, to give you an idea of what we could do and what we will do. The first result is about the charge flavor, lepton flavor violation processes for from GSI decays. So you have heard from the sessions 2 days ago that the charge lepton fluoridation is very hot topic pursued by many different types of experiments. Actually, GSI decays is also one of the places to look for that. Mining for the theoretical models have calculated these processes and introduced many mechanisms like something diagram like this and this, and some of them could produce could predict the branch ratios of such decays. For example, GSI to E mu could be enhanced to 10 to minus 16 to 10 to minus 9. GSI to E tau and GSI to mu tau could be reached to 10 to minus 9, 10 to minus 10 to 10 to minus 8. Now we have 10 billion that is 10 to 10. So it's feasibly to touch this upper bound of these models so that we can have a stringent test on them. Actually, the search results of these decay channels all come from base collaborations. For example, base 2 detector, we are using 58 million GSI sample to probe all of the processes. We have improved the GSI to immune upper limit with 225 million from base 3 dataset. This year, we published the latest result of GSI to E tau with a full 10 billion GSI data sample. We have divided this data into two subsamples of 1.3 billion and 8.7 billion. So we are using a different tagging channel for tau decay. This time we are using the pi0 new because this is has very well constrained kinematics with one charge track to good well reconstructed leptons, photons to reconstruct the pi0 and one missing neutrino. This is also kinematic constrained. So we require two charge tracks, one identified electron, one identified the pion, two photons reconstruct pi0 and one missing energy larger than 430 MeV. And we performed the blind analysis to define the signal region in the U-means variable, which is defined as the missing energy minus the absolute value of missing momentum as defined in this region. After the unblinding, we can see that the observed data samples are consistent with the background animation we do prior. So basically, based on these results, we have performed the maximum code. We have using the Bayesian method to set up a limit. This is the likelihood distribution. We can set the 90% confidence level limit to be 7.5 times 10 to minus 8. This is more than 100 times better than base 2 results, which is the ones based on the channel of tau to mu plus neutrinos. Actually, this is also the first paper based on the full 10 billion GSI sample from base 3. The second result I want to report to you is about the GSI weak decays. We have studied the GSI decays very carefully for many years, but most of the decays studied are from the hadronic, electromagnetic, and radial decays. The weak decays is too rare and very not studied so often before. But it has a very rich phenomenology because it means the C quark decay weakly through the double boson to very final states. And due to the kinematic constraint, GSI couldn't decay to one pair for D mesons, so the finals always contain one D or DS mesons. We just using various tag mode to tag the D meson and the accompanying particles and reconstruct the final states. Previously, base 3 has searched for GSI to DS, DS star plus E nu, GSI to DS rho, and GSI to DS K star, etc. For this semi-leptonic decay channels, we always using the hadronic mode to tag D mesons. For these hadronic final states, we can using the semi-leptonic decay mode to tag the D mesons, and so on. And recently, we have updated the results from the GSI to DE new process, also with the full 10 billion GSI sample, also using the same U-means variables as I mentioned in the previous analysis. Basically, we have carefully studied background and we have compared this the main background for gamma conversion and the hadron misidentification, and we can find that the inclusive Monte Carlo could produce these features very well, so we can make a maximum electric fit to retrieve the signal yield. This is the fitting result after unblinding. So you can see this is the background model of the blue line. This green histogram is the expected signal. So you can see by the fit, we didn't receive any signal near the signal region of U-means around 0. So we set upper limit by this formula, and this limit is now set very stringent as 7 times 10 to minus 8, which is also more than 100 times better than the Pierce result, and put some stringent constraint on the fit models. The third result I want to report is lifetime number violation processes from the sigma decays, sigma plus decay to proton plus same sign electrons, and sigma inclusive decay to sigma plus. The reason we search this inclusive channel because its phase space is very limited, and the lepton momentum is very low and couldn't be reliably reconstructed. So we couldn't distinguish, for example, the sigma minus to sigma plus EE versus sigma minus to sigma plus EE plus neutrinos. So we search them inclusively. Basically, these processes in the diagram level, they are both down-type quarks, two-type down-type quarks directly converted to up quarks. In some new phase models, for example, similar to neutrino-less double-banded decay, some Mariana neutrino-like features could induce them like this. And so we can probe this mechanism by using our huge data set. We do a blind analysis, and we are using the double tag technique. So the tag channel we're using is DSI to sigma 1385 plus sigma, because this has very high branch ratios, and we can tag them very clearly through the pi lambda decay product and lambda subsequently decay to proton pion. So basically, we have obtained more than about around 150,000 single tag events, and very clean signal. And you can see here, this is the signal, this is the background, and we can retrieve very clearly. And then we can go ahead to do the double tag analysis with both channels individually. For the first channel, we require 2 charge tracks in the tag set, with one identified as proton, the other identified as 2 electrons. For the inclusive channel, we require 1 proton and 1 pi zero to be reconstructed, and the others are missing. These are the unblinded data for these both channels. You can see there is no events remaining in the signal region, and we have very low background even outside. So basically, we can set the upper limit on this channel as 10 to 10 minus 5, on this sigma minus to sigma plus inclusive channel as 1 times 10 to minus 4. Both are the first search, and could provide further information on the model building in future. The last result I want to report is barrier number violation processes. Is actually lambda oscillation processes. Basically, we have a huge sources of hypons, including the lambda. For example, GSI2 proton K minus lambda bar. If such oscillation procedure could happen, then we will see a so-called wrong sign process of GSI2 P minus lambda. So both right sign and right sign and wrong sign process could go through EM and strong processes. So we reconstruct them individually, and we have a very good efficiency for reconstruct both of them. And then we integrate the ratio by studying the yield and the efficiency, and get this oscillation rate, because we don't have a dedicated vertex detector, so that we can only be sensitive to the integrate rate. Once we reconstruct this oscillation rate, this could be related to the oscillation parameter by this formula. This oscillation parameter is related to the mass difference between lambda and the lambda bar, if the oscillation could happen, and then we can limit this parameter. So this is the result. So basically, search with 1.3 billion GSI events. So from the bottom, you can see the wrong sign events distribution. You can see very narrow lambda peak from the proton and the pion reconstruction, and the upper plot shows the expected signal shape from the wrong sign Monte Carlo simulation. To see a wide range, you can see that there is no events remaining at all, only one event outside the range. So we can set the limit on this oscillation rate to be 4.4 times 10 to minus 6. And this convert to the oscillation parameter of the mass difference to be 3.8 times 10 to minus 15 MeV. This is also the first limitation on this process. And we would expect that this preliminary result could be published very soon. So let me wrap up due to the time limit. The Bay3 experiment has performed a very wide range of study of exotic decays and new physics in recent years. We have obtained many first search of best limit. Today, I have a report to you several new results which mostly published in 2021, including the charged lepton flavor violation decay of GSI to E tau, charmonium weak decay of GSI to DE new level number violation processes sigma to plus EE and sigma minus to sigma plus inclusively, and barrier number violation 2 process lambda oscillation. So you can see from these results, we have many great potential with unique data sets and analytic techniques. And as you heard from the plenary talks, we also have a concrete further data taking plans and upgrade plans for the next 5 to 8 years. So many of the future program and the sensitivity has already been provided in the white paper we published last year, so you can further consult that. And we are also trying to explore more and more beyond our boundary. So just stay tuned, and we believe more will come. Thank you very much.
Thank you very much, De Jong, for very interesting report. Now we have time for questions. I see one. Alexei, go ahead.
Hi there, nice to see you. I have a short question. So this lepton flavor violation, violating decay, it's a nice result. Is there a chance to see radiative lepton flavor violating decays with a photon in the final state?
Yes, actually, that was also in progress, but we met some, this is not so easy as compared to this and also immune. And because these additional photons could have a very wide range, and especially we have many fake photons in EMC and very soft photons sources is sometimes it's very difficult to model. So we are fighting against that. We hope we could also provide these results in the future. We will provide, but the work is still in progress.
Fantastic, thank you.
Okay, does anyone have any more questions? No? If no, I have one. De Jong, you, in your introduction, you mentioned about dark photon. Do you have some results about the subject?
Yes, we have published, I think we have published 4 papers related to dark photon. Because they are not the new one, so I didn't mention it very carefully. Mm-hmm. So for example, we have using the ISR processes of E plus E minus to photon plus E plus E minus and photon plus E mu plus mu minus. We have also searched through GSI decay through, for example, eta plus EE, GSI to eta prime plus EE. All these 3 are just normal dark photons. We also search for these leptophobic dark photons through GSI radiative decays. We also published, I think it's last year, 2020. Yeah, it's also put a limit. So we have 4 papers, and also we could also probe the invisible dark photons. These are still in progress.
Okay, thank you very much. Okay, if no questions, thanks again, De Jong.
Thank you.
Thank you. And now we are going back to the LHC experiment, and now the Andrea with review of the phasor experiment.
Yes.
Andrea.
Everyone.
Okay. Please translate your slide.
Yes, I'm doing this right now.
Yes.
Okay. Hope you see my slides.
Yes, yes, it's fine. Okay, go ahead.
Okay, so thanks a lot for the invitation, for organizing this nice workshop. I'm here to tell you about the phaser experiment at LHC. So as an introduction, let me spend a few minutes on the physics prospects. The experiments at LHC, as you know, have been focused over the past years on looking on heavy and strongly interacting particles. And you do that by basically looking at the transverse plane. So since we have seen no new physics at the TV scale so far, this initial paradigm has been broadened over the years. And there are two main directions that we have been used at LHC for broadening this paradigm. One is using existing experiments by adopting new trigger techniques or new reconstruction ideas. For example, looking at displaced objects, or for example, looking at analysis using trigger level quantities. There are a lot of, let's say, R&D that has been put on the large experiments at LHC in order to broaden the physics coverage of the searches. The other direction has been to propose new experiments, and you want to do that to complement the coverage of the existing experiments. And when you think about this, you are mainly looking towards new physics, which comes through particles which have longer lifetimes and lower masses. So among these two directions, phaser aims at, let's say, embarking into the second one, and in particular aims at searching for light and weakly interacting particles. And the aim of phaser is accomplished by looking at the very forward region at a distance where the known background is highly suppressed, and by doing that using a dedicated low-budget detector, which is placed in a side tunnel, a TI-12 side tunnel LHC. And the detector has been supported by the Simons and the Eisen-Simon foundations. So a few more words on the idea behind phaser. So the new physics LHC focus, as I said, at the transverse plane, which means that high events which comes with high PT, meaning high transverse momentum So usually this means that whatever new model you pick up, it comes with some cross-section of new physics, which can be of the order of the picobar or femtobar. So that if you translate this range of cross-sections in the luminosity, which is foreseen at around 3 of LHC, which is 150 inverse femtobar, means that the number of events, of new physics events, can range between few hundreds and few 10,000s of events. Obviously, I'm not taking into account any acceptance with the detector, any acceptance with the trigger, and so on, and the ability, for example, to isolate the signal of the background. Just talking about pure number of possible new physics events. These numbers, I mean, it's not super small, but if the new physics is light and weakly interacting, then you may argue that looking at the very forward region instead of the transverse plane is a better place to look at, because in that region, you have an extraordinary rate of low mass phantom molecular particles. To give you some numbers, if you want to look at this direction, you have to take into account of you have to take the cross-section of the inelastic protoproton collisions, which is about 75 millibar, so really order of magnitudes above the signal cross-section that we were speaking before. And this translates, again, using the same luminosity foreseen for LHC-3, translates the number of inelastic events, which is about 10 to the 16. This means more or less that 10 to the 17 pi0 particles are created in very forward region, which means that 1% of those, more or less, are the particles that enter in the phaser acceptance. So the number of pi0 in the very forward region is extremely high. And if you look for light and weakly interacting particles, you could expect that in very few cases, for example, some of these pi0 particles will decay to some new physics. Pi0 is only an example. There are other low mass phantom molecular particles. But this is just to give an example of the order of magnitude difference with respect to looking at the transverse plane, with respect to looking at the very forward region, if you assume the new physics is light and weakly interacting. Okay, so where phaser is located, as I said, is in the very forward region. We are close by the Atlas interaction point, which is basically here, is one of the main 4 points of interactions at the LHC. And here we have the LHC tunnel, which is going towards the LHCb. And here there is this TI-12 tunnel, which is a service tunnel between the SPS and the LHC. Here we are about at 500 meters from the interaction point. So if you go to the, let's say, to the lower part of the slide, you can see in this sketch, in this right sketch, which is about drawing, which is about the distance between 460 to 490 meters from the interaction point. You see very clearly that there is the LHC tunnel, which is already, let's say, going away towards LHCb, while the beam collision axis is on the other direction. And the beam collision axis passes through this tunnel, and here is where the phaser is located. So that we are basically online with the beam collisions, and if there are some neutral long-lived particles that are created in some decays of low mass standard model particles, these can travel all the way up to the location where phaser is located. Okay, here just a sketch of the detector layout. We have a 1.5 meter decay volume, which is inside the magnet, which is basically this first red part. Here is where we expect the possible new physics to decay, so the possible new neutral and long-lived particle to come and decay. And then we have 2 meter spectrometer with 3 tracking stations, 1, 2, and 3. And then we have for triggering, we have 3 scintillator stations, 1 here for vetoing and 1 and 2 here for let's say, for confirming some activity. And then at the end of the detector, we have an electromagnetic calorimeter for looking at the, let's say, energy deposits of the possible decays of this new particle. The whole aperture is about 20 centimeter, which means pseudo rapidity, which is more than 9.1, which is very, very, very forward, obviously. Okay, so the dimensions you see are very compact, which means also that the detector comes with a very, say, low budget. Okay, so we performed some exercise in terms of sensitivity, and here I'm just showing an example. We already discussed about dark photons, which is a nice benchmark. So we are picking again this benchmark. So here the benchmark is that in the collision between protons occurring at LHC, particularly within the Atlas experiment, there can be a production of a particular dark photon plus X, and then the dark photon after traveling can decay to 2 electrons. And if the energy of the dark photon is order of the TeV, the products are collimated, and the decay products are within the acceptance of the phaser detector. And for certain particular ranges of lifetimes, you get also the decay within the phaser detector. So the signature that we are looking for are 2 high-energetic, oppositely charged tracks. You can see those here, E plus, E minus, which are coming from a common vertex in the decay volume, and which are also pointing back to the interaction point in Atlas. And in addition to that, we need to have no signal in the scintillator station, so in the first scintillator, while we do have some activity in the 2 other scintillators, which are needed to trigger the event, and obviously some, in case of electrons, some energy deposits in the calorimeters. So what does it mean, this in terms of, let's say, sensitivity to this particular benchmark? Here we have this very popular way of showing the sensitivity. Here in the y-axis, you have the epsilon parameter, which controls the coupling between the standard model and the dark photon. And here the range is between 10 to the -3 and -6. And here we have the mass of the dark photons, and here we have the range of 10 MeV up to a few hundreds of MeV. And here you see that with just 1 inverse femtobarn of let's see data, phaser is able to exclude possible dark photons in this range of masses and epsilon values. And by growing the data sets up to, for example, 150 inverse femtobarn, which is what we can get by the end of round 3, obviously the parameter space that can be inspected by the experiment becomes pretty large. This obviously, as I said, is a quite popular way of displaying the results, and in fact you can see that on the same plane there are already results which have been put by HCB and BEL2, for example, and there are also by other dedicated experiments that have been proposed or that are taking data that do plan to let's say, put constraints on this plane. Okay, the discovery potential exercise has been conducted not only on dark photon, but also on other models. Here we have again the dark photon model, but here we have the dark Higgs on the top right, the heavy neutral lepton on the bottom left, and the actions particles on the bottom right. So for all these kind of new physics models, there is some sensitivity. In addition, it's nice also here to highlight that here you have the contour of the exclusion by Phaser itself, which as I said is fully funded and will be taking the Terra 3, and also a possible Phaser 2 experiment, which basically doesn't really exist, but it's just an idea of a possible projection for the luminosity LHC period. And in this possible idea, Phaser 2 will be a kind of bigger experiment. So instead of, for example, of a radius of 10 centimeters, will be a radius of 1 meter, and the luminosity also will scale accordingly to the operations of the luminosity LHC. So assuming that these numbers will become real, then you can appreciate how Phaser 2 will have better sensitivity over a wide range of parameters compared to Phaser 1. All of this has been detailed in a Phaser paper, which has been published on Physics Review. And we have the link here at the bottom. Okay, now I will spend a few minutes just to, let's say, list the various sub-detectors that we have in Phaser, starting from the tracker. Here we are using some spare silicon strip modules that were left from Atlas. So as I said, a cheap solution was found. So in this case, we are talking about 72 modules. The total number of channels is about 10 to the 5. They be arranged in 3 stations, 1, 2, and 3. Each station comes with 3 layers and 8 modules per layer. We do expect to have a resolution of 25 micron, say heat resolution of 25 micron, and the possible presence of defects of the below 0.1%. These numbers have been carried out using extensive testing on surface and also cosmic ray rounds. Then scintillators, as I said, we have 3 stations. They are needed for vetoing charged particles at the start so that we can only select neutral particles entering into the detector. And the efficiency is measuring cosmic data to be more than 99.9% for a single layer. Then we have the colorimeter at the end. This has been with a readout using KMTs with custom voltage divider base. And the colorimeter is constructed with 66 layers of LED and scintillators. And this corresponds roughly to 25 radiation length. And the expected energy resolution of 1 TeV is 1%. And then I haven't mentioned it yet, but there is also another, let's say, twin detector, which is placed at the beginning of Phaser, which is called Phaser New, because there is also a dedicated neutrino program with a dedicated emulsion-based detector, which aims to study neutrino production, propagation, interaction at TeV scale. And I will not go too much in details on this because tomorrow there is a dedicated talk by Tomohiro at the neutrino session where you get all the details about the Phaser New program. But let me just mention that within the Phaser New physics program, there has been a pilot run which has been taking data in the past years. And this data has been already analyzed. And within this data, there is already the first neutrino interaction candidates events at the LHC that has been reported. Here we have the archive link of this analysis, and the analysis has also been the manuscript has also been submitted for publication. So in addition to this new physics program that I highlighted, Phaser will also come with a dedicated neutrino physics program. Okay, here you have a few pictures on the evolution of the installation of the Phaser detector. You see on the top left in August 2018, so 3 years ago, how the tunnel, the service tunnel was looking like. There was nothing, just let's say services, general services. It took some time to clean it up and having, let's say, it ready for the start of the installation. One thing that was also very important is that some drilling works to lower the floor of the tunnel. This was needed to be perfectly on axis with respect to the beam direction. And this was completed in April 2020. And then after that, the real installation started. Here you have a snapshot of what the detector was looking like in November last year, with the major magnets already installed. And by April of this year, April 2021, all the detector was installed and in place. So, as I said, the detector is fully and successfully installed, and this is the case since end of March 2021. And since then, we have been taking cosmic ray data, plus some test beam data in the first part of August of this month, basically just a few weeks ago. We have extensive studies of the data that's been taken, which are ongoing, and there are some plans for publication of this data. And we believe that we are on track for physics runs in the LHC round 3. So some more information on the ongoing commissioning of the detector. So the detector is basically running almost continuously since the start of cosmic data taking. Here you see a plot which is ranging from the mid-April up to mid-May. So this spans over 1 month. You see the trigger rate of this cosmic data taking runs, which is almost constant at about.
I'm sorry, Andre. How many time you need more?
Okay, I'm almost done. About 10-15 hertz, and this is the rate that we get when we require a 2 scintillator coincidence. And then of this data, we do, for example, we are exercising the reconstruction, also prompt reconstruction. And here I have an example of a track which is seen in a nearby scintillator in a particular event. And the rate of events in which we find a track in a single station is about 1 per minute. And then we have the curve simulation, reconstruction, and all the monitoring, which is also being developed and exercised. This brings me to my summary. So Phaser is a new experimental LHC that's been designed for detecting light and weakly interacting particles, and is also complemented by a dedicated detector for neutrino physics. And you will get more information about that, let's say, tomorrow. Phaser is installed in the LHC tunnel, has been taking cosmics and has been data since the end of March. The commissioning is ongoing and is proceeding very well. And this ongoing work now on various pieces of the detector and also on the data flow and the calibration of the data and the construction of the data and so on. In addition to that, we have the first neutrino interaction candidate has been observed and a related paper that is submitted for publication. So all in all, the work is progressing and Phaser is looking forward to the first collisions of the LHC round 3 in 2022. Thanks a lot for your attention.
Okay. Many thanks, Andre, for nice review of Phaser experiment. Now we have time just for one brief question. Okay. If no, thank you again. And before moving ahead, I would like to ask all speakers to try to save time. The organizer asked us to stick the original timeline, so please do it. And now we coming to the new results from the new physics from the CMS experiment. And Jyoti, are you online? Yeah.
Hello everyone, I'm audible.
Oh, okay, we see you. Yeah. Okay.
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 So hello everyone, I'm Jyoti and will be presenting on the behalf of the CMS collaboration. So I'm presenting on the search for the resonance in the photon plus jet final state using the CMS data. Starting with the introduction, so we all know that standard model gives an extraordinary insight to the fundamental nature of the matter, but yet we cannot explain everything in the universe with the standard model. So there are many standard model, beyond standard model searches going on, and one of them would be is why only there are 3 generations of the quarks and leptons. So there are models which are predicting that quarks and leptons are not the fundamental, and there is yet an underlying structure for the fermion families to be discovered or known as to. And another BSM model would be outstanding enigma of the particle physics, that thus a hierarchy problem, which is the large difference between the scale of the electroweak and the Planck scale. So the existence of the extra dimension can explain such large difference. We know that standard model confined to a 3 ray and only gravity propagates in the extra dimension. To the next slide. So from the previous results, We have the existing results by the CMS at least at the center of mass energy 13 TeV, decaying to photon plus jet channel. So we have excited state of quarks and B quarks that would be like the quarks and the quarks are not the fundamental. So that are excluded by the CMS up to 5.5 TeV, that is the excited Q star, light quarks, and B quarks, that is a heavy flavor B quark, are excluded up to 1.8 TeV with the luminosity 35.8 femtobar inverse. And excited quarks are excluded by the at least up to 5.3 TeV with the 36.7 femtobar inverse. Two other models are, that is the quantum black hole models ADT and RS1 of the QBH. They are excluded up to 7.1 TeV and 4.4 TeV by at least with luminosity 30.6.7 femtobar inverse. So this the coming slides will be the search for the new resonance decoying to photon plus jet final state with the luminosity 137 femtobar inverse, that is the same as luminosity for the 2016 to 2018. So the more data we know leads to more potential for the new signals, and there are many new techniques implemented. So we are expecting the better results with the more data. The bottom left plot is for the signal shapes of all the signals considered, that is for the excited quarks, light quarks, excited B quark, heavy flavor, for the ADD model, for the QBH, and for the RS1 model. The shapes for the excited quark signal, that is for the red and the green, are the similar ones, and for the ADD and RS1 for the QBH, which are blue and the magenta one, are similar. So this is for the resonance mass of 4 TeV. To the next slide, the signal modeling composite models predicts that there is the substructure of the quarks with light flavor and heavy flavor, and the excited search for excited light and heavy flavor with the coupling multipliers to the standard model of 1.0, 0.5, and 0.1 is performed. And for the other model, that is the quantum black hole models, the quantum black hole we know are the quantum analogs of the black holes, and they can be produced at the LHC. Due to the radiation and the experimental effects, it appears as a resonance. So QBHs are the non-thermal objects. They are expected to predominantly decay to a pair of particles. So there are well-known models of the QBH are there, which are studied by many experimental high energy experiments. That is for the ADD, which is n is equals to 6 extra dimension, and the RS1 with n is equals to 1 extra dimension. So for the model QBH RS1 decaying to photon plus jet, this is being studied first time in the CMS. To the next slide. Photons, we know in the CMS there is a tracker after the collision point, and to track the particles track, and then there is an ECAL, which is for the reconstruction of the photons and the electrons, and after the electronic calorimeter there is hadronic calorimeter for the reconstructions of the hadrons. So we reconstruct the photons in the ECAL, and for the jets it is the reconstruction is being performed in the hadron calorimeter. So photon energy are calibrated in the electronic calorimeter of the CMS, and there is obviously no tracks associated with the photon. And jets are reconstructed in the hadronic calorimeter. So there is a condition applied with jets with the delta R, that is less than 1.1 between them, are merged together to form a wide jet to account for the final state radiation. Like in this, there is one jet and there is jet 2, and if the delta R between them is less than 1.1, they are merged together and they are termed as the wide jet. This is to account for the FSR. To the next slide. So the standard model backgrounds, the major background to this study is, as we see that the here we have the quarks and gluons, that is they form a quark and B quark, and then they radiate or decay to quarks and gluons. So the major background to this study is the standard model photon plus jet background, and with a very small contribution from the QCD and the electroweak background. So to reduce the background and to improve the signal efficiencies, selections are applied, like high PT photon in the barrel region of the detector, that is with the delta eta, with the eta of the photon less than 1.44, and the high PT white jet in the central region of the detector is selected. For the resonance to exist, the photons and jet produced via hard scattering would decay mostly back to back, and they are selected. Also, the multi-jet backgrounds, which is contributing when the pion decays to two overlapping photons, like shown in this small diagram. That is, we see a photon deposit energy in the ECAL in many super clusters, and also when a pion decays to two photon, it is deposits such type of energy with the red color shown. So to reduce such kind of background, the delta eta condition between the photon and the white jet less than 1.5 is imposed. To the next, the analysis strategy. So the search for the resonance is performed by looking for a bump in the invariant mass distribution of the final state particle, that is a photon plus jet. And the background estimation is done from the data. And the simulations are used for optimizing the selection that are being applied, and also with the validating with the data. So on the right side, we see two plots that are the photon PT and the jet PT. The upper one is the photon PT distribution, and the lower one is for the jet PT distributions. So we see they are both well in agreement. We have the backgrounds, that is the GJ is the standard model gamma jet background, which I already mentioned in previous slide. That is the major contributing background. The light gray one is the QCD background, that is the multi-jet background, and the other two backgrounds are from the electroweak background. And two signals are shown here, that is for the excited quarks and for the QBH with ADD model for the two mass points. So these distributions are well in the agreement, and the distribution here, it is for the 2018 data with luminosity 58.7 femtobar inverse, and we see the same distributions with the 2016 data with luminosity 35.8 femtobar inverse, and with 2017 data with 41.7 femtobar inverse. So we see that the data is consistent with the standard model expectations here. To the next slide. So to observe any excess of events, as I already mentioned in the previous slide, that we look for a bump hunt in the invariant mass distribution of the photon plus jet. So the distribution, the invariant mass distribution, is fitted with this polynomial function to look for any bump. This distribution, this functional form is for in the numerator, it represents the mass dependence of the pattern distributions, and in the denominator, it refers to the mass dependence of the QCD matrix elements. So in the right plot, here it is the standard model simulation, the black points as mentioned in the legends, and other are the signals peaks shown. So these are the expected signal mass point shapes for the four models. That is for the, this is for the three models. For Q star excited quarks, 2 mass points, 2 TeV and the 4 TeV. For ADD model QBH, it is for 3 TeV, and for the RS1 model QBH, it is for the 1.0 TeV. So we are following the policy that the data is kept blinded, and the MC simulations are used as a proxy of the data. So data will be kept blinded until all the selections are being optimized, and we are happy to see the data until then. So the functions is chosen here, the polynomial function. It is chosen on the basis of the Fisher test and the goodness of fit test, with their p-value significance at greater than 0.05. To the next, systematic uncertainties. The major systematic uncertainties come from the uncertainties on the parameters in the background functional form. That is, in the previous slide, the polynomial function, there are various parameters. Can I go back? See, let's have P0, P1, P2, and P3. So the major background contribution come from the uncertainties on those parameters. Also, the bias study is performed to account for the possible bias due to the choice of the functional form chosen. That is, that we have chosen this functional form, but many other functional form can depict our data. So we perform a test with those functions, and we see if there is any bias related to the functional form chosen, and if there is any, that is included in the systematic uncertainty. So we concluded from the results we checked that the systematic due to the bias is the negligible as compared to the statistical uncertainty of the fit. And other uncertainty dominated are by the photon ID efficiency, inefficiency, which I would say that is the 10%, and for tagging the B quark, which is the 14%. To the next slide. So the expected limits are calculated with MC, and the expected upper limits on the cross section for the signal measured is as that the excited quarks are excluded up to 6 TeV, the B star excluded up to 2.3 TeV, and for the QBH model, ADD is excluded up to 7.6 TeV. So these exclusion mass points are for the MC predictions, and data is still blinded. And bottom three plots are for the these signals. That is, the left side is for the excited quarks, then the middle plot is for the excited B quarks, and for the right plot it is for the black hole ADT. To the summary, the search for the excited quarks and light and heavy flavor quarks is performed using the CMS data with the luminosity 137 femtobar in burst. And there is a possibility of quantum black hole at the LHC, and the decaying to particle state is also considered with the two models, that is for the ADD and for the RS1. And expected exclusion limits on the signals are calculated. Since the data is blinded, till the selections are optimized from the simulation, so we are waiting for the results, preliminary results, and hopefully they would be good. So yeah, thank you.
Thank you very much for a nice talk. Now we have time for discussion, questions. Does anyone have questions before we go ahead? No? If no, thanks again, Jyoti.
Thank you.
And next speaker, Amandeep, with review of CMS exotic results.
Hello, can you hear me?
Yeah?
Hi. So do you see my slides?
Yeah, sure. Okay. Go ahead, please.
Hello everyone, this is Amandeep Kaur. I'm from Punjab University, and I will be going to present some of the latest results in the exotic from the exotic physics by the CMS detector. And before moving to the results, I will briefly describe the CMS detector. So CMS is one of the two multipurpose detector at the LHC ring, which resulted in the discovery of Higgs boson in 2012. And with successful data taking during run 2 and having several upgrades for implementing fast electronics, CMS has recorded up to 139 femto1 inverse of luminosity from 2016 to 2018 at 13 TeV. So as you can see in the bottom figure, this is the plot from 2015 to 2018, and the recorded luminosity from 2015 to 2018 at 13 TeV was 150 femto1 inverse. So this led to more precise standard model measurements and better understanding of standard model physics, and it also opened doors to explore rare physics signatures beyond standard model. So here is the latest picture from the standard from the CMS detector, which is currently under various upgrades. And here I show the mean number of interactions per bunch crossing happening in 2015, 2016, 2017, and 2018. On the next slide, I will here now the question explain why we wanted to look for exotic signatures, or we wanted to look beyond standard model. So as we know that here the standard model actually successfully explained the structure of matter and the forces between them, but still it fails to answer many important questions like inclusion of fourth fundamental force, that is a gravitational force, why we see only 5% of matter made up of ordinary standard model particles, why there are only 3 families of quarks and leptons, and if there is any there is a more fundamental theory of which this standard model is just a low energy approximation. So to answer all these questions, new models beyond standard model have evolved with time, and they predict the new phenomena at the TeV scale. So what do we look for beyond standard model? we look for signatures of new resonances, which explain the previously mentioned questions. We look for signatures of dark matter candidates. We look for long-lived signatures of long-lived particles, or we look for the new quarks like leptoquarks, excited quarks, or other form, vector leptoquark or scalar leptoquarks. So first, I will talk about the results from the CMS, various CMS analysis. I will talk about this W gamma resonance search that has been performed in the CMS using the full run to, that is 2016, 2017, and 2018 data. So here in this analysis, W decaying to two pair of quark jets has been considered, which will be forming a single large radius jets, and which is having the two subjects. Because of the boosted jet topology due to the high Lorentz boost of the W boson, this wide AK8 jet has two subjects, and this soft drop algorithm, jet algorithm, is used to remove the soft wide angle radiation coming mainly from QCD, and this helps to attain more signal efficiency and suppress the background such as QCD. So on the plot on the right-hand side here, we show the different backgrounds and data in control region, which is represented in black dots, and the signal region, which is the red dots, as a function of mass of J gamma system. And here different signals are also shown on this plot. And we see that over this smoothly falling background, no excess in data has been observed, and the limits has been set in both spin 1 and spin 0 resonances. So here in the left-hand side, I show one of the plot from this analysis, where we show the green bands, and the dotted line shows expected upper limits on the cross-section times branching ratio, and the solid line, black line, shows the observed limits on the cross-section times branching ratio as a function of mass of the resonance. And the success around 1.5 TeV has been observed with local sigma of 2.8 sigma, and it is examined to be just a statistical fluctuation in data. And with this, the limits has been set on heavy scalar and vector triplet bosons with masses between 0.75 and 1.40, and these bosons are excluded at 95% confidence level. This analysis also shares with us the model independent limits, which can be utilized by various theoreticians. On the next slide, I here show another resonance search performed by CMS using the dielectron and dimuon final products. And here this search actually searches for both spin 1 particles, that is Z prime, and spin 2 gravitons. Here on the left-hand side, I show the mass of dielectron system, and here the black points are the data points, and these different colors are for different backgrounds. And here we also here in the high I mass end of the spectrum, we see the Monte Carlo signal samples, and we see that over this smoothly falling background, no excess has been observed in data. Similar is the case for the dimuon channel. But this analysis actually results in more stringent limits on the masses of various spin 1 particles and spin 2 gravitons in the RS model. And here on the left plot, on the upper left plot, we see that the cross deviation from the standard model Z search, we see that as a function of mass of Z prime, the limits has been set, and the lower mass limits of 5.15 and 4.56 TeV are set for different model of Z prime. In the bottom, the limits has been set for the spin 2 graviton in the RS model, and we can see that the lower mass limits of 2.47 TeV up to 4.78 TeV are set. Also, this analysis results in lepton flavor universality results at a TeV scale, and this has been the first results from the CMS. And here we see the ratio of differential cross sections of dimuon and dielectron system, And these error bars shows these both statistical and systematic uncertainty. And we see that no significant deviation from standard model expectations are observed, and the results are more or less around the unity. So these are the first results of lepton flavor universality tested at TV scale by the CMS. On the slide 7, I show here the another resonance search performed by the CMS detector, and we probe here the trijet trijet resonance with boosted dijet and single jet. Here it is assumed that this R1 resonance decays at rest, and this R2 resonance has mass so small that the results of this R2 resonance are boosted and are highly collimated. So this analysis actually will result in 2-jet system. So here we see that one of the various plots for this analysis. Here the signal is considered to be 2.9 TeV, and the mass of the second resonance, which is spin 0 radion, is considered to be 0.4 TeV. And we can see that the data agrees well with the standard model background, and no excess has been observed. So this analysis actually results in upper limits as a function of mass of the resonances, and this analysis also provides the reinterpretation for this KK gluon decaying to dijet pair. So this is the plot for that. Also on the next slide, slide 8, here is another analysis search performed for heavy charge boson W prime. Here W prime decays to either electron or muon and large missing transverse energy. And this in this, the decay products of W prime are highly back-to-back. That is, the electron or muon are in the opposite direction to the PT miss. And as we can see, this analysis provides the upper limits as a function of mass of W prime. So here I just show the final fit, the data and different backgrounds as a function of transverse mass of muon or electron and met as a function. And here I showed these two signal samples here. So no significant deviation from standard model background is observed in this case also, and the limits has been set as a function of mass of Z prime. So best exclusion limit obtained is 5.7 TeV in the mass of sequential standard model Z prime. Also, this analysis, because of searching for W prime in the high mass region, this analysis is sensitive to the W propagator. So the standard model W propagator is considered to be with these W and gamma parameters at 0. But the effective field theory interpretations quantify the potential deviation from the standard model expectations. And we now, with this analysis, we wanted to observe the deviations and in the oblique electroweak W parameter. So the here the fit result shows the using 2017 and 2018 data, and the fit result shows that the region is constrained by the is consistent at 2 sigma here, 2 sigma with the standard model value of the W propagator at W parameter at 0. Next, on slide 9, I explain here the next exotic signature, that is a leptoquark. So leptoquarks actually appear in many beyond standard models to answer the questions like why we have the same number of same generations of leptons and quark. And these leptoquarks, they carry both lepton and baryon numbers. They carry fractional electric charges, and they decay in lepton in one lepton and jet. So these leptoquark searches are highly motivated by the grand unified theory, technicolor models, composite scenarios, R parity violating symmetry. So indeed, the signature of this leptoquark will provide an explanation for a series of anomalies that have been observed by Babar, Pelle, and LSCB in the B meson decays. So one such result analysis is performed by the CMS for the probing of leptoquarks. In this analysis, we consider two production modes of leptoquarks. One is pair production of leptoquark, one is the single production of leptoquarks. In the pair production of leptoquark, we consider that the leptoquark couples to top quark and tau, and bottom quark and neutrino. And in the single production of leptoquark, we consider that the leptoquark couples to top quark and top quark and tau, and bottom top quark and neutrino, and bottom quark and tau. So in this analysis, we consider the high. This analysis will include high PT miss, that is a high transfer momentum, missing transfer momentum, high HT here the scalar sum of PT of all jets, and one hadronic top candidate and one hadronic tau candidate. So the main backgrounds in this analysis would be real top production and the misidentification jet as considered jet faking the tau hadronic. So these backgrounds are actually calculated or estimated from data. So here I just show one such example of different backgrounds in one of the two topologies that have been considered in this analysis. So on the left, we have hadronically decaying top quark reconstructed in the merge topology. Here we have hadronically decaying top quark reconstructed in this resolved topology as a function of ST, which is a scalar sum of PT of top quark, tau hadronic candidate, and PT miss. So the lower limits at 95% confidence level on the leptoquark mass in the range of 0.98 to 1.73, depending on the leptoquark spin and leptoquark coupling are set. And here I just show one such example of coupling, and as a function of the limits as a function of leptoquark mass. The regions to the left of these lines are excluded for the signal of leptoquark. So another exciting analysis or search by the CMS is performed using for the exotic Higgs decay, where exotic is in association of Z boson, which provides sensitivity to this analysis. And this exotic Higgs decays to two scalar, which further decays to jets. And because of this long-lived nature of the scalars produced, these jets would be displaced jets. So we considered the prompt dilepton and greater than 2 displaced jets with hits in the tracker volume. So with this, the most stringent constraints on Higgs decaying to light long-lived particle are set. And on the plot on the bottom, we show the different validation regions and the signal region. And because most of the standard model processes has smoothly falling distribution for number of jet, but for this signal, we have the displaced jet greater than 2. So our signal here, signal region is highly depleted in the different backgrounds. So H2 scalar branching ratio is constrained to be below 5 to 10% for proper decays lengths of 10 to 100 millimeter and masses between 40 to 55 GeV. So no significant excess over standard model background is observed, as you can see in this picture. And so similarly, the constraints are set for both scalar going to DD bar and BB bar.
Mandip, I'm sorry, your time is close to be over.
I will be quick, sorry. Yeah. So the next results are from CMS are the first results for long-lived hadronic showers in the N-cap muon system. In the previous, so in this, the hits from the long-lived particles, they decay hadronically in the muon subsystem of the CMS detector, as you can see in this cartoon, where this shows the signal efficiency in the CSC. So in the N-cap we have CSC, so it shows the clusters in the CSC. So to suppress the backgrounds such as out of time pileup, these clusters are built in the CSCs with this timing window for the cluster. And here I show the cartoon for in the R5 plane how the long-lived particles, they decay to different hadronically in the CS and give hits in the CSC. So no significant excess, as you can see in this picture, in the second bin, which is the signal region bin, is observed above the standard model predictions, and the limits are set in this scale, this long-lived scalar decaying to dd bar, bb bar, and di tau bar. So here I just show the different mass of the scalar, the limits as a function of the C tau. So one other results are for in the when we have the jets in which gives signal in the tracker ECAL and HCAL. So here we have the distinctive is of the secondary vertex, and in this analysis, secondary vertex, this is the secondary vertex is reconstructed, and the dominant backgrounds are QCD backgrounds. So a gradient boosted decision tree technique is used, which uses variables like vertex track multiplicity, signed impact significance of impact parameter, significance of transfer distance here, as you can see in this cartoon. So with this, with the GBDT score of greater than 0.98, we see that in this signal region, no excess has been observed. So the branching fractions are excluded for C tau between 1 to 340 millimeter with the masses of 40 GeV for light flavor, and for C tau of 1 to 530 with masses greater than 40 GeV for PV bar. So on the one of the last form for very low mass bosons, for this particular analysis, this B hadron decays via this decays to the muons, and this muons are actually the displaced muons. So this for this analysis, dedicated ion trigger has been developed with low transverse momentum to select displaced muons with transverse displacement of less than 11 centimeter from the interaction point. And this helped in exploring the inaccessible phase space as low diamond bands. So a bump hunt is performed from 0.3 to 50 GeV, and most stringent constraint to date on the BSM signal in the wide range of signal and lifetime hypotheses are performed. So here, you can see that over this smoothly falling background, no significant excess over is observed, and limits are set for C tau for 1 millimeter, 10 millimeter, and 100 millimeter, as you can see in this bottom picture. So just to summarize, CMS has performed wide range of analysis for exotic signatures, which helped in probing in multi-dimensional phase space, and many new searches and now shared with the run2 data. This rise in new techniques and the tagging algorithms for run3 are developed, and which will give us further new results, and new tools using machine learning are in practice. So we are excited to look for exotic signatures with upgraded detector and advanced technology. Thank you.
Okay, thank you very much, Amandip, for comprehensive review. Just one question.
Mm-hmm.
Does anyone have any more questions? Any questions? If not, thank you again. And now we're going to the Atlas results. The first talk by Mohammed.
Hi, good evening. Can you hear me?
Yeah, sure.
Okay, my screen. Okay. So can you see it in full page?
Yeah.
Okay, so thanks. So
okay.
Yes, okay. Yes, let me start it. So today I'm going to highlight some of the newest and latest results concerning the searches of a new phenomena in the Atlas experiment. So let's just take a short motivation about this kind of searches. As we know, the standard model has astonishing success in describing the elementary particle interaction, the discovery of the Higgs boson, and many other things. Still, many shortcomings or questions already left by the standard models. So, for example, hierarchy problem, or the gravitational force is not included. So this is the motivation for searching for new and more advanced theories, frameworks, like to describe and to cover the weakness of the standard model. Like, for example, we have SUSY, like a random syndrome model, where the unification between the gravitation and the electroweak, and many other frameworks. So on slide number 3 here, like in an Atlas experiment, we have a rich program of searches of a new physics in different areas, and like to see like some for sure to answer the questions already left by the standard model, and to see like some deviations from above the standard model, like for example to see some resonances or some non-resonances physics, like on some of the couplings and so on. So today I'm going to highlight some, or like, few results from the Atlas experiment, in particular targeting the BSM resonances and non-resonances physics in different decay channels. And if I have a time, I'm going to highlight like some 2 results from the exotic decay into long-lived particle in different decay channels. So in slide number 4, let's get started with the resonances decaying in a full hadronic decay channel. Like in this kind of decay channel, it's already covered in different scenarios, in new physics scenarios, like for example, the searches of heavy Higgs, heavy gauge boson, or excited quarks, and so on. And in this decay channels, like a wide range of resonances already covered, like for the masses between 400 GeV up to 10 TeV, highlighting like some new techniques and improvements to be sensitive to the presence of new physics, like for example, improvement on the B tagging algorithm, in particular for the jet with a high BT, some new techniques like to reconstruct the hadronic decay of the top jet in the boosted region or the resolved region. So this kind of techniques can help like to increase the sensitivity of the presence of the new physics, and some algorithm to reconstruct the tracks and vertices for macroscopic live particle, like in terms of the exotic decay of some particles in a long-lived particle. So let's get started with the first results concerning the resonances decaying in the top quark and B quark. So in this analysis, like the deep neural network already used to identify, in particular, the large R jets containing or originated from the top decay, in this case the hadronic top decay. In the case of the B quark, more advanced or modified, improved B tagging algorithm already used to or applied on the small R jet to reconstruct the jet or to tag the jets originated from the B quark decay. In this analysis also like improved data-driven method, like to estimate multi-jet in the signal region. 2 signal regions already defined based on if we have a tagged top or tagged B-jet and so on. So in this analysis, the mass ranges for the right-handed W boson, it will be varying between 1.5 TeV up to 5 TeV, as we can see from the plot on the top right, for the different masses with a different width. And in this analysis, let's say the expected limit, like we on the top, in the W right-handed W prime boson to be less than 4 TeV. So going now to switch the topic concerning like resonances in a single lepton or dilepton decay channel, and even in some analysis in multi-lepton decay channels. So in this analysis, as we know, like it will be the cleanest decay channels, since many backgrounds it will be with a low contribution. In particular, when we request like a dilepton or more leptons, like in the final state, it's a probe for like a several analysis, for example, like a Z prime in the sequential standard model, or some excitations from other models. The nice thing, or like in this kind of decay channels, it will highlight some other variables might be insensitive to the presence of a new physics, like for example the partial reconstruction of the final state and something like this. So in this analysis highlights like a different techniques and improvement, again, like estimating, like for example the background in the signal region, some reweighting techniques to get better data, Monte Carlo agreements, some machine learning techniques, like for example, deep neural network to reconstruct, for example, the final state of the top anti-top decay channel in the dilepton decay channel. So slide number 7 here, I'm going to highlight like the vector-like quark production in the dilepton and the 3 lepton decay channels. As already mentioned, this kind of vector-like quarks already addresses in several BSM scenarios, like the existence of this like of vector-like quarks. It will be mainly decaying to the 3rd quark generation, as well as like the standard model WZ boson and the Higgs boson. And this this kind of vector-like quarks can have like normal charges at the top and the bottom, and exotic charges, for example, 5/3 or -4/3. And this analysis, deep neural network already used to classify the jets originated from the decay of the, for example, the Z boson or again, like as I mentioned already, new variables already used in this analysis. Like for example, in the 3 lepton decay channel, we can use the HT, which is the scalar sum of the jets, and lepton BT as a discriminating variable, as we can see from the bottom plot on the right, and the invariant mass of the Z boson plus the leading or subleading beta jet in the case of the dilepton decay channel. So from the expected limit, as we can see, we can exclude this kind of vector-like quark, like a top T quark with a masses less than 1.6 TeV. So going to slide number 8, here the same scenario, but a single vector-like quark production in a single decay channel, and single lepton decay channel. Mainly this search is targeting the production of vector-like T quark decaying to top B quark and in association with the Z or Higgs boson, where the Z decaying leptonically and the Higgs boson decaying hadronically, mainly to B quark pair. In this analysis, the results already interrupted in several benchmarks, like for example, to set the limit on the mass, as well as the universal coupling constant. The events here, it's like divided based on the number of jets, like in the final state, and the B jets already, B-tag jet, it's called like a low jet in the case of T, top B quark and Z, and high jets in the case of T, top B quark and Higgs. So the discriminating variable here, it's called M effective. It's the scalar sum of the lepton and jets plus the missing energy in the final state. And we can see from the contour plots, we can exclude, for example, the coupling constant for at each mass point above the black one. And in the case of the branching ratio, as a function of the width as a function of the branching ratio, we can at each mass point we can exclude above the white contour plots, and we can see why we choose already this effective mass as a discriminating variable, since we can see the separation between the signal and the total background. So going to something which is non-resonant searches, like in this case, non-resonances in dilepton decay channel. As already mentioned many times, like recent measurements give a hint of possible like violation, lepton flavor violation, and like for example in the rare decay of the B meson into K meson and a pair of dilepton, in this case di-mu1 or di-electrons. Dielectron, and this result already interrupted with a 4 fermion contact interaction, 2 quarks, in this case P quark and the charm quark, plus 2 leptons in the final state, which will be either dilepton or dimuons. So in this analysis, like a limits already set on the contact interaction energy over the coupling constant scale, like to exclude in the dielectron decay channel for a value lower than 2 TeV, while for a dielectron decay channel it would be 2.4 TeV. As we can see from the from these two plots in the one BTAG jet region. So in slide number 10, here highlighting the heavy boson resonances in a semi-leptonic decay channel. In particular, here I'm going to highlight like the latest result concerning the W prime boson decaying into W boson and Higgs boson, where here Higgs mainly decaying to B quark pair and covering the mass in here. The targeting mass, it will be between 300 GeV up to 5 TeV. So in this analysis, like a new or improved B-tagging algorithm already applied to increase or to, let's say, to identify the B jets originated from the B quark decay from boosted Higgs already used. It's using the technique, it's called variable radius track jets. In this case, you will increase the number of, or let's say, captured B tagged from the Higgs decay in the boosted region. Two signal regions already defined based on the number of B tags, and the limits already set on the mass and the GH and GF for the coupling space, as we can see from plots on slide number 10. So we can execute the limit for on W prime boson to be, for example, less than 3 TeV, and we can exclude for each mass point, as we can see from the contour plot, at 4 TeV and 3 TeV and 2 TeV for different values for GH and GF. So on slide number 11, here I'm going just to highlight like some new results concerning exotic decay of the Higgs boson in the fully hadronic decay channel. It's already predicted by several theories. Here, the Higgs boson, it will decay to electrically neutral pseudoscalar boson, which is called A, and this A mainly decaying to B quark pair. Data-driven method or techniques already used to estimate the background. Displaced vertices already reconstructed from the combination of the collected standard tracks as an inner detector and what we call it large radius tracks. The number of observed events in the signal region is 0, and we set or exclude the branching ratio with a 10% for different masses of this A boson, as we can see from the plot on the top, and in while for the plot in the bottom here in different analysis combined with each other, setting 10% between 10%, let's say, on different scenarios. So finally, here I'm going to the last one, which is the long-lived particle decaying into hadronic jet in the ATLAS experiment, in particular in the muon system. As we know, it's sensitive from or protected in different models. Here, only we targeting the standard like Higgs boson particle with a mass of 125 GeV, and this particle, which is phi, decaying to 2 long-lived particle S. These S mainly decaying to the heaviest fermions here, like a pair of P quark or C or di tau decay channel. Also, as we can see from the plots in the bottom here, we set like exclusion limit on the branching ratio above the 10%, and in the plot on the top here by assuming different masses for S and phi, and we can see the expected limit. So here just showing as a summary plot for different analysis with the limits that we gain in the exotic group with the different scenarios, and here the limits on the long-lived particle as expected or predicted from different physics scenario. So finally, here going to conclusion. Let's say it's highlighting the new results from ATLAS experiment in the resonance for PSM resonances and non-resonances searches, as well as the exotic decay into long-lived particle. Different techniques you can find in these results or paper to increase the sensitivity of the new physics, and finally, as expected, like no significance yet on the top of the standard model. So everything looks like in agreement with the standard model in wide range of masses and cross sections. So thanks for until.
Thank you very much, Mohammed, for very nice review. maybe anyone have any question? No? If no, thank you again. And now we switch on to the supersymmetry from Atlas.
Okay, thanks. Let me stop sharing.
Mayuki?
Yes, hello.
Yeah.
I'm trying to share my slides.
Yeah. Please make full screen. Yeah, sure.
Do you see? Yeah.
Yeah, sure.
Okay.
Go ahead.
Yeah, thank you for giving me an opportunity to have a talk here. I will present searches for supersymmetry with the Atlas detector. Yeah, supersymmetry is a new symmetry between fermions and boson and provides a supersymmetric partner for every standard model particle with spin 1/2 difference. Here is a list of the supersymmetric particles. For this presentation, what is important is in particular chargino and neutralino, which is a mass eigenstate with a mixture of Vino, Higgsino. Yeah, the lightest neutralino can be a candidate on dark matter. The gauge content of the lightest neutralino is important because the lytic density is sensitive to it. Supersymmetry provides elegant solutions to many open questions. For instance, electroweak symmetry breaking is naturally predicted because the particles are closely related to the Higgs mass required to be relatively light by naturalness. And SUSY provides a good dark matter candidate and unification of forces. Moreover, the recent neon G- anomaly can explain in the SUSY. I would like to mention the recent G- anomaly in SUSY point of view. Supersymmetry at electroweak scale can explain the observed G- deviation. As shown in light figure, muon and electroweakino, which couple to muon and photon, can cause the deviations from the standard model. Light muon and electroweakino are required to explain the G- anomaly. The preferred mass range is well matched to our SUSY searches. We can search for the candidate models with muon and electroweakino productions. A left plot is exclusion limits in muon and lightest neutralino mass plane. The orange region are excluded mass ranges. The hatched bands indicate a few examples of regions that are compatible with the observed muon G- anomaly at 1 sigma level. These regions are good targets of our searches. Yes, this plot shows the production cross sections as a function of mass for SUSY particles. Productions with strong interaction of gluino and squark have copious production. Colored particles have significantly larger cross section than non-colored particles and were main targets in early round 2. Electroweakino productions have small cross section and are motivated by dark matter and the G- anomaly. And for lepton production, light lepton can explain muon G- anomaly. Yeah, each of these can decay in variety of ways of giving a rich set of signatures to search for. I have only one slide for strong production and third generation squawk searches. Many new results have been published, although I do not mention them in this presentation due to time limitation. As you can see in left plot, green masses up to 2.3 TeV are excluded. In light plot, stop masses up to 1.3 TeV are excluded. I will focus searches for electroweakino and lepton productions after this slide. In searches of electroweakino production, a strategy on the search depends on the mass difference of the lightest neutral SUSY particles, LSP, and next LSP. The first target is Vino LSP scenario with mass difference less than the vector boson mass. which has a LSP to be a good dark matter to match the observed dark matter density. This can be searched in final state of 3 lepton plus missing ET. And the second target is pure Wiener LSP scenario with mass difference around 100 MeV, where a doublet of Wiener state are LSP. It can be searched in final state with disappearing track. The third target is a large delta M region, which has not been explored yet. This can be searched in final state of fully hadronic final state. I will present results of these searches. The first search is a final state of 3 lepton plus missing ET from offshore WZ process. Target scenarios are Vino-Vino LSP scenarios where next LSPs are Vino dominated and LSP is Vino dominated. Challenging issue in this search is that we have a lepton PT down to 4.5 GeV for electron and 3 GeV for muon to get better sensitivity on smaller mass difference, so that there are large fake or non-prompt lepton backgrounds. We developed a BDT-based isolation used to tighten the requirements on the lepton with the lowest PT. We have a significant gain from the new isolation where electron and muon passing the fake electron and the muon passing the standard isolation are further reduced to quarter with 70 to 90% efficiency as shown in right middle plot. Primary discriminant is MLL mean, that is the smallest invariant mass of lepton pair with same flavor and opposite charge. Right bottom plot shows the distributions of MLL mean showing the standard model backgrounds as well as signals with various mass splitting. Signals demonstrate a cutoff matching the mass splitting while backgrounds do not. The dominant background is from standard model WZ events with only leptonic decays, which has 3 real and prompt leptons. The background is estimated using Monte Carlo and normalized to data in dedicated control regions, which are designed to be orthogonal and similar to the signal regions. This method is validated in validation regions where there are good agreements between data and estimation in light plot. Light plot shows light plot show in the results, the observed data are consistent with expected standard model background yields in left plot, and in a light plot shows the exclusion limits for Vino LSP scenarios. The limits are set at up to 300 GeV for delta M, about 25 GeV. Yes. Next search is a case with very small splitting, mass splitting. A mass difference is predicted to be of the order of 100 MeV in scenarios where the LSP is Wien-like and other Suji particles are decoupled. This corresponds to a charging lifetime of about 0.2 nanosecond. The long-lived charginos are characterized by distinct disappearing plaque signature and are reconstructed using at least 4 measurements in the Atlas pixel detector with no subsequent measurements in outermost silicon tracking nor any associated energy deposit in the calorimeter. The pion from the charging decay has too low momentum to be reconstructed as a track. A high momentum jet from ISR is required to ensure significant missing ET, allowing to trigger on the events. The final state are characterized by at least 1 jet, large missing ET, and at least 1 disappearing track with large transverse momentum. A main background is a fake, which arises from random combination of pixel hits. Fake background has unreal track, which is not associated to any other object. The shape of the fake background is estimated using the fake enriched high impact parameter control regions. Bottom left plot is a PT spectrum of pixel tracklet for disappearing track in signal region. Background predictions are shown by the various lines. An example of the expected signal prediction with charging mass 600 GeV is shown in overlaid inlet. No significant excess above the background prediction is observed. The exclusion limits are shown as a function of charging lifetime and mass. In middle plot, the pure Wiener lifetime is shown by the gray dashed line, where charging mass is excluded up to 660 GeV. Exclusion limits on Higgs-Zeno LSP is shown in right-hand side. In the case of pure Higgs-Zeno, charging mass are excluded up to 210 GeV. Yeah, next is a new search for electroweak production in fully hadronic final state without lepton. This search focuses for hadronic decay modes from W, Z, and Higgs bosons that take advantage of the large branching ratios and should provide sensitivity to heavier electroweak. A key technique for this search is tagging of boosted boson, where two quark jets are highly collimated and merged into a single jet. We use a boosted boson tagging with a combination of jet mass and jet substructure variables to identify jet with two-prong substructures. The taggings are optimized to maximize the background ejection, maintaining an efficiency of 50%. In this search, we inclusively target the mass difference between the produced electroweak and LSP greater than 400 GeV by selecting the high PT kinematics and explicitly reconstructing the two boosted standard model bosons. Left plot is the distributions of effective mass, which is defined as a scalar sum of PT of the two large R jets and missing ET. The dominant backgrounds are the two new plus jets with fake boson jets with two collimated high PT ISR jets. It is estimated by dedicated control region by inverting the tagging selection. In left plot, in left plot, no significant excess is observed. In middle plot, exclusion limits on Wiener production in simplified model are shown. In right plot, exclusion limits on various branching ratio assumptions beyond the simplified model are shown. In general, Wiener masses between 400 GeV and 1060 GeV are excluded for Wiener production, and Higgs-Zeno masses between 450 GeV and 900 GeV are excluded for Higgs-Zeno production. Yeah,
excuse me, but you have already spent 12 minutes and now have 3 minutes more.
Okay. Yeah, I will finish soon.
Thank you.
Yeah, last search is a direct pair production of leptons decaying into final state with two charged leptons and missing ET. As I mentioned before, light sumion is motivated by the G-2 anomaly. The final state is exactly two oppositely charged leptons with PT larger than 25 GeV and missing ET. Left plot is a transverse mass MT2, which is a kinematic variable used to bound the masses of a pair of particles that are assumed to have each decayed into one visible and one invisible particles. A signal with large mass splitting features high MT2 value, while WW backend has an endpoint of W mass. As you can see, no significant excess is observed. In right-hand side, this is the exclusion limit of direct sumion production. Sumion up to 600 GeV are excluded. And for summary, we explored the full RAN2 dataset with a wide range of analysis program at Atlas. We have no hint of SUJI so far, but there are still well-motivated phase spaces to be covered. In particular, direct electroweak and lepton productions are being scrutinized with promising opportunities in high mass and compressed scenarios motivated by naturalness, dark matter, and muon G- anomaly. Many new searches are ongoing to cover more phase spaces with new techniques. All the recent Atlas search results are available in this link. Preparation for round 3 is underway. We are looking forward to extend reach beyond round 2. Yeah, that's it. Thank you.
Thank you very much to Mayuki for a very nice review and saving time. Now we have some slot for question. Anyone have any question? If not, thank you again, Mayuki.
Thank you.
And the next speaker, Bruce, with multi-lepton anomalies at the UHC.
Can you hear me and see the slides?
Yeah, sure.
Okay. Thanks for allowing me to talk, and it's always nice to talk at Lomonosov since I am actually a graduate from Moscow State University. Okay, so let me dive right into it, and in order to do that, I'm going to spend a couple of minutes on the simplified 2HDM plus S model, which will help us put everything in perspective. So what you do, you know that the standard model has a complex doublet. You extend that with a second one, and if you add a scalar singlet, you basically end up having what we refer to as the 2HDM plus S. You can see there our paper and also paper from other colleagues that that delved into the theoretical questions of the 2HDM plus S. Now, so what you do is you go from the very well-known 2HDM potential on the left to the 2HDM plus S potential, where you have additional terms where the singlet scalar field is added, and the result of that is that you have quite a rich phenomenology that has not been explored by the Large Hadron Collider at large. There's so far there's 3 papers, but clearly the phenomenology is much wider than that. In order to make the long story short, what we do is that in this quite complex ecosystem of signatures, we're going to be focusing on diboson signatures. And we're going to assume that the multi-lepton anomalies that the LHC displays will be described by the dominance or the decay of a scalar around the mass of the electroweak scale decaying into SSSH, where HH plays a diminished role as we have already stringent limits on HH production. So the bottom line here is that this phenomenology is basically, for the most part, unexplored, virtually unexplored at the Large Hadron Collider. What people do typically is HH, but you will see a tremendous amount of phase space open up, but we do searches for dibosons where at least one of the bosons is not the Higgs. So we're going to be focusing on these signatures. And the thing that pops up first when you look at the signatures is multi-lepton fine states. And it is obviously work that we've been doing since 2015, 2016, where we, upon scrutinizing some features of the round 1 data, we formulated this model that we thought would be able to describe them, which later give rise to predictions for multi-leptons. So everything dates back to that time. And what I'm going to be showing now is not a result of scanning the phase space, but there is a procedure that has been put in place in order to avoid tuning or look elsewhere effects. So the significance of the excesses and anomalies you will see is in fact global, not local. All right, so the first thing that appears as a result of this phenomenology is that you have the production of the heavy scalar through gluon-gluon fusion, like the Higgs, but now it's heavier, and it decays into SH or SS. It doesn't, this really not a big difference when it comes to multi-leptons, and that will give you opposite sign dileptons in association with something else, and that something else is jets, but also, as you see on the right-hand side, B jets. So this is quite distinct from the standard model production. If you look at the lower left graph, the red curve is the standard model Higgs with the corresponding QCD spectrum of jets. This, because it's a dye boson signature, this BSM signal would come up with some jets. So this would be basically not the same phase space as the standard model Higgs. And also you would have B jet, which is extremely important. So this is not very different from the standard model, but different enough so that it requires separate searches. Another type of final states that explain also another class of anomalies is that when you have, because you have a large Yukawa coupling to the top, now you have open production of these bosons and also the CP odd with top, double, and single. And that gives rise to a different class of anomalies, producing same sign leptons, 3 leptons with B jets, including 3 B jets. And this explains the anomalous production of TTW, TT Higgs, and 4 top. 4 top especially is a recent type of excesses that both Atlas and CMS are reporting that has generated some interest in the literature. So you basically have opposite sign leptons, same sign leptons, 3 leptons with Bs and without Bs. So it gives you now an ecosystem of multi-lepton excesses. So let's look at the methodology, because the last thing we want to do is to scan the phase space and be swamped with Lucas way effects. What you cannot do and shouldn't do is try to run some sort of automatic procedure that would scan the entire phase space of all the results of Atlas and CMS to see whether you see a significant deviation. That's not what was done here. What was done here is that based on some features of the round 1 data, we figured that this is the model we want to explore. This model, as you've seen already, predicts anomalous production of multi-leptons. These were verified, especially in round 1 with very minor round 2 data in 2017 in this paper here. And then we decided, okay, we're not going to touch the model anymore. We're going to fix the parameters. We're going to fix the final states based on the prediction of this simplified model. So we are only looking at more data with the same final states where the regional excesses were seen, or final states that were predicted by this simplified model with no tuning of parameters and no scanning whatsoever. Essentially, what we said, look there and see what happens. And this led to, first of all, scrutinizing with a lot more data, some of the same final states, and identifying other final states that have not been explored before, such as, for instance, same sign leptons with 0 Bs and 3 leptons with 0 Bs and ZW with 0 Bs, where we see excesses as well. But again, these are not subjected to Lucas way effects because we set the procedure back in 2017. And you see basically a list of some of our papers that are documenting these excesses. So now what I'm going to say is that, okay, in terms of significance, when you combine all this significance within the context of the simplified model, this graph dates back to 2019, the significance is way above 5 sigma. The inability of the standard model to describe multi-lepton final states, and these are mostly seen in control samples, is insurmountable. And it has grown ever since. So we now know these are not statistical fluctuations. And in fact, we just published recently, a few months back, a paper in EPJC indicating that even in the Higgs sector, we have an excess in the production of leptons in association with the Higgs boson that is significant. So the important thing to bear in mind is that the LHC has a very serious problem in describing these final states in control regions. So what typically people do is they basically scale up Monte Carlos, or they reweight them to somehow hide the problem under the rug. And we don't think that is something we want to do. This is a recent paper that we published in Physics Letters, where we focus on the problem of the TTW cross-section. The TTW cross-section and the LHC, as we know, is significantly higher than predicted. And we work with some theorists to really go into the nitty-gritty of the calculation to ensure that no diagrams were missing, that we actually understand what the calculation was doing. And we concluded that the K factors that were used by the experiments were about right, and we basically confirmed that X's, and that this calls to obviously for theorists to do a next to next order calculation. Now, this table, obviously, I only have 12 or 13 minutes, so I cannot go through the wealth of all the data. This takes basically a whole seminar. So we have basically 1, 2, 3, 4, 5 types of leptonic excesses that are predicted by the simplified model with these very simple ansatz of a heavy scala decaying into SS or SH, okay? And the significance are here, and they are just growing, and they continue to grow. And there's been 2 attempts by theorists to explain the one in the top sector, but we don't believe they've been successful. And the fact that we don't understand the production of leptons with invariant mass less than 100 GeV is the fact. And it hasn't been explained by either high order corrections or the production of a standard model type of processes to date. Now, let's move on further. So we have this litany of multi-lepton excesses, and you can always play devil's advocate and say, well, this could be something that could be explained away, although it's very difficult to believe that you can have so many different types of processes with so many different kind of standard model processes failing. But now, of course, obviously, the key here is to identify in the data those resonances. And we have recently identified, we're going to come up with a paper next week of a possible candidate of S. We've scrutinized the available, publicly available data with diphotons and Z gamma in associated production, meaning this is not a direct production of S, as you saw earlier. This S is the result of the decay of a heavier boson that is produced directly. So what you see is, what you look at is diphotons and Z gamma in association with something else, they being those B jets or dijets or leptons or missing energy. And this is a graph that you obtain when you weight all those final states with S over B, and you can see this very nice structure here around 151 with a significance of more than 4.8 sigma global, not local, global. You can see the corresponding graph in terms of the p-value, where you can see the scan that was performed and the range with which it was performed. The range is motivated by the invariant mass of dielectrons that constrains the range, but also the availability of data. We couldn't go beyond 155. So that's really what constrains the search. And you can see this clearly defined peak in p-value where the gamma gamma is dominant, with some small contribution from Z gamma and BB bar that is not shown here. And this calls, and this will be in the paper, for experiments to do something that has not been done before. When people look at diboson signatures with diphotons and BB bar, they typically require that the invariant mass of the diphoton system and BB bar be equal to the Higgs mass, because they are concerned about the di-Higgs production. But we are arguing that in light of these results, the multi-lepton anomalies and this tantalizing 5 sigma around 150, that experiments look at gamma gamma BB bar in asymmetric configurations where gamma gamma could be anything, but BB bar would be off shell and vice versa. And you can see here on the left, the prediction based on the numbers from the data. So this is now a prediction, or what you would see with run 2 and run 3 data. The blue would be the signal normalized to the X's that I've shown you before, and the red is the standard model background in gamma gamma BB bar, where the gamma gamma would correspond to the on shell S. When the BB bar is the on shell S, and gamma gamma is off shell, then of course you have poorer signal to background, but both combined surpass the 7 sigma for one experiment, run 2 and run 3 data. And there's of course a lot of combinations you can do with this. So we are calling on the experiments, the paper will be calling on the experiments to reuse the gamma gamma BB bar data in a much broader context beyond HH. All right, so this brings me to my outlook and conclusion. So the first thing that needs to be borne in mind is that the LHC has clearly defined multi-lepton anomalies. They appear in corners of the phase space dominated by different processes, whether it is WT, TT bar for top, VV, TTV, VH, 3Ws. There's just too many of them to believe that mismodeling could be behind it, but we are open to any conversations. It's been already 5 years, by the way, with theorists and Monte Carlo experts to see whether this can be fixed. So far, we haven't seen an explanation, and papers get published in leading journals. These discrepancies can be explained with a simple ansatz, where a heavy scala around the electroweak scale would decay into SS or SH, where S could be treated as some sort of Higgs-like boson with a mass not too different from the Higgs boson. And also we've seen in recent months in a paper that we published in EPJC that also the Higgs data is not as compliant with the standard model as it may seem, in that there is a significant discrepancy of now more than 4 sigma in the production of Higgs in association with leptons. And last but by far not least, we have just finished an analysis of the gamma-gamma and Z-gamma spectra that are publicly available by Atlas and CMS in associated production, where we see an excess of at least 4.8 sigma global, around 151, and this further motivates diboson signature searches that would now be sensitive to the mass of H. In that the invariant mass of gamma-gamma BB bar can give us a quasi-narrow peak with a resolution of about 6% or so. And we're calling on the experiments to look deep into and expand the analyses that use gamma-gamma and BB bar final states. Thank you. Hello.
I'm sorry, I was muted. Thank you very much, Bruce, for very promising approach, very promising techniques in looking for anomalies for new physics, and excited results. Let's wait for round 3. So maybe anybody want to ask question? If not, thanks again.
Thank you.
And now the next speaker is Jacopo with rate decay at LHCb.
Yes. Hello, can you hear me?
Yes, sure.
And can you see the slides?
Yes.
Okay,
go ahead.
Yes, thank you very much. Yes, I will talk today about rare decays at LHCb, the recent developments in rare decays at LHCb. At LHCb, we want to use rare decays to probe new physics, of course, and rare BDKs can do the job at much higher scales than direct searches if we express the effect of new physics in terms of an effective Hamiltonian in which the high and low energy contributions are factorized into Wilson coefficients and effective operators. And the effect of new physics could be that of modifying the values of Wilson coefficients or even adding new ones. And a coherent set of anomalies has arisen in measurements involving B2SLL processes in the past few years. So we need to understand more about these anomalies. So today I will talk about recent developments in the study of rare BDKs at LHCb. And in particular, I will talk about the measurement of RK, the measurement of the properties of B and BS to mu mu, which will be available on arXiv starting tomorrow. And I will talk about the branching ratio measurement of the BS to phi mu mu decay and the first observation of BS to F2 prime mu mu. Then the angular analysis of BS to phi mu mu, and finally the measurement of photon polarization in lambda B to lambda gamma decays. So let's start with RK, which is defined as the ratio of branching fractions of B plus to K plus mu mu over B plus to K plus EE. And it has been measured in the using the full LHCb dataset, which corresponds to 9 inverse femtobarn. And the standard model prediction is 1 with corrections of the order of 1%. The main challenge of this analysis is to get the differences between muon and electron detection under control. And in order to do so, LHCb uses a specific algorithm which allows to take into account the energy of photons which are detected in the calorimeter and add this energy back to the electrons if the direction of the photon is compatible with coming from an electron. So the Bremsstrahlung photons is somehow recovered. And then RK is measured as the double ratio using the B plus to J psi K normalization mode, and the rare and normalization modes share an identical selection in order to cancel the systematic uncertainties. So plenty of cross-checks have been performed in order to perform this measurement, and in particular the R-J psi ratio is supposed to be close to 1 even in presence of new physics. So it's a stringent cross-check, and it does not benefit from the cancellation of systematic uncertainty in the double ratio. And as you can see, the result is compatible with 1, which means that we are doing the job right. And also the R psi to S ratio has been measured, which instead is a cross-check of the double ratio with Q square away from the J psi pole. And also in this case, the result is in agreement with unity. So what's important to understand is that these cross-checks show that the control of the efficiencies is at the order of 1%, which is really good to perform this measurement. So these are the results. The mass fit of the rare modes has been performed in 6 different categories. And RK is extracted as parameter of the simultaneous fit, while the normalization yields are incorporated as Gaussian constraints. This is the final result, and the uncertainty is statistically dominated. And the main systematic uncertainty comes from the fit model that is used to perform the fit of the rare electron mode. And the results show a 3.1 tension with respect to the standard model prediction, which gives evidence for the violation of lepton flavor universality in B2K LL decays. Let's talk about now the measurement of the properties of the B and BS to mu decays. The standard model predictions are very clean since they depend only on one Wilson coefficient and a single hadronic constant. And another interesting quantity that we can define is the effective lifetime of the BS to mu decay. The effective lifetime depends on the contributions of the heavy and light mass eigenstates. And since in the standard model, only the heavy mass eigenstate contributes to this quantity, this asymmetry is supposed to be +1 in the standard model. To perform the measurement, 2 normalization channels have been used, the B to K pi and the B to J psi K decays. And after a strong PID cut on muons, the main backgrounds which are left are the combinatorial background, which is coming from a random combination of tracks, and some partially reconstructed semi-leptonic background in the left sideband, and doubly misidentified B and BS to 2 hadrons, in which the hadrons are misidentified into muons, which peak in the signal region. The simultaneous fit is performed in 10 different categories, which correspond to 2 data taking runs and 5 bins of BDT. The first bin of BDT is rejected since it's dominated by background, and using the full LHCb dataset, which corresponds to 9 inverse femtobar. The yields of misidentified and partially reconstructed backgrounds are estimated on simulation and are fixed in the mass fit, while the combinatorial background is left floating. So we come to the results of the mass fit, and in particular, the BS to mu is observed with a statistical significance of more than 10 sigma, while the B to mu and BS to mu gamma, the initial state radiation, are compatible with the background hypothesis. So these are the results, and in particular, the branching ratio of the BS to mu decay is found to be in agreement with the standard model, while on the other 2 upper limits are set. And the uncertainty is statistically dominated, while the main systematic uncertainties for the BS to mu comes from the knowledge of the fragmentation fraction ratio, while for the B to mu from the exclusive background mass model. Now let's talk about the effective lifetime measurement, which is performed in a tighter mass window such that the misidentified and partially reconstructed background in the left side bands are cut away, and such that so we can loosen the PID requirements. The background subtraction is performed in 2 BDT bins using the S-weights technique, and the final fit is in fact performed on the background subtracted decay time distribution, and this is the result, which is compatible with the standard model hypothesis at the level of 1.5 sigma. Now, I want to spend a few words on the branching ratio measurement of the BS to 5 mu decay, which was previously measured by LHCb using 3 inverse femtobarn and has been now updated with the full LHCb dataset. And the phi is reconstructed through the decays into 2 kaons, and a tight mass window is chosen around the nominal value of the phi mass. The normalization mode is the BS to J psi phi decay, and these are the results in bins of Q squared. And if we focus the attention on the bin between 1.1 and 6 GeV squared, depending on which standard model prediction we consider, we have a tension of 3.6 or 1.8 sigma. The total branching ratio is determined by summing up the various contributions in the Q square bin and corrective for these vetoed regions in order to get rid of these resonances. And these are the results in which the first uncertainty is statistical, the second is systematic, the third is from the extrapolation to the full Q square region, while the fourth one here is the uncertainty on the knowledge of the branching ratio of the normalization channel. The dominating systematic uncertainties vary across the bins. However, the most important ones are the knowledge of the branching ratio of the normalization channel and the model used to generate the Monte Carlo signal events. Together with the branching ratio measurement comes also the first observation of the BS to F2 prime mu decay. Again, the full LHCb dataset has been used, and a wider mass window around the F2 prime nominal value of the mass has been chosen. A two-dimensional fit to the mass of the B and the mass of the F2 prime has been performed in order to separate the signal from other non-resonant contributions. And these are the results, which are in agreement with the standard model prediction. And the decay is observed with a statistical significance of 9 sigma. The main systematic uncertainties comes again from the knowledge of the normalization channel branching ratio and the uncertainty on the ratio of branching fraction of phi to kk and F2 prime to kk, which enters the calculation of the branching fraction. Then we talk about the angular analysis of BS to phi mu, which was performed by LHCb again using 3 inverse femtobarn, and now it has been updated using 8.4 inverse femtobarn. A 4-dimensional fit is done in order to determine the values of 3 helicity angles. A 4-dimensional fit to 3 helicity angles and the B invariant mass is done in order to determine the values of 4 CP averages and 4 CP asymmetries. The event selection is identical to the one used to perform the branching ratio measurement, while the non-resonant contributions is at the level of 1 to 2% and is ignored in the fit. The results are in overall agreement with the standard model expectation, even though a mild tension is observed in FL. Moreover, a fit to the CP averages observables varying the values of C9 has been performed, which shows again a mild tension with the standard model of 1.9 sigma. The uncertainty is statistically dominated, and the systematic uncertainties vary for the angular observable, which is considered, and across the Q-square bins. So let's talk now about the measurement of the photon polarization using lambda B to lambda gamma decays, which is a flavor change in neutral current process, which is suppressed in the standard model. And the photons which are emitted are predominantly left-handed or right-handed for the anti-lambda B decay. The angular distribution depends on the cosinus theta p, which theta p is the angle between the proton momentum in the lambda rest frame and the lambda momentum in the lambda B rest frame, and on the value of the photon polarization, which is supposed to be +1 in the standard model, plus some corrections. or -1 for the anti-lambda B. This analysis is sensitive to right-handed contributions in B to S gamma transitions. 6 inverse femtobarn have been used to perform the measurement, and the background from random combination of tracks is suppressed with the use of a boosted decision tree. While the main background, which are left, are the combination of real gamma with random photon, which is called combinatorial background, and lambda B to lambda eta, in which the eta decays into 2 photons and one of them is missing. So these are the results. The mass fit has been performed in order to constrain the signal to background ratio, and a fit to the cosinus theta p distribution has been performed to extract the value of the photon polarization, and the acceptance is parameterized with a 4th order polynomial. In addition, also the measurement separately for the lambda B and anti-lambda B has been performed. And these are the results, which are in overall agreement with the standard model prediction. And the main systematic uncertainty comes from the limited knowledge of the angular shape of the combinatorial background. So I come to the conclusions of my talk, and as you can see, as you may know, a coherent set of anomalies has arisen in measurements of rare B2SLL processes, and several new measurements have been published by LHCb in the field of rare B decays. So we are living quite some exciting times, and we need more measurement in order to understand the nature of the flavor anomalies. Thank you.
Thank you, Jacopa, for the nice talk, for the very nice review of the LHCb results. Does anyone have any questions? No? Okay. If no, thank you again.
Thank you.
And our last but not least talk for the session. The next speaker is Michel?
Yes,
Please.
can you hear me?
Yeah, sure.
Okay, let me share my screen. Can you see the full screen?
Yes.
Okay,
Go
perfect.
ahead.
So I'll start.
Okay.
So I will present the measurement of the very rare K2 pi nu decay, which is done at the Na62 experiment at CERN. The Na62 experiment is located in the north area and is using the SPS beam, and is a continuation of the quite rich KEON program at CERN, which started even more than 30 years ago with Na31 and then continued in Na48 and so on. And now we are in this Na62 second run, second data taking run. So I will report on the results which are from the first run on the data taken between 2016 and 18, and I will focus on the 2018 analysis and result, and then give the combined result from the full run 1. So here is the detector layout. So we are getting the beam from SPS at 400 GeV primer protons. Then they hit the target and creating the secondary beam at 75 GeV momentum. And about 6% of the secondary beam are the kaons, which are of our interest. So we have then the decay region for these kaons, which is 60-meter long. In a high vacuum, and we have about 3 megahertz kaon decay rate in the experiment. So how we do the measurement? So first of all, we take the kaons before they are decaying in the differential Cherenkov counter, and we measure their momentum with the silicon pixel detector, and this is how we know that there is a kaon at the beginning. Then it enters the decay volume and it decays, and then with the downstream detectors we again measure the momentum of the downstream track. So for the signal it's pi plus. We have the scintillator hodoscopes to get the precise timing and suppressing some backgrounds. We have the Cherenkov counter again to provide the precise timing and to suppress the muons and identify the pions. And then we have a set of calorimeters, electromagnetic calorimeter, liquid krypton, and two hadronic calorimeters. Then we have the muon detector, again for the suppression of the K-mu2 decays, and we have some photon veto detectors along the whole beam or the whole vacuum chamber and around the detectors. There are the large angle vetos and the small angle vetos as well. So this is the layout of our detector. So about the PINU decay itself, it's a flavor changing neutral current loop process, and it's highly suppressed in the standard model due to the quadratic G mechanism. And thanks to its dominant short distance contribution, it's very clean theoretically, and it's very precisely calculated. The relative uncertainty from the pure theoretical aspects is about 3%. Here you can see that the predicted standard model value is 8.4 plus minus 1, but this is dominated by the uncertainties on the CKM parameters. The true theoretical uncertainty is lower than that. And part of this, or why it's like this, is except of the short distance contributions, we're getting the hadronic matrix element from the K3E decays. So thanks to that, we are canceling some uncertainties there. Okay. Thanks to its rareness, this decay is very sensitive to the physics beyond the standard model. And here is just some list of several papers where this particular decay is mentioned as a good opportunity to study various beyond the standard model scenarios. For example, the Z prime models, the Littles-Higgs, custodial random syndrome, supersymmetry models, lepton flavor violation, and leptoquarks. And yeah, these are just a few of them I mentioned here. Precise measurement of this PINU decay can discriminate among different new physics scenarios thanks to its sensitivity to this new physics effect. So this is the history of the measurement. So you see that it's a decay which interested people for a long time. And the first observation was done by the Brookhaven experiments 787 and 949, where they published the first measurement of the branching ratio. And then the NA62 experiment published results from 2016, 2017, and then 2018 combined with these two. And I will focus on this 2018 data set in this talk. So what is how we do the measurement or the analysis for the PINU? So our signal is just the single charged pion in the final state and nothing else, and quite a lot of missing mass. So we actually define the region by means of the missing mass, which you can see on the top right side of the slide, where we have the region 1 and region 2 defined, together with the most abundant background events from the decays, from the kaon decays. We've also shown in the red line the kinematics of the PINU enhanced by 10 to 10 factor to be visible. So what we need to do is we need to match in time and space the upstream kaon with the downstream pion, and be sure that there is nothing else around, and it's kinematically within the regions 1 and 2. We have these two regions to suppress the dominant background from the decays of the K2 pi plus 2 pi, K2 pi plus pi 0, which you can see as a nice peak at the pi 0 mass. So to do that, the requirement is order of 100 picosecond timing between the subdetectors, mostly between the upstream and downstream part. Then we need 10 to 4 background suppression purely from the kinematics, so basically on the missing mass. Then we need a high suppression of the muons to get rid of K-mu2 events. And then we need a strong pi0 suppression again to get rid of the dominant background of K2 pi. So our signal selection is done in based on the missing mass, which is calculated in various ways from the measured values of momentum of the downstream and upstream part in the spectrometers. Then we use also the reference beam values computed as an average of the beam. And then we also use the momentum reconstructed in the Cherenkov detector reach. So these are 3 different ways how to define the missing mass to cross-check and to be sure that our missing mass is well calculated. So as mentioned, the selection is a single track in final state, which is matched to the upstream K+, which is identified in the upstream detectors. Then we do the pi plus identification in the reach and then in the calorimeters. We reject the photons and we reject the multi-tracks because one of the backgrounds which is entering region 2 on the site is K3 pi events where you have 3 tracks in the final state. So then we have to define the decay vertex of the kaon, which is within the 60 meters of the fiducial volume. And then we restrict ourselves to the specific momentum bins because of the pi mu discrimination in reach. Below it's not sensitive, and also from the upper side we have to have some energy for the photons to be seen in the calorimeter, and so they can be rejected. And here are just some performances for the muon rejection. We're having like 10 to 8 rejection. For the pi0 rejection, it's also 10 to 8 rejection, and the resolution on the missing mass is 10 to minus 3 GeV square. Okay, it should be missing mass square, and the time resolution is at the level of 100 picosecond thanks to the Cherenkov detectors. So now the background contributing to this pi nu sample is well, the dominant one is coming from the upstream decays. So how it works? This kind of a background appears when the kaon decays upstream and only the pion is entering into the signal region. So for example, the pi0 from K to pi decay, the pi0 is absorbed in the upstream part, for example, in the collimator, and then the pion itself can go inside our decay region, where it will be matched with some accidental kaon and will create some fake decay vertex and can signalize the signal event. So these kind of decays are dangerous, and we have quite stringent cuts to remove them. And actually, in 2018, we installed the new collimator to help to remove these early decays, to absorb more of the decay particles upstream. So the whole data sample is split into the subsets S1 and S2, which means with the old collimator and with the new collimator. The S1 sample is about 20% of 2018 data, and S2 is about the next 80%. So in total, the upstream backgrounds contribute in 2018 at the level of 3.3 events. You can see the numbers for S1 subset and S2 subset in the table below. So then we have the background from kaon decays. So as mentioned before, we have k mu2, k2 pi, and k3 pi, and k4 as the main backgrounds, where the k mu2 and k2 pi are estimated from the data with the formula which is given above. So basically, we calculate what is the fraction of background in signal region, which is measured on the control data. Then we check what is the how many events are in the background regions after applying the full pi-nu selection, and then we multiply these two numbers and we get the expected background in the signal region with the pi-nu selection. On the picture on the left, you can see the control K2 pi sample, which was used to study the tails of the missing mass of the missing mass square distribution, and you can see that it's modeled quite precisely with respect to the Monte Carlo. So here again in the table are the numbers of the expected background for these different sources, and you can see that the upstream background is quite dominant background for our experiment. So we use the control. The whole pi-nu analysis is done as a blind analysis, and then we use some control regions to validate the background, and this is how it looks like. So you can see that we see 8 events in one of the control regions where we expect 10.9, and we see 31 events in another region expecting 32, and so on. You can see the other ones on the left side of the plot, and you can see that it fits quite well our expectation. So here is just the same table like it was in the last slide. So the signal regions are still blinded. These are these regions with these small squares. And now when we open the signal regions, we see 17 events in 2018 data sample.
Michel, I'm sorry, you are talking about 15 minutes. Please go to the final results.
I will go. Yeah, so these are basically the results. So you can see the separate data samples 2016, 17, 18, S1 and S2, and the combined result is this 10.6 plus minus 0.9 plus the statistical error on the 10.6 at 68% confidence level. So just a short interpretation of the result. This result is basically excluding large deviations from the standard model, and hence we need a precise measurement to understand if there is something new in this kind of decay. Here are just some examples how it is affecting various beyond the standard model scenarios. This K plus to pi plus nu bar is related to the neutral mode by the Grossman-Neer limit, and actually our result also gives the limit on the neutral mode. So the future prospects for the K to pi nu decay is well, we are taking data for the this year and following years, and we updated a little bit the upstream region to suppress further the upstream backgrounds. So we added some new detectors to better control the upstream backgrounds. Okay, so I presented the complete result from the run 1, which is 2016-17 plus 18, and the result is for now compatible with the standard model, and it has 3.5 sigma significance. And we are going to we continue the data taking when we did some improvements in the hardware of the experiment to suppress the main background sources. Okay, that's it. Thank you.
Okay, thank you very much. Maybe anybody want to ask the last question? Opening session? No? If no, thank you again. And okay, now our session is over. And in conclusion, I would like thanks again all speakers for their useful talk and valuable contribution to the conference, and all those who stand with us in this Sunday evening. Thank you.
Okay, colleagues, thank you very much for all the speakers of this session, and in particular for those who still remains to the very end. Also, we are very thankful to Sergey for the job he has done for the conference, being the chairman of this session. And just I would like to say to those who are innumerous now here as me and some of my colleagues, that all presentations of the plenary session and also session A are available, they are recorded on our website. And so it means that all interested persons who even are not participants of our conference have a chance to listen to your talks, and then even to ask questions, but privately, but ask questions. So I think that we shouldn't be confused about our not numerous presence in this very late hours, even from Moscow time. Okay, well, once again, thank you very much, and I hope to see you everyone to see you tomorrow on the next day of our Lomonosov conference. Thank you very much.
Thank you, Alexander. Thank you all.
Thank you.
Thank you. Goodbye.
Bye.
Bye-bye.
Bye.